Okay, before to deep dive a bit in foundation model, there will be some security announcements. So yeah, please, if you can run the video, please. Thanks a lot.
Welcome to ESRIN. In the unlikely event of an emergency, any kind of emergency, you can report it to the security team from any internal phone by dialing 3333. From an external phone or a mobile, please dial +39 069 418 0333. Emergency numbers and a site map can be found on the leaflet you were issued along with your security badge. Ignoring it is at your own peril. In case the building needs to be evacuated due to fire or any other kind of emergency, please follow your ESA host to the nearest exit. If you lose your way, follow the exit signs. To leave the building, do not use the lifts, only use the stairs. During the evacuation, refer to ESRIN security guards and local area coordinators for advice. Once outside, move towards one of the 4 external meeting points on site. Do not return to any of the buildings until the all clear is given.
Okay, thanks a lot. Okay, let's start. So I'm very happy to open and kick off this workshop on foundation model for Earth observation. So we are in ESRIN, the ESA Center for Earth Observation, and this event is co-organized with our colleague from NASA Impact. Personally, I'm Nicolas Nonjepe. I'm with the ESA PhilLab. So PhilLab is kind of a disruptive innovation lab within the Earth Observation Program Directorate. And in the opening, virtually, because he couldn't make it, we have Rahul Rabachandran from NASA Impact. And we are definitely very thrilled and excited to have this event with you guys. So this week, it will be all about foundation model, as you can guess. The idea of this event is really to create a dynamic and like a moment for you and the community to exchange on this topic. We'd like to showcase the latest breakthrough in AI, deep learning, and foundation model at large. We'd like to highlight what are the different applications or science that could be derived from this technology. And of course, I mean, if we could also project ourselves and move towards commercialization and try to define what could be the next EO product and services triggered by this technology, that would be even better. We have to be also factual and look for the current limitation, look at the current knowledge gaps and challenge in this new technology. And I hope that this comment that we receive from you will kind of nurture what could be the roadmap that will be implemented by the agencies, either NASA or ESA. As you may know, on Wednesday, there will be some hands-on session. We'd like you to practice actually on foundation model and with the mindset of openness and open science, of course. I'm very happy because here, actually, the ESA Academy granted 5 sponsorship for students to travel and come here at ESRIN. We would like to inspire as well the next generation, and I think this is very important as well to do it. So the agenda would be very packed. We have 3 days with, as you may see on this program, with 2 parallel tracks. There will be one in this Bighall. There will be another one in the Magellan that you pass by on the left when you enter the building, the site. So 72 oral presentation, 12 sessions, 76 poster presentation. All the poster session will be in this room, that's in the tent, which is on your left there. There will be an invited session on Wednesday morning and an interactive ideation session on Tuesday afternoon as well. And of course, you will have food, you will have drink, you will have coffee. So there will be a cocktail that will be served in the tent this evening. There will be also many coffee breaks. The lunch will be served at the canteen at ESRIN here. And for those that subscribe for it on Tuesday afternoon, Tuesday night, we'll have the non-hosted dinner in Frascati Center. So a few rules about security. So you are not free to go wherever you want here on site, so you should remain in these rooms and also in the Magellan. There will be as well the canteen, so yeah, you are not welcome to go wherever you like, so please stay around the designated event area. Please always wear your lanyards and the badge at all the time, because it will help the security to identify the participants. For those that received the welcome email, there will be some shuttle bus in the morning and also late evening for you to come back. There will be some announcement later today, because I don't know if you see, there is some strike tomorrow for the train in between maybe Rome and Frascati. So there will be some announcement about that maybe later today. We'll try to give you some accurate information on that. Lunch, I already mentioned that. So you can use the prepaid vouchers for those that subscribe for it. Otherwise, you can pay by cash or credit card. And for the speakers, there will be the technical zone in the back of each of the rooms, so in the Bighall and also the Magellan. So please upload your presentation in advance. And again, this event is for you, it's for the community, so please actively participate. Be also considerate for others, meaning that we have different background. There might be some Earth observation specialists, deep learning, AI scientists, geoscience scientists, so please be considerate about that. Share your insight and also have fun, of course. And with that, so this is the agenda for this opening session. Later on, there will be some video recording from Simonetta, the director of Earth Observation Program. Then we'll have a talk from Rune Froberhagen, who is the head of the Climate Action, Sustainability and Science Department. And then there will be a panel led by my colleague Anka. With that, I'd like to also invite virtually Raoul that couldn't make it, and I hope that he can be online and give some few words. So just bear with us some few seconds. Yeah, Raoul is there, fantastic. Can we check the audio? We cannot hear you yet. Yeah, you are muted.
Can you hear me?
Yeah, we do hear you. Go ahead. Fantastic.
Yeah, awesome. First of all, my apologies for not being there, but I'm super excited about this workshop. As most of you know, that AI has already become an important tool on how we use Earth observations, and especially as we go towards bigger and bigger models, more complex models. I think it is imperative for us to work together to build these models in a way that it's useful for the entire community. That was the primary motivation for us joining forces and holding this workshop. So this workshop is the first step towards that, in working together and building models that are useful for the entire EO community. I would like to say a big thank you to ESA for hosting this workshop, and a huge, huge thank you to Nicholas and Anka for the amount of effort they've put in hosting this workshop. So if you get a chance, please make sure and tell them thank you for the effort that they have put in. I will join you all at the third day when we reconvene back with debriefs of the different sessions. So I look forward to hearing the debriefs. And thank you again, and hope you guys have a great workshop. Nicholas, back to you.
Thank you very much, Raoul, for your words. Thanks. So next, also virtually, there will be an opening welcome from Simonetta Kelly, the director of Earth Observation Program. And actually, as you may know, there is the Geo Symposium or workshop, which is also organized in Rome at the same time, starting today, so she could not make it. So please, if you can run the video for her. Thanks.
Good morning and welcome. Today I have the honor of opening this workshop co-organized with our colleagues from NASA to discuss the exciting advancement in geospatial foundation models. As you all know, we are witnessing an unprecedented surge in Earth observation data. Vast amounts of information are continuously generated by a growing number of EO missions, whether from space agencies like Esa-Nasa, commercial entities, or expanding new space sector. In fact, the Sentinel missions alone generate several terabytes of data every single day. Together with NASA, we aim to push the boundaries of what EO mission data can achieve. Foundation models represent the next big leap, offering groundbreaking potential to enhance analytical and predictive capabilities in geospatial applications. One of the most promising benefits is the ability to address the scarcity of labeled data, reference points, and in situ observation, long-lasting challenge in this field. Of course, embracing foundation models for EO data comes with challenges. As a community, we must work together to adapt these models to unique characteristics of EO data, including multimodality, integrating data from SAR, optical, and other sources, multi-resolution, spanning from sub-meter scale, 30 centimeters, to kilometric scales, high dimensionality, particularly relevant for upcoming missions like CHIME, multi-temporal, capturing dynamic changes over time. Beyond the technical challenges, it is equally important that we focus on demonstrating and consolidating the benefits of foundation models across the entire EO ecosystem. We must also explore commercial application, ensuring that these models and value not only to scientific research, but also to Earth observation products and services. For this reason, it is essential that our scientific community is well-trained, fully prepared to exploit the resources to a maximum potential. This is why I particularly welcome the hands-on session, practical approach of this workshop. Open science and education remain at the heart of ESA mission, and this event exemplifies the spirit of collaboration between ESA and NASA. Foundation models present a unique opportunity for the EO community, big tech companies, startups, researchers, commercial players to work together, ensuring that we harness this technology not only for the benefit of earth sciences, but also for commercialization and business opportunities. In closing, I wish you all the best for a productive workshop, as this is the first international workshop of foundation models for EO, co-organized between ESA and our friends from NASA. This is a really milestone moment. Let's make most of it and have a good workshop. Thank you.
Perfect. Okay, it's time to move to the next speaker. Rune Floberg-Hagen is the head of the Climate Action, Sustainability and Science Department within the Earth Observation Program Directorate. The floor is yours, please.
Thank you, Nicola. It's my privilege and honor to welcome you here to ESRIN on behalf of ESA as the local host and organizer. It's also my privilege to spend some 20 minutes with you, hopefully, to explain a little bit what is cooking in the kitchen of the European Space Agency, not only in terms of foundation models, but in general what we are doing in order to generate and enable positive action for our planet. But before I do that, I'll start with, for those who don't know ESA very well, a little bit what we are all about. So ESA is consisting of 23 member states, as Slovenia recently joined as number 23. We have a convention which dictates what we are supposed to do, and we are located in various places around Europe, and we have a total annual budget of about 7.7 billion in this year, 2025, out of which we are quite proud to say in the Earth Observation Program Directorate that we account for more or less exactly 1/3 of that amount. So this says something about the focus on the Earth observation and the applications and services that we are enabling through our program activities. Where you are today, ESRIN, we are about 1,000 people working here on site from various parts and corners of the agency, but also from various parts and corners of Europe. It's a place that is used a lot for meetings, and this is one example. So we have thousands or tens of thousands of visitors each year, but it is also a place where we do a lot of activities linked to data management, high-performance computing. We do a lot of innovation, both in terms of what you know and what we're going to talk about here, what is born in what we call the Phi Lab, but also in more general terms for Earth science. The program directorate, called Earth Observation at ESA, is spread over actually 4 sites, if we include headquarters. So the technical activities linked to the bending of the metal and building the satellites is not done here. That's done out of our site in the Netherlands. Some of the climate activities are run out of our site in Oxfordshire. But the bulk of the activities linked to innovation, linked to earth science, is managed here from ESRIN. ESA is a pan-continental space agency, and we cover all activities in the space domain. And here what you see on this slide is basically what we are doing in order to make the most out of the public sector and also private sector investment into the missions and into the services that we help enable. And it's a little bit described how we are organized in order to do that. The title of my presentation here is Enabling Earth Action. So obviously I'm going to talk mostly about what is in the lower left here and also in the lower right, where the innovative part, the transformative part, and the disruptive part of the space program are being discussed. We have, meanwhile, as a result of decades of, I would say, good public sector investment in Europe, we have a very healthy ecosystem of satellites and satellite missions. There is an abundance of data, how to extract information and enable decision making and also positive Earth action is, as I say, one of the key focuses of the evolution of the space program. And right now we are working towards the next ministerial council. For those who are not familiar with the terminology, this is the place and the meeting in Europe where we get our funding for 3-year slices of time, basically, and the next of those is going to be in the last week of November in Bremen in Germany, and is a very important milestone for space in Europe, and it's also a very important milestone for you because it's going to dictate how much money you will get for doing foundation models supported by ESA, at least in the coming 3 years. The ESA Lab is a home for many of these activities here in our house, here in ESRIN. We have a building behind here which offers the opportunity for collaboration, in which there is a lot of fail-fast activities, but also fail-forward activities that are being run and being managed, and foundation models is one of these topical areas. And we also, of course, try to support the good ideas and the things that turn out to be feasible from that by helping taking these solutions, these opportunities to the market. So this is at the core of what we call the Phi Lab. And we are happy to say that this type of investment that we do in the public sector into all of these activities, it pays off because there is companies that are making revenue and also even breaking even at some point based on the activities that take place. Here are some examples. I'm not going to talk much about them here, but just to exemplify that besides foundation models, many of the things that we are talking about here are linked to, for example, cognitive cloud computing in space. It's also linked to quantum computing, and other activities that might seem to be a little bit far away from what you directly measure with Earth observation in the first place. But if you look carefully at it, there is quite a lot that can be done. Yeah? So we have the fortune to make use of this thing called the Phi Lab and make it available to you as a community. In fact, we also see that there are new types of Phi Labs popping up across Europe, at least, built on this model in which countries decide that they would like to co-fund activities in this domain together with ESA to, if not copy, then at least make the best out of what we have done and learn from our mistakes in order to generate more disruptive innovation and more opportunities for startups and emerging players in the field. So all of that means that on top of the missions that I showed before, which were 86 in number, there is also a second kind of ring of missions, if you remember the plot that I showed before, in which we are enabling a lot of other, usually faster, smaller scale, but also highly innovative satellite missions to become available. And only early this year, for example, we launched 3 of these satellites I say we are supporting here. We are not a customer. We are not, let's say, the owner of these missions, but we are partner and enabler of these activities, supporting the companies that would like to realize their dreams. So this is about PhilLab. We also have a science hub here, which is a similar facility, but focusing more on Earth system science and on climate science. This is a facility in the Olive Garden behind here. You might have the opportunity to visit, where we offer opportunities for collaboration in Earth science. We offer the opportunity for you to bring your people here, work directly with a high-performance computing facility and with all the data that we have from our missions to realize sprints, scientific sprints, and deep dives into things that cannot be done efficiently, at least by sitting at home in your office. The Earth observation program is also very much targeting the climate discussion, and that might not be a surprise for any of you. All of the so-called essential climate variables that can be monitored from space, there are some 36 of them. The number varies a little bit with the work done by GCOS, but we at ESA, we are responsible for delivering 27 of those as input to the UNFCCC and IPCC activities linked to the status of the climate, for example. So this is just to say that the use of foundation models that we are discussing here is not only for innovation and commercial use or for new things. We also intend to apply it on things that we have been working on for a very long time, and we like to make them better, more efficient, and perhaps we managed to extract even more information from those data sets than we have been able to do so far. At the heart of all of this, we should not forget that there is a lot of policy behind the activities driving the space program today. Let's say 10 years ago, even 5 years ago, most of the space program were driven by service monitoring needs, Copernicus, for example, or scientific needs. Today, we are seeing policies in the international scene and certainly in the European scene popping up in which space is not a key driver, but space is an enabler. So we are being asked to provide information in support of all of these things that I show up here. The SDGs is a trivial example, perhaps. A more challenging one is the convention on the support to the Convention on Biological Biodiversity. There was a big meeting in this very room not so long ago when we had the first workshop, which was looking at what Earth observation can do in that domain. And of course, we do not measure directly the biological biodiversity, but we are pulled into this discussion because we have something to offer. And the more and the better our technologies work to extract this information from our data, the stronger and stronger the embedding of that will be in the policies in terms of verification, monitoring, reporting, and so forth. And therefore, also the stronger the funding of these type of activities we will be able to get in the future. And that holds for all of these examples that I show on the screen here. Maybe you have your favorite one. What I can tell you is that for us at ESA, this part of the landscape, the enabling and the support to the policies, is becoming a stronger and stronger drive over our investments and therefore also of the member states' investment in the Earth observation program. Now, if you thought that we have a lot of data today, there is going to be a lot more, not only with the expansion of Copernicus and the extension of, let's say, the new generation of the already flying ones, but also the fact that there are ever more research missions coming into the game. Just a bit more than a week ago, we launched Biomass, which is a mission carrying the first P-band synthetic aperture radar in space. And what it's going to do is to be able to measure through the canopy of the tropical forest, let's say, the volume and mass of the active biomass, basically. And we are going to be able to monitor the health of the carbon absorption system of the world, the natural one, on a continuous basis. And this obviously is data that will be combined with other types of information linked to the carbon cycle and which will be very, very useful for the extraction of information. So the idea, of course, is that through the investment in the space program at ESA, we pioneer these type of technologies, we maximize the return of the mission, but we also see what can be done beyond the time horizon, if you will, of any single space mission, in this case biomass, that I mentioned just because it's the most recent one. So all in all, we're going to see a tripling, if not quadrupling, of the amount of data coming from space. And if you combine that with data coming from non-space resources or sources, in situ data, models, and so forth, it's quite phenomenal what we have to tackle. So how do we extract information out of all of this? We have developed a concept for that at ESA, which we call the Earth Action, which is really how to put all of these elements into a single framework. In the past, we had a climate program, we had a development assistance program, we had Copernicus. We will still have Copernicus, obviously, but the key point here is that in terms of enabling of Earth Action, we try to bring all of these activities together under one single coherent umbrella. One strategy, one plan, maybe more than one report, because there's quite a lot of information, otherwise it'd be very thick. But the point is that we have given ourselves the task to work together to, first of all, measure the planet, then understand, develop predictive capabilities, enable decision-making by those who have that as a mandate, and therefore do the positive action for the planet. And a bit more detail around all of this, because this is what is going into our new program proposal, is really that we are trying to address all of this coherently for Earth system science, which is one of the topics that we will be talking about here at this conference, climate science alike. In the past, they were in two different programs, and that doesn't really make a lot of sense. Enabling policies, I already talked about that, yeah? And this is a challenge because the policy framework is complex. I don't know how many of you have spent time reading thousands and thousands of pages of policies. It's not the most exciting material for reading, but it is of direct relevance for what we do and how we guide our investment. Then, readiness for global action and partnerships. This is about taking what we learn from our investment into the space program and do good in other places, build partnerships with other countries and regions around the planet. Could be Latin America, could be Africa, could be in Asia. Yeah? And we are seeing nowadays space and Earth observation as a public good, a common good, and we want to make good use of all of this. So all the partnerships with the entities that are responsible for the policies and have investments and programs that are supportive in this domain are our partners in this evolution of the space program. We call it co-design and co-development because this goes beyond somebody sitting in an office at ESA and writing what he thinks the member states should pay for the coming years. Industrial competitiveness is super important. Those of you who have read the Draghi report will have understood that Europe needs to do something to remain competitive in an economic sense. And how you combine that with sustainability is a challenge. Earth observation, again, is a player in all of this. And we need to enable a strong and healthy Earth observation sector. And that's an area where we are against very steep competition. And of course, all of that is supported by a good number of enabling elements, out of which disruptive and transformative innovation is one, but not the only one. We have other instruments like the open calls that some of you might know, or the Sentinel user preparation program, and so forth, and the tools and the facilities that I mentioned before. So what I'm trying to say here is that there's a lot going on in the space program that is not directly being discussed in this conference, but it's taking also the input and the output of this conference, actually input from you, but towards us as an output from this conference that we can use in filling all of this stuff with content to make sure that we do good in our definition, in our calls, in our ITTs, invitations for all of you to participate in our program. And that's why workshops like this one are super important, not only to exchange ideas, but also to generate positive momentum for the future. Now, a little bit more detail about this meeting. So obviously, I kind of already said that. We are dealing with massive volumes of data. And so in this context, the foundation models and the geospatial foundation models that we are discussing here are super important. Now, we have also seen lots of initiatives in this domain, maybe 100, yeah, focusing on developing geospatial foundation models in the past couple of years. Nevertheless, in terms of production environment, in terms of operative and operational services, we have seen a little bit less. So why is that? Maybe that's a topic for discussion here. And also, maybe in this context, we should be discussing some of the benefits that we can get from these foundation models, like how they can help craft high-performing task-specific models when in situations where training and reference data are scarce or even expensive. Yeah? Can we accelerate the time to market for the AI models? Can we enhance the data analytics at scale in order to somehow extract more insights from the data? I hope the answer to that one is yes. And also how to unify the various modalities, okay, the type of data, radar, optical. I mentioned biomass is a new data source. There could be others, atmospheric chemistry, for example, with a totally different data set. And how to extract and make good use of the data characteristics in terms of spatial or temporal scale into a common representation that can be used for all of this. And if we can do that, my commitment towards all of you is that we will use that in the enabling of Earth action in the future. Okay. Now, just some examples about what is going on. We have been working recently on something which well, I guess we can simply put it as making the Sentinel data AI ready. Major Tom is the name of that, but it's more than just a data set creation. Major Tom, by the way, for those who don't know, is a figure from David Bowie's songs, for those who are a fan of that guy. For example, from Space Oddity, was frequently there. In any case, I did not invent his name, but the whole point here is that we are trying to propose, at least, or make use of Major Tom as a research activity, as an enabler for creating a standard that is there to curate, to share, and combine these large-scale EO data sets. And this is highly successful. There's a lot of Sentinel-1 and Sentinel-2 data in there already, and this will enable and make sure that the Sentinel-1 and 2 data are also AI ready for the future. We also launched recently, in collaboration with IBM Research in Europe, Jülich Supercomputing Center, and a project which is led by DLR called TerraMind, where we look into how to make good use of these open source resources like Major Tom to create foundation models that are of super high quality. Now, I do not feel competent to talk about TerraMind as such. There will be much more competent people doing that later today and also later in this week. But the point is that there is a lot that can be done by this type of partnerships, this type of activities that we do together. And there are others, like the one that we do together with the Norwegian Computing Center and so forth. And in the end, bottom line of all of this is that perhaps in the future, on top of having Major Tom, or TerraMind and other models available, we also would like to enable, let's say, a more direct interaction with the machine to be able to extract all of this information. So like simple text information saying, I want data on the latest Sentinel-1 images over Rome, which is affected by oil spill, for example. Just as a simple quote that you can do, and that we have some sort of automatic delivery of this data. I do not want to quote the name of the facility that is done by Gigatech in similar ways, but this type of assistance, of course, is also part of the job that we are doing to support foundation model works. TerraMind, I think I said enough about that already, because others will be much more competent than me to do all of this. But today, to our knowledge and to our benchmarking, this is the best performing AI model in terms of geospatial foundation models today. Yeah? And we released this on Earth Day, actually, on the 22nd of April. So I don't want to repeat myself here, but to say that what we are trying to do here is to enable the collaboration with you and between others, maybe those who are not in the room today that can be invited the next time, to address these barriers of enabling this type of solutions. What is key to us in ESA is to make use of the FAIR principles, so findable, accessible, interoperable, and reusable data, so these open aspects are important, and we believe that this is key enabling task and key enabling feature of all of this. And for that, we have even developed with the colleagues here Earth Code, which is the collaborative open development environment, which is supposed to enable all of this, to promote the coordination, to enable the reusability of the research, and also of the research, sorry, and of course also to support the consistency, transparency, and collaboration process in general. I mentioned Earth System Science and the Science Hub behind here. We believe that foundation models do have a strong potential to help fill in scientific knowledge gaps. For those who have read the new ESA, Earth Observation Science Strategy, you will have seen and will have read that this is one of our key objectives, to do that as quickly as we can with the information that we already have available. And we do believe that this is an area in which the foundation models can actually contribute quite a lot. And part of that work in ESA, for those who are not part of that ecosystem today, is that we organize that around clusters that are pertaining to particular scientific domains like atmosphere, hydrology, carbon cycle, and so forth. And they're all listed here. And we offer the opportunity to use the Science Hub, and I repeat my offer from before. If you have ideas for how to use foundation models in this context, we are more than welcome to come to us, and we will be happy to host you and your team to collaborate with us, with the data, with the models, and using the computation facilities that we have available for all of that. I'm coming towards my end, but I cannot avoid talking for 1 second about the prospect of foundation models for climate. If we can do good things for system science, climate science is the same, and there is already quite a lot of work based on AI going into the essential climate variables. But we do believe that a lot more can be done in this domain. Yeah? And this is obviously a domain of the space program which, at least in Europe, still is well funded. Yeah? And we are therefore very keen to explore, and we are doing that already, the possibility of driving or writing up a new AI strategy, which is how we support, in particular, climate action in this, let's say, in this way. Yeah? Already today, as I said, some of the ECVs and also the tipping point analysis and the coupling between ECVs is being addressed through AI, but a lot more can be done. There is money behind all of this. There is a little bit of money now still before the next ministerial council, but for sure there will be much more money after November 2025 when we get let's say, a refill of our wallet. So in summary, I'd like to close here saying that the foundation models for us at ESA is an excellent opportunity for the community, for the big tech companies, for startups, and also smaller companies, obviously, and commercial players in general, to work together and basically makes the most out of this wonderful, wonderful opportunity. So we hope that you will be a critical friend, that you will state what you think, and also tell us what you think is a priority, and we will listen to all of that. And with that being successful, I'm quite sure that there will be future workshops, international workshops of this kind, also in the future. Maybe one last slide for me is to make sure that you're all aware of the Living Planet Symposium. It's a major event in Europe on Earth observation. We expect somewhere between 5,000 and 6,000 people in Vienna to discuss all aspects of Earth observation in the last week of June. And for those of you who have studied the program, you will know very, very well that there is plenty of room for the type of activities that we're discussing in this workshop. So with that, I say make space for good. Thank you very much for listening to me, and have a great 2 days. Thank you.
Thanks a lot, Rune, for this exciting talk. Now I invite on stage actually Anka, my colleague from ESA, and also all the panelists. Please join the stage.
Thank you, Nicola. Thank you, Rune, and to Simonetta for the opening remarks. It's my pleasure to welcome the panelists on stage. Yeah, we're missing one. So good morning and welcome also from my side. My name is Anka Angela and I will be moderating this panel today. So this panel is really bringing together a distinguished group of thought leaders and practitioners spanning space agencies, academia, industry, and the policy sphere. The panel looks ahead towards the future of AI for Earth observation, and we know that foundation models and AI are not just technical innovations, but they're becoming essential tools to understand and to manage our planet in this era of rapid environmental and societal changes. So this conversation that we will have today will set the stage for a deeper technical and scientific discussion to take place in the today and tomorrow and on Wednesday. So without further ado, I will like to invite everyone to dive in and to hear the views of our invited speakers, invited panelists, to hear what they think, where AI for EO is headed, what breakthroughs are on the horizon, and how we can address the challenges that come with them. So I will introduce the panelists individually, and they will give each their opening remarks, opening thoughts, and then we will go to a Q&A session. So we'll start off from the left side. So we have with us today Kevin Murphy. Kevin Murphy is the Chief Science Data Officer for NASA's Science Mission Directorate, where he advances AI, cloud computing, and data science across 5 science divisions. He ensures NASA's data is discoverable and usable globally, overseeing strategic planning and implementation of data systems. Previously, he managed data systems for Earth-observing satellites, initiated the commercial small-sat data acquisition program, and led the Satellite Needs Assessment Working Group. At Goddard Space Flight Center, he developed projects like near real-time science data production systems and scientific data visualization systems. He has numerous awards, including the NASA Exceptional Achievement Medal, and I'm very happy that he's joining us today. So welcome, Kevin. Thank you for being here.
Good morning, everybody. Really happy to be back out at ESRIN. Maybe a little story about myself before I start. I think the first time that I came to ESRIN was in 2011. So it's been about 15 years since I've come out here, and it's incredible the amount of growth, the number of satellites in the community that is built up off of that. Thank you very much for the introduction, Anka. And I'll get right into this so I don't belabor it. But NASA does invest quite a bit of funding into AI, and we do that in 2 major ways. We invest in kind of automations of systems that are off the planet, right? So those are rovers, those are helicopters, those are satellites that need to be able to incorporate information that they identify out there, use that information to make the best decision in a very far away place because those latencies are way too long. What I'm going to talk about with you today, though, is how we take the data that those instruments collect and then use it for our benefit with foundation models. So the overall strategy for science within the SMD Directorate, or the Science Mission Directorate, which contains divisions that look at Earth science, heliophysics, astrophysics, planetary science, and biological and physical sciences. All right, so a very disparate group of people that have different tools and different techniques. The way that we do that is that we identify some of these high-level goals, like accelerate and advance scientific discovery. One of the things that you notice when you work across multiple divisions is that the types of problems that they have are often similar. The solutions may be a little different, but the types of problems in terms of how do you format your data, where do you put it, how do you make it available, are somewhat similar. The second one is, as we look towards incorporating and making high quality models, how do we do that so that they empower and embed the scientific knowledge from the group of people that developed it into the model itself, right? How do we compose our machine learning scientists along with our domain scientists so that we get a really good high quality product on the backside? And that takes quite a bit of work, both in terms of selection, model development, refinement, revisions, kind of beta releases, and then finally the full releases. Typically that takes us about 9 to 12 months of some dedicated series of meetings to evaluate the models, especially with known benchmarks. Finally is fostering higher payoff innovation. So pursuing the cutting edge of how we do these kind of smaller pieces of work and then linking them together so that they really produce something that you couldn't have had otherwise. So our approach to doing this without pictures, I'll have pictures on the next one just to make you feel a little happier, is that we have a 2-year strategy where we develop the core foundation models based on the highest quality, longest term data sets which exist within our archives. And we do at least one of those for each of our 5 divisions, so heliophysics, planetary science, earth science, et cetera. And we develop a large language model built on the publications which reference those data sets, right? So it's not just how the internals of those long time series work, but also what people were able to observe by using those outside of this foundation model construct. And we're pretty far through that. And the next slide will show you that we've done 3 of the 5 already, although within Earth Science for the Prithvi, we've done 2. We've done a weather and climate, and we've done the harmonized Landsat Sentinel, which I think will be built or discussed a little bit in here. Once we get these built, we want to do multimodal models within those models, okay? We want to be able to use our heliophysics model, our Earth weather and climate model, and our lunar model to do some predictions in terms of space weather events, especially as you look at kind of the LEO or the low Earth orbit or cislunar orbits as we try to send humans back into those locations in the future, all right? And as we get out to Mars, something similar would happen. And then as we launch satellites like Roman next fall, which will produce an incredible amount of information, how we develop foundation models based on that and the LISA observatory as well. Over the long term, however, what we want to do is we want to cross-link these models and develop something called accelerated discovery using agents. And this is stuff that we are just beginning to put together in terms of the strategy and the implementation plan. So a prototype of this should be out in the next, I don't know, 6 months or so. So here are the kind of pretty picture versions of the 5+1 strategy where you see we have earth science, biological science, astrophysics, planetary, and heliophysics in a large language model that runs through the astrophysics data server or the scientific explorer to help put those pieces together. These are models that are either out in the wild today on Hugging Face or will be soon, as is with the heliophysics model at the bottom. So our first release was the harmonized Landsat Sentinel product in conjunction with IBM Research. And that was one of the smaller models, but that is one of the highest value data sets that NASA has. And it was about a 600 million parameter model, took some hours to produce. MERA 2 is a simulated data set. And that ended up being a 2.3 billion parameter model with about $2 million worth of supported compute. But you can do turbulence, weather, and severe prediction in that. And solar dynamics is just moving along very quickly. This is a partnership that we have with the National AI Research for Researchers or resource for researchers out of the National Science Foundation. This is where we're using about 1/4 of the NVIDIA GPU system for about 1/4 of the year. And we've seen some really good results in how well this does predictions over standard methods, up to 16% in some instances, which is incredible, right? Like I remember being at these types of conferences 10 years ago and you'd be like, hey, I got a 0.5% better or 1 or 2% better improvement, and it took me all year. Well, we've been working on this since, I guess, January, and we have already gotten 16% better in some of the same types of things. Okay, so this is my last slide. This really describes the goal that we're currently kind of iterating on, which is accelerated discovery. And that's how we think we link these AI models together in each step of the scientific life cycle, because that's what we're trying to do. This is accelerated discovery for science. Links to publications, the models, the large language models, the open software code, and visualizations to expedite that time that it takes to discovery. So if we can reduce the amount of time researchers have to spend on any one of those steps by 10 to 20%, we can do more science with it. The tools would be available openly following our standard practices of open science, if you're familiar with what they are. Using kind of agentic workflows is the next big challenge in AI, and something that's going to take us some time to work out, potentially in meetings like this. We've already got our critical enablers put up. We've got our science foundation models. We've got our large language model. We've got a lot of the data. Currently, it's in commercial cloud environments, but in the future, we can also bring it back on premise. We're working very closely with industry and partnerships, and we have a large high-end computing system at our Ames facility in California that has a number of GPUs which are optimized to this work. So with that, I'll stop this, and you guys can ask me some questions. Thank you.
Thank you very much, Kevin. I'd like to introduce Dr. Yifang Ban. She is the lead of the recently established Geo AI for EO convener. She's the professor and director of the Division of Geoinformatics at the Department of Urban Planning and Environment at KTH Royal Institute of Technology, and an associate director at Digital Futures in Stockholm, Sweden. Her research focuses on Earth observation, big data analytics, and machine learning or deep learning for urban mapping, urbanization monitoring, and wildfire and flood detection to support sustainable and resilient development. Yifang, you have the floor. Thank you.
Thank you very much for the introduction, and it's a great pleasure to be here. I really see so many AI EO foundation model in the community here. So here I want to talk about the recently established AI for EO working group within the group of Earth observations, group on Earth observations, and how to accelerate Earth intelligence for all through artificial intelligence and Earth observation. So this is our QR code. If you're interested in joining, please scan it, but I'll have it in the end as well. So here I'm wearing the Geo hat. So as you all know, our planet is facing grand challenges from urbanization to loss of biodiversity that has a tremendous impact on our society, and also extreme weather events, including urban heat events, cost 500,000 deaths per year. And also pollution that is even more extreme, affects claim 9 million lives per year. And we have 2.4 billion people do not have access to nutritious, safe, and sufficient food all year round. And for many entire nations, rising sea levels, drought, and floods are becoming existential risks. So now is the time to use Earth intelligence to make better decisions for people and for our planet. So this is where GL comes in. So at GL, we made it our mission to deliver Earth intelligence for all through participation like many of you. So GL is a global partnership involving 116 governments and over 162 organizations from academia, business, UN, civil society, so we're very broad, bring together EO providers, users, and also practitioners to promote open, free, equitable access to EO data and also Earth intelligence solutions. So basically, the idea is to support more fact-based, more sustainable decision-making. So in November 2023, GL has a new post-2025 strategy. It's called Earth Intelligence for All. So within that strategy, we would like to integrate Earth observations, models, and innovative new technologies, including artificial intelligence, machine learning, and plus others, into the design of services that provide Earth intelligence. So AI for EO is highlighted in this post-2025 strategy. As we all know about Earth observation big data, and there are a lot of opportunities and challenges. So in terms of AI for EO, we have advanced deep learning tools that can accelerate a lot of automatic image processing, classification, change detection, time series processing, multimodal data fusion, and accelerate many applications, agriculture, air pollution, biodiversity, disaster monitoring, and environmental change monitoring, and specifically SDG monitoring. So therefore, with this backdrop, we established the AI for EO working group. There are many different goals, and I will not say too much, but more specifically, here are the 4 major objectives. It's promote cross-disciplinary, cross-community collaborations. EO scientists, data scientists, AI experts, practitioners, decision makers will come together. We would like to support capacity building and knowledge exchange, develop, disseminate cross-cutting AI tools and resources solutions. Finally, not least, enhance data-driven decision-making and support, policy support. So that's our goals, and what we have done so far is we divided into 4 different working groups. So when you scan the QR code, you will be brought into the 4 areas, so you can choose what you're interested in doing. We also organize webinars on legal, ethical issues of GL spatial AI. We plan activities at Argus and also participation in AI for Good. And also just to showcase a few examples of my own team's work, AIEO for 2D and 3D urban mapping, urbanization monitoring, as well as for wildfire detection and monitoring how to detect fires as early as possible using AI models, and also how to monitor the fire's progression in near real time. So let's work together to protect our beautiful but yet fragile home planet. Thank you. So scan the QR code before it disappears. Thank you. So welcome all.
Thank you very much, Yifeng. It is my pleasure now to introduce our speaker from the European Commission. So we have with us Federico Fierli. He is an expert in the Research General Directorate of the European Commission, so DG RTD, seconded from EUMETSAT. His activity focuses on supporting and promoting the uptake of climate and environmental data in science, services, and policies. Federico is an expert in atmospheric science, climate, and Earth observation. and he works closely with users in EU programs, now on current and upcoming research programs at the EU. Federico, I pass you the floor.
Yes, good morning, and thanks for inviting me. I don't know if there are slides. Oh, okay, perfect. Here they are. Yes, Federico, thanks for the introduction, and very happy to be here. I mean, I can probably tell that my first time in ESRIN was a bit before you, was in 1998 as a student of the University of Rome. But I mean, it's a pleasure to be here. Basically, the main element that I want to give you is really something that is going across European Commission, the European Commission programs, and also my experience in a space agency. So the numbers that have been also mentioned by Rune and Simonetta are there. So basically, in the last 30 years, we have an increase of an order of magnitude of the number of Earth observation capabilities, and even a larger order of magnitude in terms of the amount of data and the diversity of data. So basically, there is a terrible growth of the European programs on Earth observation, not as fast as AI, but I mean, is one of the most important technological and scientific growth that we have seen in the last couple of decades. And this is built on meteorological satellites, on the Sentinel program, on the Earth Explorer mission from ESA. This at least at European level. And this is backboned by programs that are implemented still at European level, like the digital twins, Destination Earth, that have been recently mentioned, and also the Copernicus services that really want to bridge the gap and to enable a vast amount and a vast type of users in order to best access the data. AI and the foundation model are central to this, because these are really becoming a very fundamental tool to work with this data. I tried here to put some perspective and question from the point of view of someone working at the Commission, and then trying to identify which are the direction of the new programs. So the first question is that has been also mentioned by Simonetta in the beginning, is the cross modality. So the satellite data that comes from different techniques, they have different formats. They have different representativeness, they give different information. And most of the information can be important for one single thematic, for one single element. The importance of AI in this is to make data fusion. Data fusion is, I mean, here I give you an example about wildfire that have been mentioned. So for wildfire, we have information that is coming from vegetation, is coming from weather models, weather forecast models, like the one from ECNWF, to have an idea on how the fire season will go at different time scales. Has elements on plumes, like for instance this one from the Sentinel and MTG. So these are plumes of a fire in Greece. So this gives the position where the fire are. Elements on the pollutants like carbon monoxide that are linked to the emissions and the burnt area. All these elements are contributing to build one single vision and one single bunch of information that is important for many purposes. So, for instance, the purpose of monitoring on long term, on predicting at different time scales. I mean, for instance, one of the needs for prediction of wildfire and readiness for wildfire season is the analysis of historical data. So there is a need to merge together an enormous amount of information. For this, we also need to go for universal representations. So the possibility to have tools that are valid for different purposes, going from emergency to climate change, to climate models, and so on. One example is, for instance, one project that is called Weather Generator, that is supported by Destination Earth, that really aims to put together the different scales from weather to climate. The possibility to have scalability. So basically to have a general model or a general approach that can be used at the different regional scales. For instance, the Geo-Regional Association is a good example for this. So working from the global to local scale and then adapting to the stakeholders. Also, there is the question of having, introducing new data sets. So basically there are additional data sets that are coming and that these may be integrated into models. I gave you the example of wildfire. Another example is about air quality. So in air quality, for instance, information comes from different sources and different types. And you may need to integrate from the single observation of ship tracks, that is a very important source, to trends that can be detected by multi-year analysis. Accumulated data, this is the example for ammonia, and ammonia is a data set that has a quite important error, and that is, for instance, for this you need to accumulate the data over years, or for instance reports a tendency, general behaviors, or general evolution of emissions. All this information may be merged together, for instance, in having emission estimates. Just to think about the story of the Paris stocktake, that we are now starting, and how it's important to have tools to have a good estimate of emissions. And here are a few challenges. I will not go into that because I really expect to learn from you here during this workshop, but I really would like to put the point from the point of view of the stakeholder on the data quality and trustability. So basically, you need to apply the outputs of these models to things that are important for the society, that are important for the economy, that are important for the planet. So you need to have accuracy, and also you need to be trustable in terms of the decision makers. Because we know that these models or this approach, for instance, for the wildfire can lead to the point to say, okay, do I need to go with the aircraft, or how to deploy the aircraft to combat fires? And these are key decisions. So for this, you have trustability. You have many aspects that are there, for instance, the interpretability and so on. And I also have put here just a few points that we consider important in terms of perspectives in research. So explainability, the capability to go on the supervised learning, multimodal models, because one of the points is really to integrate social data, impact data, so to have something that is really able to work with different type of sources, different type of shape of data, federated learning, but also the possibility to go to simplified models, a strategy to simplify the models, for instance, for a satellite to put them in the ground segment, or even in flight, in order also to deal with the computing needs. I stop here, and I thank you very much.
Thank you, Federico. I'm sure many of these topics will be addressed in depth over the next few days. So let me introduce our fourth panelist. Today we have with us Professor Gustavo Camps-Valls. He is a distinguished physicist and full professor at the Universidad de Valencia. He brings a wealth of expertise in AI and causal inference, specifically applied to the world of geosciences and remote sensing. He has an extensive research with an H-index of 100 and recognized as a highly cited researcher, is an IEEE and Ellis Fellow and a member of the European Academy of Sciences and Academia Europaea. He approaches the topic of foundation models with a keen eye on the complexities of EO data, and shared with us that he believes the true power of these models will only be unlocked when they transcend the identification of correlations and begin to deeply integrate principles of causality and the underlying physics governing our planet. So Gustavo shared with us a short video about his group, so I would like to ask my colleagues in the back to play this video to learn a bit about the activities that his group is leading. Okay, thank you. I really like how this puts a human spin on on everything that we've heard from our previous speakers. Would you like to say a few words? Yeah.
Okay. Well, thanks for the invitation, and I thought that the video were like better than just like a 5 minutes speech, right? And anyway, I would like just to highlight the fact that our research agenda is basically building on 3 main blocks of integrating domain knowledge in machine learning, just to make it more consistent and eventually sparse, more compact, and eventually like lightweight. The second step of our approach is to, again, incorporate knowledge, but this time from physical understanding or biological process understanding or chemical. And that will not only make it more consistent with what the domain science is about, but also about we want these models to reveal some properties that we cannot really measure, so learning about the latent representations that the algorithms can actually learn from data. And the third part of our agenda, or research agenda, is not about encoding knowledge, but decoding knowledge. We want to learn something in the scientific endeavor, right? We don't just are happy with deployment, right? But we want to learn. And as a scientist, I would say that interpretability is non-negotiable. Right? So we should kind of advocate for these algorithms to become like more transparent, trustworthy, and of course more interpretable. That speaks directly to not only to interpretability but to causality, and that's why I was mentioning this important point. It's been like 2,500 years since we as humanity have been talking causality. And now we have like these kind of very nice oracles, I would say, between LLMs and foundation models. But we are not happy with just using and asking the oracles, but we want to understand what are the internal mechanisms of what is that. And we can eventually have to harvest this very nice opportunity to ask what-if questions, not just what is there, right? And how is happening the things, but what if we activate or deactivate some particular process, or what would have happened if I acted differently? So it is not only about learning, but also encoding domain knowledge in terms of causal relationships. And in that regard, I think that that, of course, speaks to a new family of foundation models that should be trustworthy, compact, and interpretable, and grounded on and aligned with principles that we all believe that there exist in nature. So yeah, that was kind of a summary of our research agenda and where we are at, and we believe that foundation models are a very good opportunity to boost all our knowledge, not only just to apply them and solve technical problems. Thanks.
Thank you, Gustavo. And our last panelist is William El Sayed. William began his career at the French Ministry for Economics, working on technology policies, and he later joined Mistral AI at its inception as the right hand to the CEO, Arthur Mensch. Currently, William is developing Mistral's public sector go-to-market strategy and leading customer R&D projects, driving the company's mission forward in the AI landscape. William, I give you the floor.
Good morning, everyone. I'm really delighted to be here, as it's the first time Mistral is traveling to Rome, so it's a great honor. Thank you very much for your warm welcome. I will try and first to give a bit more of a sense of our vision as a company, and then I will move to more VLM, vision language models, topics. So just a quick words on Mistral today. So it's been founded 2 years ago. As a EU-based company based in Paris, and in 2 years, so now it's more than 250 people. We have opened 4 offices, obviously Paris, but also London, Palo Alto, and Singapore. So we have 1.1 billion of funding to basically train those foundational models, and I will get back to that right after. We have trained more than 15 models in less than 2 years. Foundation models, mostly open source. That is also going to be the topic of my presentation. We have also built a platform to serve those models in SaaS, but also on-premise. And obviously, we have now a huge network of partners and customers, not only at the EU level, but it was very important to start with the EU to build great collaborations at the scientific level, but also at the industrial level, and obviously now all around the world. So now a few words on open source, because it has been the project of Mistral from the beginning. We wanted to decentralize AI. So when the 3 French founders working in private AI labs wanted to create a company, the purpose was quite clear. It was to decentralize AI because it was mainly served through private APIs back in the days in 2022 with the release of ChatGPT, which was one of the best demonstrator ever of a technology. And we wanted to make sure that this technology was usable locally, was customizable, and was explainable. So 3 things that are very hard through private APIs. So we released open source models that you can see here. Our 2 first open source were pushing a bit of pressure on the open source, I would say, ecosystem, helping the others also to build on top of that. So we obviously made significant contributions in the field. And what you can see here is that the last DeepSeek model that is really now catching up with the private models is a MOE. It's a technology that we've been working on from the beginning. And so there's kind of a very interesting positive loop here where open source is catching up. And I think that's great news, as you can see, catching up with the very best private models today. So that's a very positive trend, I think, and we are committed to continuing that progress. Why do we believe in open source? I think it's quite clear. First, you can build secure private AI that you can deploy wherever you want. So I think that's important when it comes to owning your data, owning your models, your core competencies, all your processes. So that is obviously the first reason. Then you can customize them very well. So you can basically continue pre-trained models. You can fine-tune them. Obviously, that's the whole purpose of what we're doing here also at ESA, is to make them relevant for the field. Then you also control the full stack from the GPU to the UX. I think that's key nowadays. And you avoid lock-in, which can happen pretty much in technology in the past 50 years. So now, why do we train VLMs? When we look at the classic vision models, they are pretty good at solving simple tasks or precise tasks. Here you can see that a model that is more than, I would say, more than 20 times smaller than a VLM can make the job for understanding images. But the thing is that you cannot properly reason on top of that image, and so that is why VLM also was a great breakthrough in the field, is that now you can, I would say, reason on top of an image, and you can connect text, and so tokens, to pixels. And that is something that is quite new, and that has been very much the center of our project, in the past 2 years. So we've been working on those use cases that you can see here that are quite obvious. Image captioning, OCR is now progressing a lot, data extraction and processing, analysis of complex images, so that is really what is changing right now, and the fact that you can build personal assistants and visual assistants. If you take a look at the VLM architecture right now, there's a few advantages. First, as you are connecting pixels to text and language models, so you can reason on top of this image, so that is first. Then you can, it's adding one more sensory inputs in an agentic workflow. So if you think of a whole agentic workflow, this is really game-changing. You can build more relevant workflows with vision. And also, these models are generalist and multitask in essence. So you can basically ask way more things, and you can use one model instead of 25 back in the days if you had to analyze or I would say if you had to solve a very complex problem. Then on the other hand, if you look at most of the use cases today, why it's interesting to use VLM is that they are fast on small images first. they can support variable image resolution. So they are very accurate on real world and high resolution images. And obviously they can process large documents with interleaved text and images. And that is also, I would say, game-changing today. A use case that we train a lot on is the scientific content explanation. So if you take, for example, a document like this, LLMs are quite strong at explaining those figures and those charts. So this is something that is working well. Another one is that you can, for example, here generate a web page out of a simple drawing that you made. Like this is also an example of reasoning over an image. So that is game-changing compared to models 3 years ago. And now if we take a look at the current models that are available, so we are putting a lot of pressure in the open source ecosystem because you can see that there's no more difference between private models and open source models in vision. So you can see the main benchmarks here. So our 12B model is performing as well as a lot of private models, and even better sometimes for the small size models. So this is a good news also if you want to experiment a lot of tasks locally, if you want to try a few stuff. That was the purpose. And the very last open source release is Mistral Small, multimodal also, that is working quite well on the main benchmark, vision benchmarks, and here also competing with the best private and I would say other open source models. So it's the right moment, I think, to try new stuff because capabilities are already ramping up, and it's really a moment where we're learning a lot about the use cases. Now, if we take a step back on the VLMs, they are right now great captioners, for sure. They are great at document understanding and chart understanding, but they are still very bad at reasoning over images. So it's just I would say it's just the very infancy of VLMs. And the coming progresses I would say in the next 2-3 years will have direct impact on robotics, and that will be very easy to observe. The VLMs, the research right now is not focused only about execution, so it's not only working on the trainings like distributed training, CUDA kernels, system engineering, but right now it's also about trying out new architectures. So several projects ongoing, obviously, multimodal fusion, input data, looking at more diversity in the input data. So we're working a lot on using radar images and a lot of very, I would say, images that you cannot find easily on the open web, because that is what is lacking right now. Obviously, transformer variants and hybrid models. So there are a lot to do right now, a lot of research left to do. It's not only about execution, so and it's really the infancy of the field. So I hope we can dive into more details during the discussion, but that was just what I wanted to say. It's very promising as a field, and thank you for your attention.
Thank you very much. We've heard a lot about the opportunities and applications of foundation models. So I would like to spend a few minutes to talk a little bit about the innovation and maybe the challenges that we face. So maybe one starting question for Kevin. So collaboration has been mentioned a lot in this discussion and also in the introduction. So in your opinion, how can international space agencies, institutions collaborate a bit more effectively to develop, share, and apply foundation models for Earth observation?
I think, can you guys hear me? Yeah. Okay. There are a variety of different areas where collaboration is necessary for these things to work properly. You can look at some of the foundational components, which are your data policies in a way that allow for sharing. I think for the folks in this room, that happens to be the case. But also, when we build foundation models, on-ground calibration understanding prior to launch is incredibly important for making the ultimate products much more robust and easier to use. So it's not only the policies, it's also the collaboration on building the instruments. And I'd even extend that out to commercial industry so that they can be integrated more easily into some of these global observing capabilities that we've got. I think to where we put our software, what methods we use to develop models, to help in understanding transparency of those models is something that you'll probably hear a lot about because there is still a lot of apprehension in the community for using these types of tools, especially in decision making. I mean, at some point they're going to realize that if you throw enough data into it that is good and the people that are working on it are excellent, that the results are probably going to be better than the ways they use these things typically. But whatever we can do to make that robust, I think is really important. So maybe I'll stop there and let the rest of the panel comment.
Thank you, Kevin. I really love this idea that collaboration goes across the value chain. It's not just on downstream, it's not just when we get the data, but then we need to start how are we going to work together on foundation models. And you did mention a bit about policies, so I'm looking at Federico maybe now. Looking ahead, what additional policies or frameworks do you think are needed to enhance data accessibility, ensure transparency, and maximize the operational impact of foundation models?
Yes, it's. I mean, I think it's a two-handed question, or two aspects. So the first one is about also the data availability. There are differences, for instance, in data availability and data access in the US and in Europe. So as example, the European Commission has now an artificial intelligence agenda that is implemented and is evolving. And with this frame, there is a new data union policy. Because in some way, the information and the data are the necessary fuel for any type of tool. This is one of the aspects. The second one that I see is what we mentioned before about trustability. Because at the end, what we want is that the foundation models, the output, they are also used by decision makers, by the policy themselves, for instance, by sectors that need reliable and fast response. So in some way, there is a need for policy in terms of what is usable, what is not usable, or also to define something that goes a little bit beyond the policy about the quality and the trustability. And also all of this is basically addressed in AI roadmap. One of the points, and I go back to the Kevin point, is the importance, I mean, not to have a unified system, but I mean, to have a recognized framework that is across, for instance, the agency, the organizations that are really at the edge in terms of artificial intelligence, but also towards the business. We have seen the example of Mistral AI, and also driven by, at the end, the guys that they needed to use these systems for the real life.
Thank you, Federico. Going more towards the science part, Gustavo, we will have a lot of examples throughout the week of the applications and the challenges that are faced in all of these applications. But could you give us some examples, some key scientific challenges to adapt foundation models to the complex, multimodal, multi-resolution nature of EO data?
Okay, so there are so many challenges on the pathway, right? So I think that my personal view, we are still in the inception and the infancy, I would say. Of course, I would identify kind of two types of different challenges. One, a part of technical challenges, of course, on how to combine and fuse different multimodalities. As I said before, we cannot see the Earth just as an isolated complex system, and as a complex system is a combination of subsystems that are interacting each other. And when I see in this workshop like a lot of multimodality, right? We are only looking at a very tiny niche of multimodality, only looking at, SAR and optical and LiDAR maybe eventually.
But there are so many different data sets there, right? And the important scientific questions not really boil down only to use Earth observation data, but most of the times they have to do with social and economical variables that we want to ingest and process and understand. So in a way, I think that the challenge will be that, no? How to compensate and how to fuse or combine different multimodal data that come from different perspectives of the whole system, and they are unevenly sampled and oversampled somehow. And in the end, you want to trying to shoot with a big gun to a very little or data scarce problem, right? Because in social and economical variables, they are very, very scarce limited. And I think that one of the challenges is this thing, right? So technical. How to incorporate and how to combine all these uneven sample data streams. Another more fundamental is what I just said, right? Like the fundamentals or the foundations of these latent representations that we try to learn and we want to deploy, right? And I don't know. I want to basically. Put a finger on the blister here, and to activate or reactivate the debate, right? So I think that in a way, this fallacy of democratization of foundation models is a bit annoying, right? So because we are kind of, okay, we are developing a bunch of models that everyone will use, but we are kind of converting ourselves as just, a button presser, right? So we just get whatever, whoever, now develop something, and then we will apply it to whatever other application. But we don't know really what is going on internally, right? In the internal representation of the model, and if it is right for the wrong reasons, maybe. So how can we actually manage to understand these models and how to make them more trustworthy and transparent? So I think that's, of course, a long-term challenge that we will have to face, but both are equally or even more relevant than the technical ones that we will probably manage in the upcoming years. Yes.
Could I?
Absolutely, Fang, yeah.
Yeah, I agree with you. There are, many opportunities and challenges. What I want to point out is, like, we're driving forward, foundation models with great benchmarks, for example, Pangea and others. We achieve good technical, benchmarks or metrics, but when you use in real-world applications for operational deployment, maybe it's not working. I think this is also one of the major challenges because we want to deliver Earth observation-based actionable intelligence, for people, decision makers to use. So as a science technical community, we also have to consider not just technical benchmarks and also operational perspectives.
Thank you. William, do you want to intervene? Because I saw you agreeing with many of the things that Gustav was saying. So what would be, from the industrial perspective, some of the, maybe the risks that we are facing in the development and adoption of foundation models?
So I think right now, what we need to improve, so we have four things to improve right now, and that can drive the field towards better deployment. The first one is compute. So for sure we are exploring new types of compute, also to deploy the models locally, and edge deployment I think is going to be a game changer. Second, in terms of explainability of the models, we have a lot to do to enable some sensitive applications. Right now it's not reasonable to do some stuff, and so that is going to be moving, I hope. Then multimodality is really something that will create a lot more of use cases, and we are really pushing on that front. Not only, so obviously voice is harder than expected, so we are also working on that. Vision is, the thing is that you are constrained to the data you find on the open web when you are an LLM provider, most of it. And so what you need is to find scarce data set to improve your models. And so that's why we need deeper collaboration with research institutions, public institutions, to access these data, to build these useful models, and to also make sure that the models are trained once, and then they can benefit to the whole ecosystem, so that you don't lack computing power when you are in a university or anywhere else. The computing power right now is, I would say, concentrated in the hands of a few private labs, and it's important that there is a deeper collaborations between the private labs and the institutions around the training of the model, so that you can train them once, and then you can customize them for specific applications. So I think that will change also. I hope there will be progresses. And the last one, I think, so explainability, computing, deeper collaboration. Yeah, I think that's most of it. Yeah.
So there is a lot on scalability here, so different phases of scalability. How do you scale the production, the deployment, the adoption, and so forth? So maybe going back to Kevin, what do you think are some key challenges and opportunities in scaling these models for real-time applications for climate, disaster response, planetary exploration?
So I think a big part of scalability is how robust you can make the models to begin with, how you can make that information available to people that will want to use those models for operational tasks as well. So there's a fair bit of training related to it. We try to make that as minimal as possible. We have been doing workshops where we train. I think there's some workshops at the end of this session on Wednesday where fine-tuning for specific kind of operational needs will be discussed. But to do that accurately and to do that with the volumes of information that we have, access to high-end computing, which allows for those inferencing types of infrastructures in cost-effective and efficient ways is challenging, frankly. Depending on the number of people in a room like this, if everybody was trying to do fine-tuning, I would imagine it would be $3,000 to $4,000 an hour, just in computational needs, maybe a bit more depending on what you're trying to do. So we've got to figure out how to optimize those pieces. Training comes along well, but it really comes along faster when you have easy-to-use apps which give you the necessary kind of guardrails that don't allow you to look for surface temperature or water extent in ways that are physically impossible. So there's got to be some research on that as well. But scalability is not cheap. Even developing one of these models, and you'll find out that you'll need more and more of them, are very expensive to do.
So if we do manage to get them to work operationally and put them in the hands of stakeholders and decision makers, and I'm looking maybe now a bit at Yifang, how can we ensure that stakeholders take the right actions, the right directions to ensure transparency, accountability, bias mitigation, while maintaining this technological competitiveness?
Yes, and thank you. I think that's a great question. We can give the data and tools to stakeholders, and I think the main thing is really to ensure they understand, we have transparent in terms of documentation, accuracy, and how much you can trust. They're always looking at, okay, this is generate data, how do we trust it? And also really to co-create success stories or examples to demonstrate the usefulness so that it's scale up the adaptation. I think this is really important to really be able to work together, and also to really show there's not so much bias in the data, because currently a lot of bias, trend in developed countries, you try to tell Global South, use this, do they trust it or not? And also we do have a possibility of digital divide, AI is developing very fast, but then we will have countries or regions that they're left behind. So we will have to address all these kind of issues so that decision-making is everyone involved. Thank you.
Thank you, Yifang. As we're a bit approaching the end, maybe having an outlook on what's coming or what you think is coming. So maybe looking back at Gustav, how do you see that foundation models will transform scientific research in the next years?
Oh my goodness. So you are asking me as if I were ChatGPT or something, right? Okay. Well, I think that there are like, I would say maybe 3 or 4 or even 5 lines of research and impact in the real science that we are all doing that are quite promising. And still there is a lot of work to do, but I already mentioned on the fact of combining different data streams, right? Not just images, but we are now witnessing like a lot of foundation models on weather, on climate as well, and ingesting all kind of data streams together with societal and economical variables that will allow us to answer, urgent questions about whatever else, like food insecurity or migrations or something more attached to the anthroposphere, not just the biosphere or other spheres. I think that's important. Of course, that is urgent to have access to the representations, right? To the embeddings, if you want, right? And these embeddings should be a kind of available to anyone and well documented, as mentioned before. And this, let's say, core of the foundation models or LLMs or whatever else allow us to do like intervention analysis, for example. We want to in our lab, we are working on causal tools to, scrutinize and investigate what is inside, right? So asking what if questions, what would have happened if this changes? Or conditioning the embeddings to something else, no? What if the weather changes? How would be the impact, no? Would that change much or not? No? That speaks not only to intervention analysis, that's fantastic to have it in the models world, right? But at the same time, I think it is also important to answer questions about feedbacks, right? That we are always struggling in the geosciences. No? I think that in a way, answering causal questions, I mean, the what if way is an interesting opportunity having this, no? These foundation models that in principle encapsulate all the knowledge that we have, right? Ideally. So that, of course, speaks to what digital twins are basically, trying to implement there. No? So having these little monsters that can answer whatever question in a latent representation space, that's opens a lot of opportunities, as I said, right? Fusing, combining, answering questions, creating counterfactuals, creating intervention analysis that answer questions in the societal and economical realm. And I think that this would allow us to rediscover other relationships out there, right? In the past, we observed nature, right? And we built our little parametric equations to describe it. Now we are observing nature in different ways. We are encapsulating all this knowledge in a hardly accessible representation, and we want to do science in that representation. That's a terrific challenge at the same time, right? So, yeah, I will stop it. I will leave it there. Otherwise, we won't have coffee today.
Federico, yes, please.
Yeah, just one additional point on what was said. I think it's also important to understand which are the priorities that are coming from science, because in some way we want also to go with AI where are the big science questions in some way. And also to learn, I mean, the Destination Earth, the different digital twins have been mentioned. So there is a very active research that is also here in terms of usage of AI for real problems. In that sense, also the Commission has launched, and here I make some advertisement, recently a consultation to pave an AI and science way. So this will be basically the text of the next calls. So where the European Commission science may go. So I can provide you the link, but it's easy. You can go to a browser and find a consultation, AI, science, European Commission, and you have the possibility to provide, I mean, any user, any scientist, any person can provide its own view and its own point on that. And this is on what, I mean, co-working has been mentioned and is built. Another element are the gigafactories. So the Commission has started the gigafactories. So is quite recent. This goes very fast, much faster than the usual research process that is a paper, takes time, revision, and so on. So it's a couple of years. And in some way, there will be research there. So there is a need to implement research there and to make research for the correct usage. So this is also what I see. I mean, I really consider that is a really two-way approach, and we try to do as best to keep these connections.
Thank you, Federico. Maybe one closing remark from William on the industrial perspective, some key things, key technological advancements to keep an eye on that would shift the developments?
I think it's not going to be a surprise, but reasoning is really something that is developing pretty well at Mistral. So reasoning, so basically post-training, not only reasoning, but also creating a feedback loop between the model and the user with various techniques that are well understood right now, GPO, SFT. I mean, we can do a lot of things now, but to embed those mechanisms, I mean, in the system is a bit tough. So right now, we just need to work on better systems to integrate those feedback, real-time human feedback. That is going to be a challenge in terms of when you build a product. If you are in this role and you build a product, it's very tough. Reasoning is advancing pretty well. Happy with that. And the pre-training, the compression of information has been well understood. So now it's not really key. But what is key is to integrate new data sets, exotic data sets, to make those models relevant for a lot of other industries like space and defense, for example. So that's some focus right now. Thank you.
Excellent. Thank you. I'd like to thank all our panelists for their presence today. I think you can reach them also over the coffee break for further questions. So thank you again, and maybe a big applause for everyone.
Yeah, we are a bit late, as expected. So yeah, I propose that we start the session at 10 to 12. So we have 20 minutes for the coffee break. It will be served in the tent there. Then there will be two parallel tracks. The first one here in the Bighall and the other one in the Bighall. So please be on time at 10 to 12, please. Thanks.
I'm Thomas Brunschwiller from IBM Research in Zurich, and it's a pleasure to host this session and introduce the first speakers. But first, just think back. Until 2022, we only built bespoke models. Isn't that amazing? So, and only in 2023, the first EO foundation models surfaced. So, and now we're really riding the wave, diving into multimodal models and more to come. So I'm really looking forward to hear from the speakers about the latest advances, which hopefully stimulate discussions afterwards. So with this, I'd like to introduce you George Leifman from Google Research, and he will talk about remote sensing representation through mixed modality masked autoencoding. So George, the stage is yours.
Thank you very much for the introduction. So I'm using this. So I'm George from the Google Research, and before I start with my technical presentation, let me just mention the geospatial reasoning program, which was introduced last month during the Google Cloud Next. And you can just type geospatial reasoning in Google search, and you will get the blog with the announcement and with all the information about the program itself. It also has an interest form where you can leave your details and get any updates we have about this program. Just in a couple of words, this program is the combination of the collaboration between different teams in Google, which are building foundation models in traffic models, weather models, models based on the street view data, trends, and of course remote sensing imagery. And all these models are combined together using generative AI, Gemini, and using this combination, it can be used for different examples in the real world, like urban floods, pollen estimation, hunger forecast, and many more. I am from the remote sensing imagery team, and we are developing different foundation models for the satellite and aerial imaging. So today I will talk about mixed modality mask autoencoding, and tomorrow in session 7, I think, Yotam for our team will talk about vision language models, so you're also invited to hear. Okay. So this is the introduction of foundation model pre-training, so it's kind of strange to talk about it here, but I asked Gemini to write this slide, and it gave pretty good information about the foundation model pre-training. So the goal of the foundation model pre-training is to learn general purpose representation. Usually it's done by employing large-scale and labeled dataset with some self-supervised learning that learns the inherent structure in the data itself, and the output is a pre-trained model with rich and transferable knowledge. And this model can be used in various downstream tasks, and in the downstream task, usually the labeled data is limited, and this is why we need the foundation models. Usually it's used in two different scenarios. The first scenario is the frozen bug one, where we extract the features without updating the foundation model weights, and then train only the weights of the head. And or the fine-tuning scenario, where we update the foundation model weights and for the specific task, of course, along with the head itself. The work I'm going to talk about is built upon a well-known techniques, which is called mask autoencoder, which was introduced something like almost five years ago. And the idea is pretty simple. You take the image, pass it through some kind of random masking. You take the unmasked patches and pass it through some kind of encoder. Usually it's a vision transformer. And then you have a representation, decode this representation in order to get reconstruction of the image itself from the only unmasked patches. And as a result, the encoder encodes the inherent information about the image itself. So in addition to being widely used in the computer vision, it's also was used a lot during the past 2-3 years, and also in for satellite imaging. So SatMai is only one example, I think the first one, but during the last couple of years it was very useful, and many use this technique for the foundation model pre-training. But in our case, I will talk about the case where, in addition to the image itself, we have some kind of additional source. I will give an example using Sentinel-1 and Sentinel-2 images. So in addition to the Sentinel-2 images, which is going through the standard mask autoencoder, what if we have a Sentinel-1 image from the same location? So can we really use it for foundation model itself? And I will not go to the details, but Sentinel-1 and Sentinel-2 are different sensors. The first one is, Sentinel-2 is multispectral, the Sentinel-1 is SAR, and the data is complementary. For example, Sentinel-1 can see through the clouds, and Sentinel-2 not. And for example, for the icy or desert areas, if you want to see the relief of the images, Sentinel-1 is also better. So let's start with the data itself. So we collected the data set, pretty large data set of images. We took something like 100 million images from Sentinel-2, from 4 seasons from 2022 to 23. And for each Sentinel-2 images, we found an image from the same location from the Sentinel-1, which is close in time to the same timestamp of Sentinel-2. And as a result, we got something like 40 million image pairs for Sentinel-2 and Sentinel-1. And now we investigated 2 different techniques to mix the modalities. The first approach we called auxiliary Maya, AUX Maya. And the idea here is also pretty simple. And what we are doing, we are taking the path, or standard path of mask autoencoder, Sentinel-2 image, going to the masking, the unmasked pages going to the encoder. Then we have the decoder, which is trying to decode the image and reconstruct the original image only from the unmasked page. So everything here is known and straightforward from Sentinel-2. But in addition, we take the same Sentinel-2 image. We don't use any masking, put it into the shared encoder, and then we introduce an additional auxiliary decoder, which now tries to reconstruct the Sentinel-1 image. Sentinel-1 image from the same location, of course, so same pair. And both these passes, as you see here, using the same shared encoder. Okay, and then the idea is what we showed later, that the shared encoder learns more information about the data of Sentinel-2 by adding this additional reconstruction of Sentinel-1 in the loss. Yeah, you can easily extend this approach to additional sources. So, for example, if we have, in addition to source a pair of Sentinel-2 and two Sentinel-1 images, we have additional sources which is paired with Sentinel-2 image. We can just add an additional decoder and to reconstruct the additional source, and you can do it for even more additional sources. And in order not to be limited only to the specific pairs of Sentinel-1 and Sentinel-2 images, we used alternating gradient descent approach, which was introduced a couple of years ago by Akbar et al. And the idea here is to train the model by alternating batches. So in each step of batch, we are optimizing only for the specific task. For example, the first batch can optimize for only for Sentinel-2 images. So we don't even need to have pairs of images. So as I said before, we started with 100 million Sentinel-2 images, and eventually we had only 40 million pairs of Sentinel-1 and Sentinel-2 image pairs. So for example, in this approach, we can use as one of the tasks only a Sentinel-2 approach reconstruction. And the second task will be the reconstruction of Sentinel-1 from the Sentinel-2 for the pairs. Okay, so by this we can easily enlarge the training mechanism. Okay, so the second approach we investigated called Mix Maya, and here we mix two different inputs. So unlike the first approach, the input was always Sentinel-2, and only the reconstruction loss was done on Sentinel-1 and Sentinel-2 together. Here, the input is both images from the pair. Both of the images pass through some kind of entry layer. We have some kind of encoding. We mixed together these encodings, put it into the encoder, learn some kind of representation. Then we have two different decoders. The first one is the standard decoder for the Sentinel-2 image, and the second one is the auxiliary decoder for the Sentinel-1 image. Eventually, in the downstream task, both for the first approach and the second approach, we are using only the Sentinel-2 image input and the encoder itself. Okay? And all the Sentinel-1 are used only for the pre-training itself. Another way to look in this second approach is, if you look here, you can see the mixing of two images. So the upper image from Sentinel-2 and the lower image is from Sentinel-1. We can just do some kind of complementary masking between them. So as you can see, we can have the complementary masking, put them together, mix them in some kind of encoding, and then from this encoding, we are trying to reconstruct both modalities. Okay, in order to evaluate our techniques, both approaches, we use three different downstream data sets. The first data set is Sentinel-1 /11, which is publicly available segmentation dataset for Sentinel-2 images, which talking about 11 flooding events from 6 different continents. The second dataset is a classification dataset called Bighall. Bighall is also publicly available one from Sentinel-2. And finally, we are using internal Google dataset for super resolution segmentation, which is also used Sentinel-2 imaging, but here the input data is 256 by 256 images, but the output ground truth is 1K by 1K. And we have 8 different results classes for this one. Let's go to the results. So the frozen encoder, the first row is the baseline, is a standard Sentinel-2 mascot encoder, and here we have 2 approaches. So as you can see, the results in most of the cases are better for our approaches. The same you can see also for the fine-tune scenario, but here all the results are better for the approaches we investigated. And to conclude, before I conclude, I just wanted to show the example of the urban super resolution data set. So here you can see on the left the input image of 10 by 10 meter to pixel of Sentinel-2, and then the output of the mascot encoder, the baseline mascot encoder in the middle, and the detection and segmentation of the very small buildings in the resolution by 2.5 meter by 2.5 meter by pixel. And finally, on the right, you see the result of our auxiliary mask. And as you can see here, some of the regions that were not detected, segmented in the baseline, here it was segmented. Finally, to conclude, I presented 2 different supervised learning approaches. Techniques to integrate data from multiple modalities. One is auxiliary Maya, and second one is mixed Maya. And we evaluated it in 3 different remote sensing data sets. And specifically, I gave the example of combining Sentinel-2 and Sentinel-1, but this technique can be used for combination of any imagery from different pairs of images. Thank you very much.
Thank you, George. We have time for 1 or 2 questions.
Hello. Just a quick question. What is the temporal distance between different modalities that you tolerate?
I think it was something like 5 days, but I'm not sure. It's in the paper. So up to 5 days.
Yeah, thank you for the presentation. If you come back to the results slide, so what was that? Is it accuracy or?
It's for the segmentation, it's MAP, and for the classification, it's accuracy. So
okay.
Inaccuracy.
Yeah, thank you.
Yeah. All right, thank you, George. Then,
one question.
Oh, yeah. Sorry, yeah.
Thank you for the presentation. I have a question for the mix MAE. Are there interactions between the different modalities in your encoder when you're doing this approach? Or do the tokens are independent, processed independently in the encoder?
Are you talking about if I have any in positional or modality encoding in the...
Do you have cross-attention between the 2 modalities?
Yeah.
Yeah, okay.
Thank you. All right. I think we still have time. George, you're probably around. Let's talk to George later. Thanks a lot, George, again for the presentation. Now it's a pleasure to have Steve Jenks here from DIGAS Africa, and he will talk about SAT-SWIN MAE, a spatiotemporal autoencoder for multi-scale satellite imagery. The stage is yours, Steve.
All right. Okay. Hello, everyone. So today I'm going to talk about the work we are doing at DIGAS. At DIGAS, we are a bit of a special company in the sense that we have 2 very separate business lines. So on the one hand, we have our farming operations in Africa, and on the other hand, we have our foundational model work. So today I'm going to try to explain to you a bit of the history of the company so you get to understand how this came together. Right. The farming business is really simple. Farmers need to have fertilizer at the beginning of the year, but they only have cash at the end of the year. So what we do is that we bridge this gap by essentially we provide fertilizer at the beginning of the season, and then towards the end we collect a share of the harvest. Right. So we are a very rapidly growing company. We started with only 400 people in 2019, and in just a few years we are actually going all the way to 25,000. And now I'm going to show some of the photos of our operations in the ground. The people that you see here, they are all of our employees. They are agents from Degas. They come from a lot of these rural communities. And usually we organize these training camps so that they can get to know each other, get to understand our processes, and get to better understand how to use our technology. We also have a lot of warehouses because, at the end of the season, we collect so much corn that we have to store this somewhere. And so we are renting a lot of warehouses all around Ghana, which is actually quite a logistic challenge. Essentially, we are running out of warehouses we can rent. We are thinking about building new ones, and it is quite a major challenge. Now, these are some of the farmers that we work with. They are extremely, they are people from very rural areas which live in extreme poverty conditions, so it's quite challenging for us sometimes to even interact with them because they have 48 different languages in Ghana. So even if you need to collect people or train agents who come from these communities so that they can bridge these communication gaps. Now, you can imagine, right, the challenge. So we have 100 agents, 48 different languages. You cannot really communicate all of that through the phone. It's very challenging. So we built this app that is allowing us to collect all kinds of ground information on all of the farms. And now you can start to see where this is coming with satellite imagery, right? So the way the app works is very simple. We have 5 stages. First, we have the registration. So this is when we bring a new farmer. We just register them, get the name, sign a contract. We give them a bag of fertilizer, take a photo because sometimes they say they didn't get the fertilizer. And then we agree on a contract where they're going to pay us back with some number of bags of corn. Then we have the farm mapping. This is when a farmer goes with an agent. They walk around the farm, and they're collecting the boundaries of the farm, literally with a phone, and just collecting the GPS coordinates. Then we have field assessments. These are regular monitoring events where our agents go to the farmer and they take photos, talk with the farmer, make a report, and send all of this data back to our central database. Right. So this is how we collect all of the ground data. And this was the first layer into our technology stack. So how do we collect all of this data from the ground? And it was a great improvement over, let's say, phone communications. However, if you really want to have real-time monitoring that is reliable and is at scale, you need to move into satellite. And that's kind of when we started moving into our satellite network. For satellite, think about the challenge. We have 30,000 acres of land. We have to collect all of this data real-time. So we thought, okay, we need to create a satellite system. Now, how do you do this? Even though we had some data, it is still pretty hard unless you have a foundation model. And when we started, there were no available foundation models. So we thought, okay, we're going to have to create our own. And we started with a very simple approach, just the mascot encoder. We have a pre-training data set that is global. It's the SSL4EO. It has multiple seasons. And this is the architecture that we use. So it's a swing transformer where you have some video swing blocks. The way the swing backbone works, for those who are not familiar, is that it takes a high-resolution image. And then as it goes down each one of the encoder stacks, it lowers the resolution and increases the depth on the embedding, which means that as you go down the stack, you are going from very high-frequency, high-resolution imagery into low-resolution, high semantics down towards the bottom of the model. Then the way this works is a standard MAE, so you reconstruct the mask input, and you create that's how you pre-train your weights. Now, to fine-tune this model, you cannot just take it as it is. You have to add some skip connections between matching resolutions. That means that on the first layer, you have to connect the skip connection between the first encoder with the last decoder from the decoder side. And the same applies to the second layer and so on. So that's how you have to do the skip connections in a swing transformer. And these are some of the results that we got. This was the original test. We were comparing against PRIT VV1 in the, I believe this is the original, well, you have the Zone 1 floods, wildfire scars. I cannot remember if it was the Phileo bench or the geobench. And so, but you can see that here against pre-VV1, we were doing better in all of the tasks. And you can read the paper, it's there at the bottom left. We tested in 3 other benchmarks, and we were also outperforming in all of those. Especially, if you can look at these tasks here, they're all segmentation tasks. And if you look at and what I think is that because our model has the SWIN backbone, is doing much better in segmentation than a vanilla transformer, simply because it's able to capture both the high-frequency components and also the deeper semantics. Now, if you look at the same experiment without skip connections, it's the exact same model, but you remove those skip connections, then the performance edge drops. It's actually performing worse than the baselines, so it is critical that you have the skip connections between the encoder and the decoder layers. Now, that paper was written about a year ago. Now, more recently for this conference, I was thinking, okay, how is the model performing relative to more modern models nowadays? So I took the freedom to take this figure from the pre-VV2 paper, and just plotting here the results of our model in GeoBench. And you can see on the bottom, on the top right, all of the results are there, but if going more specifically into the, let's say, classification accuracy or segmentation, you can see that it's performing similar to SATLAS and on a similar level of performance as pre-VV2 300 million, even though it's the 100 million version of our model. And so in all of the benchmarks that we are able to test, we observed that both SATLAS and our model are outperforming the pre-VV version, even though they have very similar training strategies. And we think this is because the SWIN blocks have a better inductive bias than the vanilla transformer will be able to offer. Now, we are going to be releasing our model very soon. This is a Sentinel-2 based model. You can use it and test it in any other task that you are interested in. Now, we're also be able to combine different modalities, and to achieve this, we are using the work that I did in my previous job when I was at Google. So what we have is that for each modality, we just have a specific encoder, and then we have a parameter that is able to control how the cross modalities are able to interact. What we find is that in general, the optimal matching, rather the optimal point of fusion, is towards the 8th layer. Let's say you have 12 encoder layers, so around the 8th is where you find the maximum performance. And this is just one example from Eurosat multimodal, where I show that the Sentinel-2 and Sentinel-1 are able to combine very nicely. Now, this is something that we offer to our clients. Hopefully, we'll write a paper soon. I will share with you all of the results. Okay, so now I'm going to take one step back and look at the high-level overview of the geospatial industry to try to explain what position do we occupy in this high-level, in the different layers. So on the first layer, we have the satellite providers, of course, like ESA and NASA. Then we have foundational model providers like NASA, IBM, Degas, SATLAS. There are many others that are offering foundation models. And then you have the application layer. This is when you take the foundation model and actually deliver value to the different customers and the people who are interested in them. At Degas, we are operating at both these layers. So we are building foundation models, and we are also building applications. So the talk today, I already showed the work we did in Sentinel-2. I'm also going to share some other work we did in other foundation models for other satellites, and then I'm going to go into the application side. So on the foundation layer, this is the work we did with Japan. In Japan, they have the ALOS constellation, which is a satellite system very similar to SAR, where they are able to collect data anytime they want, whatever they want, because they can task it, right? They have full control over the satellites. So they were very interested in, can we create a foundational model for this constellation so that whenever there is a flooding in Japan, we are able to actually analyze the data real time. And you can see on the top, there is an image before the flooding disaster and an image after the flooding disaster. When I look at that, I cannot tell any difference at all, but the model, after it's been trained with thousands of images, is able to figure out exactly where the flooding happens. So this is an example of foundation model we created for the ALOS constellation. And usually our philosophy is that we build foundation models when needed, not because it's something we just do. And in this case, there was nothing available, so we built one. And the same applies to Sentinel-2. When we started, there was nothing out there, so we just built one that will be able to allow us to deliver to our clients. So now I'm going to talk about that, our clients, and how we are using these foundational models for them. So this is an example of a project we did in Thailand. It's a cassava project. Cassava is a major source of food in Thailand. It's one of their major crops. And they suffer from a disease called cassava mosaic disease that is very nasty. As you can see in the images, You can take a very healthy leaf, and it just completely kills the cassava plantation very quickly. So we ran a pilot there, and we got 90% accuracy from the first attempt, which was a huge success, and now we are extending into other regions of Thailand to be able to hopefully identify this disease before it's too late, and then we can just cut the ones that have gone bad. Now, we also have this other project in Thailand, which is about soil. So those of you who are interested in gardening, you know that there are two key variables. One is the pH. So certain plants grow in acidic soils, some plants grow in basic soils. And so we started by building a pH map of Thailand. The same thing about carbon. Usually, the more carbon in the soil, the better the plants will do. So we collected some data in collaboration with Sojitz. Sojitz is a great partner of us. They are also our investors, and they have a lot of farming investments around the world. So they helped us to collect all of this data. So with some ground truth data and our Sentinel-2 Foundation model, we fine-tuned into this, and we were able to get a map of Thailand, both for the pH and for the carbon. Okay, and now I'm going to very quickly go through insurance because I'm running out of time. So we're also building now, this is the latest project we are building, is an insurance project to protect our own farmers. On the top right, on the top left, you can see some of our farmers being affected by floods. And the challenge is there is not a single field segmentation model that works in Africa because the farms there are just way too tiny. So we are creating our own pipeline to collect data. We already collected 20,000 field boundaries and 20,000 yield data points. And we are actively looking for partners who will help us build this field segmentation model so we can deliver insurance. None of this will have been possible without our amazing team. We started, just Johi and I, about a year ago, and we are quickly growing into a team of 8 now. And of course, we're always looking to any new members that might be interested in joining us. And with that, I leave you today. Thank you so much. If there are any questions, please let me know. Thank you.
Thank you, Steve. Any question? It's back there.
Hi, nice presentation. Thank you very much.
Thanks.
I'm curious to know which version of Prithvi you used for the segmentation, because I've noticed some differences between the first version and the second one, and also the model size.
Yeah, so I'm just sharing the results from the Prithvi paper directly. Hopefully, yeah. This is Prithvi V2, the one that is being shown there. And you can see the weights on the bottom. And you can see that I'm comparing with the 100 million weights and our version of the 100 million Degas model. Yeah. Thanks.
Any other question?
Yes. Thank you for the nice presentation. You mentioned also yield estimation in Ghana.
Mm-hmm.
Can you tell us which data did you use, and do you plan to enhance, that is, to expand the yield estimation in other countries?
Yeah, so we are using our own collected data. To grow it into other countries, we have some partnerships in different countries in Africa, but it is very difficult to get yield data in general. So we are really dependent on that. We have a few partners in Ethiopia, we have some partnership in Kenya, and hopefully we will also have something in Southeast Asia. But yeah, it is usually quite a challenge.
Okay, thank you.
Hi.
Yeah.
For the cassava project, what data you use for input? Was it still Sentinel-2?
The satellite data was Sentinel-2, yes. And the ground truths were collected by Sojitz, actually. The same partner that we did this project with, they were the ones in charge of collecting the data.
That's impressive that you can pick up a signal on the shades of green, let's say, around the disease.
It's a combination of the changing of the greenness, but also you can see that even the NDVI will drop because now the biomass is shrinking very quickly. Yeah. Mm-hmm.
So maybe one question from my side. I was curious, how much fine-tuning data do you have available typically, especially like if it's about small farm holders in Africa or so?
Right. For our own farmers, we have 20,000 data points for this year. That's all we have. Next year, we will have another 20,000, hopefully. Yeah.
Yeah. Okay. And then you fine-tune one model for specific regions, or
Yeah, we actually cover all of the northwest of the country and also part of the east. So those are the main regions that we are collecting data from.
Yeah. Thanks.
Thank you.
Okay. Thanks, Steven.
Thank you.
So our next speaker is Ricardo Musto from Leonardo Labs. Welcome. He will talk about GeoDyno, a vision foundation model for Earth observation leveraging Dyno architecture and Sentinel-2 multispectral data.
Hello, good morning. So this is a joint collaboration that we have been doing with the ESA Lab. So I'm Ricardo Mus, I'm from Leonardo, in particular with the Leonardo Labs, so the research labs of Leonardo. And so we are here, so everybody knows what a foundation model is. Nevertheless, I wanted to show you this slide because I'm really proud, to be honest with you. But I'm going to skip on it because we know what a foundation model is, what are the rationales behind those huge models, and so I'm gonna focus a tiny bit on these slides, nevertheless, because this is what we usually want to have when we work with foundation models, right? So we pre-train this model on a huge amount of data, but at one point you have to evaluate your model, right, before usually using it for different downstream tasks, etc. Because if you don't evaluate it correctly, you're never gonna know if your foundation model is working or not. And so basically, with our colleagues from Philab, we had an idea. So everybody was already working on masked autoencoders. They work, they're amazing and everything. But probably 99.9% of all of the foundation models out there are masked autoencoders. And so we were like, what if we try to use something different? What if we try to take a different path? And so that's when we decided to use Dyno, distillation with no labels from Meta, to see if it's actually like a good backbone, a sort of good baseline for foundation models as well. Obviously, we called it GeoDyno because we didn't have much fantasy back at the time. And so you can find in the very bottom left, sort of general overview of our model. So we have the usual Dyno architecture, and then we are adding some kinds of auxiliary tasks that we want the model to actually perform. So you can see because basically we have been training this this model, and I'm going to talk about it a bit later on MajorTom, which is the huge data set released by ESA last year. And basically this MajorTom comes with a lot of data and as well a lot of labels, such as obviously coordinates, maybe clouds, permanent water bodies, etc. So we use all of this auxiliary information to try to drive the foundation model towards better representation learning, etc. Okay, so just same image, a bit bigger, so maybe even the guys in the back can see it. But basically, what is going on with those clouds heads is we're not actually performing any kind of segmentation task. We are more like trying to perform a sort of regression task. So instead of saying the network, hey, this is an image from Sentinel, try to, I don't know, see where are all of the permanent water bodies, we're just trying to ask the network, try to count how many pixels out there relative to the water class, maybe relative to the clouds class, maybe relative to the buildings and to the land cover classes as well. And we also do an embedding of the coordinates. Other models have done it as well, especially like Prithvi 2.0. They've been embedding coordinates as well, and we have seen that embedding coordinates usually yields to better results because the model is more or less trying to play in GeoGuessr. I don't know if you're familiar with the game, but basically you are shown with an image, and you have to guess where the picture was taken from. So you have to guess the coordinates, and this is what we also try to do with the coordinates ads in our model. And so, more interesting things, again, we have been training our model on MajorTom, and to the best of our knowledge, this model and other foundation models we have been developing with ESA as well are the only foundation models that have been trained on the entire MajorTom dataset. At the same time, we have also been using FastTom, which is a subset of MajorTom that we have created internally. So it's a sort of random, it's not random, it's a smart sampling of MajorTom. and it serves as a proxy. So if our foundation model works fine on FastTom, which is way less bigger than MajorTom. FastTom is 2 terabytes of data, while MajorTom is 23 terabytes of data if we are referring to Sentinel-2 Level 2A. So I was saying that if the model works fine on FastTom, we can expect it to work even better on MajorTom. So it's a proxy. Instead of like fully committing to the entire dataset, like immediately, we try to do some tests, we run some benchmarks, and then we fully commit to the entire dataset. As you can see, we've been working for the time being only on Sentinel-2 Level 2A, just again to get some results in and see if we can scale it up, everything that we have done. And we have trained our model on our HPC infrastructure, the DaVinci 1, which is in Genoa. Obviously, once you train your model, you have to evaluate it. So we have yet again used the Philaio bench from our colleagues from the ESA Lab. We have tested our model on 3 different downstream tasks, namely the land cover classification, building, and road density regression. We have been using a sort of better kind of unit, which is the UPernet. We have been implementing it, and we're going to release the new code for the Philaio bench, like the beta Philaio bench pretty soon. And regarding GeoDyno, we have the biggest VAT backbones still in training on our DaVinci, so on our HPC. So we're just going to show you the results for the VAT tiny and small, even because even if they're small, we are getting very interesting results, which may hint that maybe using Dyno or any other kind of foundation backbones can be powerful as masked out encoders. And so those are the model we have been testing. We have the GeoDyno, and we also performed an ablation study. So we have tested the base Dyno architecture without the auxiliary tasks that we've added, both for the VAT tiny and small backbones. Again, we have only trained them on FastTom because they're still undergoing training on MajorTom. We have also been testing the Philaio models that are the other foundation models we have trained with our colleagues from ESA. There is going to be a presentation this afternoon, so you can go and look at it if you're interested in how we have also worked on those foundation models as well. And we also tested Prithvi. The colleagues from ESA tested Prithvi, the 2.0 version, only on the land cover task. So these are some of the very preliminary results we have obtained. Obviously, the bigger models are getting the best results. But there is a very interesting thing, is that our models, namely the GeoDyno tiny and small, they are very small models. We are talking about 7 million parameters for the GeoDyno tiny and maybe 20 million parameters for the GeoDyno small. And nevertheless, we can still keep up with those bigger models. And again, this is something interesting, right? So it means that actually using a sort of Dyno architecture can be powerful enough. So even if we try to go on JEPA, which is another kind of SSL methods derived by Meta, by Ian LeCun, maybe you are familiar with it, we can expect maybe even better results as well. And as you can see also from the ablation study we have performed, adding those auxiliary tasks, which are very small because there is not much overhead introduced. The number of parameters is quite small. And the GeoDyno version usually outperforms the base Dyno. So meaning that the extra information we are giving to the foundation model is actually doing something good for the foundation model itself. And then we also have, obviously, we are using accuracy metrics for the accuracy, for the land cover classification. And then we go to building density estimation, so we are using an MSC. Again, the GeoDyno versions usually outperforms the base Dyno, and again, the bigger models obviously get more powerful and results, and this is the same for the road density estimation. And so to conclude, I know it was quite quick, but too many things to say, and it's quite hard to packet everything into a single presentation. What are we going to do in the future months with our colleagues from ESA? Definitely, we're going to evaluate GeoDyno with the bigger backbones. We're actually writing a paper that will be released pretty soon. we also going to finish the trainings of those model on Majorstrom as well. And we also want to scale it up to Dino V2 and even maybe other architectures as well. And we also have a kind of question that we've been thinking about for quite some time is, can we design a better SSL task? Because there are a lot of papers out there showing that usually geospatial foundation model cannot really keep up with like usual models trained on a very specific data set. So they perform good, but they don't yield those among us performance that we expect them to have. And so I think, and we all think, that maybe is because we are not designing geospatial foundation models as they should be designed. And so maybe we should just try to research better architectures and ways of dealing with remote sensing data. And we are also already experimenting with obviously other modalities as well, so that we can actually have a proper multimodal foundation model. We are also likely going to add SAR, hyperspectral data. We have a lot of missions, for instance, Prisma, which is an Italian hyperspectral sensor, and we are also likely going to also add some kind of text information as well. Thank you very much for the attention, and if you have any questions.
Thank you, Ricardo. Questions? There's one. Yeah.
Hi, thanks a lot. I just wanted to ask, when do you foresee to finish training on Sentinel-1, and whether you make the models publicly available the way it's in the architecture?
Okay, so Sentinel-1, we are still finishing like the architectures, etc. So we still have to launch the trainings, but we have a huge number of GPUs, so I don't think like the training is going to be like a huge problem. Maybe a couple of weeks, maybe a couple of months, but it depends on how much time we need to finish up everything. About the models, so again, this is a collaboration between ESA and Leonardo. The models from ESA, they're likely going to be open public. Regarding the model for Leonardo, we're still thinking about it. Maybe the idea is to make public like the smaller models so that the research can play with them and see what's going wrong, and probably the bigger models are going to kept like private for the company, because also we're likely going to use those models internally for our tasks and also for our clients as well.
There may be.
Hi, thanks for the talk. So here you basically train for augmentation invariance. So I wonder what kind of data augmentations you define for the Sentinel-2 data.
So we have been testing like for the moment with the basics basically. So we have been using the same augmentations from the original Dino paper. Now we have to be careful though. Maybe for optical images is not like a huge problem. But if you go and you start training your foundation model on SAR data, you have to be really careful with the kind of augmentations you're using, because if you perform like an horizontal and a vertical rotation simultaneously, you're basically destroying the SAR signal contained in the data itself. So you have to be really careful. But we thought that probably for Sentinel-2, so optical images, even if you perform like different kinds of augmentation, it's not going to be like a huge risk. Obviously, we didn't use any kind of color jitter or maybe any kind of brightness correction, etc. So we've been sticking to the basics. This is also one point that we have been discussing a lot, and we are still trying to see if what kind of augmentations can we use without destroying the signal contained in the data. And that's also why we're also trying to see if we can design a better SSL task, maybe even trying to go into other methods as well. I was saying JEPA before. Maybe also that can be something can be interesting to see like the results.
All right, if there's no, is there a further question? Okay, good, yeah.
I wanted to ask if you've just been using vision transformer backbones, or have you tried like some convolution-based backbones as well?
No,
no. With Dino, you can try both ResNet as well, right?
No. So at the moment, we have been using like the very vanilla VAT, let me say. Right. Again, we are still trying to scale it up. Those were like some preliminary results we wanted to get in before like fully committing to a specific architecture, etc. We are likely going to use bigger models, maybe in some mixture of experts, etc. Because the idea is to scale it up. Right. Yeah. But before fully committing, we wanted to see if the method was working. Yep. So for the time being, vanilla backbones. Vanilla VAT backbones.
Yeah. Thank you.
Great. Thank you, Ricardo, for the explanations. And I'm sure you're still around for further questions.
Yeah, absolutely.
OK, great. Thanks.
Okay, good afternoon from my side. I'm Hamad Al Mohammed from Clark University. I'm going to introduce our next group of speakers here. So next presentation is by Guillaume Astruc, if I pronounced their name correctly. Yes. Title of the talk, AnySat, a multi-resolution, multimodal, and multi-scale EO model. Can we have the slides?
by mail.
Maybe we should, yeah, maybe in the interest of time, we are going to move to the next talk. Yes. OK. So yeah, thank you. So let's move to the next talk by Ridwan Kuzu, Fast EO, a multimodal foundation model for scalable Earth observation and Earth sciences. So if you can bring up Ridwan's presentation, thank you.
Hello, everyone. My name is Ridwan from German Aerospace Center, Remote Sensing Institute. And in this Fast EO project, we are collaborating with ESA, German Aerospace Center, IBM Zurich, Jülich Supercomputing Center, and KP Labs. This is actually the granted project from ESA last year, and we completed the first year of this project, and we will share now the outcome of the second milestone of this project. And as a first start, we focused on two aspects, developing a core foundation model based on different modalities, multimodality, multisensority, multi-satellite, and multi-sequence approach. And after this, we plan to test these different models on different use cases. As you see on the right side, we have 6 use cases defined for this project, which are weather climate disaster analysis from IBM side, detection of metal leaks, on KP Lab side, observation of change in forest above ground biomass on DLR side, estimation of soil properties, detection of semantic land cover changes, and lastly, monitoring the expansion of mining fields into farmlands. As an outcome of this project, as you heard actually a few weeks ago in the Earth Day, we announced the TerraMind, a new any-to-any geofoundation model. And a few days after the announcement, we also released the source code and the model weights. And TerraMind is the first any-to-any generative and large-scale multimodal foundation model trained on around 5 billion tokens. As modalities, we cover different Sentinel-2 modalities and Sentinel-1 ground and RTC product. In addition to that, we have digital elevation model, vegetation index, land use, land cover maps, and captioning that images plus the geospatial coordinate information. And for training, we have pixel level, token level, and second level input. We deal with different kind of inputs into our modality-wise tokenization system. And using these different embeddings, we have a correlation learning to align different modalities with cross-entropy loss and sample target tokens. As downstream application, we have multimodal generation which I show later. It generates this any-to-any approach, and also for fine-tuning, as I defined in the former slide, we have 6 use cases to test fine-tuning performance of this Terramind model. Plus, another big novelty of Terramind model is thinking in modalities, meaning that when we are fine-tuning, we don't need to rely on only the inputs we have. We can also feed in parallel the generated synthetic data coming from Terramind in addition to our original data, which boosts the performance a lot. As you see here, we have some example from the generative model we developed from Sentinel-1, Sentinel-2, and digital elevation model in the last row, and the output of each generated image. They are quite decent and very good aligned with the original input data, as you see, with the ground truth. We also test our Terramind model with Pangea benchmark with different use cases and with diverse set of modalities on downstream applications, but we rely on the frozen encoder. As you see on the left side, the model we provided, the base Terramind model, outperform all other evaluated geospatial foundation models. And also this high performance is a result of this thinking in modalities approach. In addition to any-to-any approach, we also focused on vision language models in FASTIO project. For that, we rely on basically CLIP architecture. And we focused on zero-shot classification and text-to-image retrieval capability of Terramind model. In MS-CLIP, as you know, the original MS-CLIP is trained on around 400 million image text pairs. It is very well for many applications, but for specific domains, such as Earth observation domain, it is not performing quite well. So that is why there is a need for continuous pre-training with additional channels coming from multispectral and SAR data. That is why we did such improvement on original CLIP as a part of this project, and we tested with different classification and retrieval benchmark, as you see on Eurosat, Meter, ML, Bighall net. And as you see on the outer blue lines, it outperforms all the base architecture we tested here. And the overall improvement approximately in classification is around 7%, and the retrieval is around 5% improvement. And also the main catalyst of this improvement is the multimodality, if we compare our base model with RGB CLIP. Regarding the downstream applications, we have 6 different downstream applications. The first one is related to climate impact analysis. Under this use cases, we are now developing a very large-scale multimodal and multi-temporal data set. It will be released very soon. In addition to that, we have detection of methane leaks. We rely on California NG data set to test this fine-tuning this Terramind model to test it on this data. And the performance is around 86 sensitivity and 82 specificity, surpassing the other benchmark foundation models and the classical machine learning methods we tested in this project. Another downstream application related to biomass change monitoring. In this use case, we are investigating how terrain topography affect the detection of forest biomass, because we know if the terrain is very mountainous or harsh, it is quite difficult to have a proper estimation, and we try to overcome these difficulties with a Terramind model. One another regression downstream application we focus on estimation of soil properties. And for this use case, we rely on Hyperview challenge dataset. And with TerraMind, we secure the 4th place in the public leaderboard. It is already a closed challenge, but still we submit and see the performance. Last 2 use cases are detection of semantic land cover change and the monitoring expansion of mining fields into farmlands. Both of them are related to segmentation and instance segmentation. And in the first one, we create around 300,000 patches and created a data set called Sanfor map. And we compare different base architecture based on random forest, pixel-based transformers, vision transformers, and video vision transformers. And at this moment, we are also trying to compare the TerraMind model with these benchmark architectures, but the results are not yet ready yet. On the other hand, another activity we focus on is the stress factor on the forested area nearby the artisanal mining areas. And we realize we have intersection over union 0.76 percentage. When we use Sentinel-1, 2, and digital elevation data, overpassing UNet and other classical approaches. And for TerraMind results, we will share it very soon in the upcoming period. In addition to use case downstream application and any-to-any model and VLM part of the TerraMind, it is also important to consider the ethical aspects and the energy efficiency and resource utilization aspects. So that is why we have some methods to monitor and compare existing architecture. And we know it is quite efficient as compared to the state-of-the-art foundation model so far we seen. For example, TerraMind base model took around 4,000 GPU hours, and the large model took more than 7,000 GPU hours. And we will later collect all downstream applications and the core foundation model development footprints to show the overall ethical aspects and the resource utilization of this project and at the end of this summer. So as a next step, we will focus on developing an open source data set, which is called TerraMesh Plus, to have more diverse modalities and the sequence of data. Integration of advanced SAR capabilities also in the plan. Embedding some governance tools and trustworthiness tools into the pipeline. And also we plan to optimize our foundation model for edge and cloud deployments. And lastly, we would like to demonstrate end-to-end operational workflows, which will be available for easy access for the end users, non-technical end users. For this very cool, behind this cool technology, there's a brilliant team here composed of the scientists from IBM, DLR, Jülich Supercomputing Center, and KP Labs. Thank you.
Questions?
Thanks a lot for the nice presentation. So I had one question regarding your conclusions. You mentioned advanced SAR capabilities. So what do you mean exactly by that? Is it
actually we have Sentinel-1 C-band. We would like to involve additional bands from different sensors, different SAR sensors. If we can manage, that's one of the next goals. Yeah.
Any other questions?
Hi, thank you for your presentation. I'm just curious about your any-to-any image generation module, and curious, what have you guys learned about the relationship between different input parameters? So you mentioned the cross-correlation metric that you had, comparing like the outputs of different sensors. So what have you learned about your capability to generate, let's say, an NDVI image or a SAR image from an RGB? Or what have been the key differences between these different sensors based on the model architecture and your research?
Maybe it is better to get the answer from IBM side, maybe Benedict or Thomas for this question.
Right, we can elaborate on this in the session tomorrow, if that's good. I think we have some examples there where in some downstream applications, kind of this any-to-any improves the performance. So you have maybe a Sentinel-2 image as an input, you create a Sentinel-1 in addition, and then that this improves the performance of some downstream tasks. So we still have to explore why this really happens. So we expect kind of that through correlation learning, the model gets some constraints which improve the results.
Okay, thank you. I don't have access to the session tomorrow, but...
Yeah, exactly, cool.
Yeah, just a short announcement. This was a short presentation, but tomorrow we have a deep dive session for TerraMind on Wednesday. And Wednesday afternoon, we have also a hands-on session for TerraMind. If you are interested in, please join.
Any final question? Okay.
Yeah.
One last there.
Thank you. Just a question harking back to a comment that we heard in the morning about the importance of trying to draw causal understanding from your remote sensing with observation data. I come from chemistry and chemometrics, biochemistry and physical chemistry, and we would never dream of using the raw data from our instruments. We always try to disentangle and separate within the physics and the chemistry and the instrumentation and so on. But it could be that I'm wrong. I think that could benefit Earth observation as well. With your wide experience, do you see any need for a further work on using causal background knowledge in the modeling treatment of your mass data from hyperspectral and multispectral imaging, for instance?
I think it is quite important because, for example, physical aware models are relying on background information and know-how about that domain-specific expertise. That is why it will be still useful, in my opinion. We cannot replace this with this pure data. Of course, pure data boosts geofoundation models, but such kind of domain-specific background information still have quite impact as far as I saw the example in our Air Force, but maybe the other experts, Thomas, if you have additional comment on.
For the TerraMind model, we also include NDVI in the training.
Yeah,
so this is one example where we use one of the handcrafted indices, which are very useful in the agribusiness or agri applications. So that's one example. Yeah.
Thank you, Ridwan.
I thank you.
And yeah, we'll continue discussions tomorrow. Okay, let's move back to Guillermo for ENISAT presentation. Thank you.
This is a spoiler. Okay. Thank you for having me here. I'm going to present ENISAT, one Earth observation model for many resolution scales and modalities, which has been accepted as an highlight at CVPR 2025. So first, why do we want to make foundation model? Because there are some foundation models that are really performant on natural images, for example, DynoV2, SAM, CLIP, but why are they so powerful? Is that they are big? Is that they see teras of tokens? We believe this is more of their training set, which is large, diverse, and especially curated and composite. But all of this is done because natural images are homogeneous. You can always have your data set of
256 images, 256 by 256 images, and it's really easy to create a composite data set. But how about we want to create this composite data set for Earth observation? It's really hard to merge because all the observations have different shapes, and I believe that just a reshaping operation is not a good thing, for example, for SAR data, where bilinear interpolation has no physical sense on SAR data. So we want a foundation model that would be trained on a single, all foundation models are trained on single data sets, but we want to perform self-supervised learning across different sensors, resolutions, and scales. And after this, we should be able to generalize to new input configurations if we have trained on a diversely enough composite data sets. First, we want to exploit cross-modal alignment. So we don't have a simple cross-modal alignment such as text with image. We have a hard cross-modal alignment which each part of the image is aligned to another part of the image. Each sensors capture different information, as other people have already told you, but they share the same semantic because they capture the same information on the ground. So a good representation of different modalities should be consistent across modalities because you capture the same thing, you capture the same semantic. But, and also, if you just align the different modalities, you're going to specify on the common knowledge of all your modalities, but you want to keep the modality-specific information because that's what's truly important in Fusion, to just fuse the modality-specific information. So for this, you should be able to reconstruct missing inputs. This evokes, of course, MAE. A lot of people talked about MAE already. So I'm going to just make an introduction of Omnistat, which was an ECCV 2024. We just put a contrastive loss on different encoders for different modalities with time series or very high resolution image, meaning that all of these tokens capture the same area. They should be close one to each other. But as I said, we won't keep information specific with this. So we then create multimodal patch embedding with the fusion and a modality combiner. And then from one multimodal embedding, we should be able to reconstruct all modalities, meaning that in this multimodal embedding, if we are able to reconstruct all the modalities, we have kept the information specific of each modality. But this approach has several drawbacks. For example, there are a lot of disruptors in the acquisition of an Earth observation, such as the weather, the season, or just even clouds. And this is not semantic information. We don't want to keep it, but for an MAE, it would be the most important information for the model because, I mean, according to the image, these are the same semantic, but you should retain that there is no if you want to reconstruct it. And also, we want to be able to generalize across different scales. For example, if you have huge images, you want to have a bigger patch size. And if you have just small images, you want to have a small patch size. So for this, we designed ESA-Nasa, which is directly built on a JEPA self-supervised technique, where we don't reconstruct in feature space, in pixel space anymore, but in feature space. For this, a target will just see the whole information and create the ground truth in latent space to reconstruct from the student network that have been masked. And then, for the scalability problem, we just design a scale adaptive encoders where we just can put whatever patch size we want. We then built our composite Earth observation dataset that we named Geoplex, which is just a pile of open source datasets that already exist. So there are a lot of sensors. We have 11 different sensors that are just throughout the globe. We have some temporal resolution. We have a huge gap on the spatial resolution. For example, we have from 0.2 to 250 meters by pixel as modalities. And on the results, we show that this model works really well, even for segmentation, because we are able to produce feature maps at the pixel density that provide us a lot of increasing of performance. And especially on Sen1 Floats 11, we are able to beat PRIT-VV2 with not 105, but 10 times 5 fewer parameters, with just a linear probing over a fine tuning. And we show that we are even able to adapt to new configurations. So on these datasets, we have different sensor configurations, some we have never seen during pre-training, and even different modalities. For example, on HLS, which is native PRIT-Viz modality, we are able to beat it on HLS burn scar. A quick view on the qualitative results, because, yeah, I mean, these are transformers with patch size. We always want to check that we don't have any patch artifact, and the reconstruction looks quite really natural. All of this work is open source, so code and models are released, and for example, with any set, you can just use it with 2 lines of code. It's only torch dependent. You don't have to download a specific virtual environment or something like this to use it. It's hosted on the Torch Hub. And we are working on the future work that should come out in not so long, which will be a truly universal model, because we reduce the number of parameters specific to each modalities in any set, but we want 100% shared parameters across all timestamps, channel resolutions, and yeah, to be the most flexible on scales and sensors possible. And thank you for your attention. If you have any question, I will be glad to answer them.
Thank you for bringing us back on time. Any quick question? We have to sharply leave at 1:45 for lunch, but we have time for questions.
I have a quick question. Have you tried anything on SLC data for the Sentinel-1?
On?
It looks like you mostly use GRD for the Sentinel-1 in the data sets, right? Have you tried anything on a more raw product with the model?
Sorry, I don't understand your question.
The slide you had with the data sets.
Yeah.
Go back.
Here. Sentinel, the Sen1 Flood 11 is mostly GRD. I was just wondering, it's a quite highly processed data product, right? So I was just curious if you've tried your model with something more less processed.
No, honestly, this is not a really work on data. We just assume that these data sets are like diversely enough, but we didn't want to modify the data set. We don't have any data augmentation as well in our work. Yeah, we just treat the data as it has been provided by the data sets.
Thank you.
Okay. Thank you, and hopefully we'll catch with Guillermo during the lunch. Thank you.
Thanks.
Appreciate it. And final presentation of this session by Genjar Sumbul on breaking representation barriers for EO, a sensor-agnostic foundation model.
Thank you for the introduction, Ahmed. Hi, everyone, again. I hope you have enough energy. I'm assuming that you're super hungry, but I hope my presentation will pay you off. I'm Genjar Sumbul again. I'm a postdoctoral scientist at EPFL, working together with Davis Tuya at ECO Laboratory. Today I'm going to talk about how we can break the representation barriers across different Earth observation sensors so that we can come up with a sensor-agnostic foundation model. And by the way, this work is supported by ESA through OSIP project. being text for that. So, okay, let's start. As we all know, foundation models have been found effective for automatic and large-scale analysis of massive Earth observation data through learning transferable image representations. Actually, they are quite powerful for reducing data sets or test-specific efforts by learning such representations. Unfortunately, we have such many models, although they have been proven effective for many diverse tasks. Most of them are still sensor-dependent, sensor-specific. For instance, we have Scale-ME for RGB data or SAT-ME for Sentinel-2 multispectral. And recently, we have also multimodal foundation models for Earth observation. And actually, most of them are computationally complex, demanding architectures, and still relying on fixed combination of sensors, like in Chroma. And they require massive pre-training sets to be effective, actually, so that there's a still significant barrier remains, the lack of unified image representations for sensor-agnostic processing of EO data. Which is indeed a very challenging task, actually, due to the heterogeneous nature of Earth observation data, and mostly due to differences in spatial and radiometric resolution and the spectral range that they cover, as you can see from an example of images here. So then, across such sensors, how we can break representation barriers, how we can pre-train a simple yet effective models while demanding as little data as possible to be effective, and how we can enable downstream transfer using a single unified model. So this is most of the direction of this talk today. So to answer all those questions, actually we have a very powerful physical property. All the different sensors capture subset of the full electromagnetic spectrum. So by leveraging this as our solution, we introduce ESA-MAE, a sensor-agnostic foundation model that unify sensor representations by projecting any sensor data into a spectrum-aware space that is shared and divisible. And on top of it, we pre-train a single transformer model with a self-supervised objective, reconstruct masked patches directly in the spectrum-aware space. So here is the illustration of our pipeline. We first extract patches from multi-sensor input data for transformer training, and then we apply spectrum-aware projection on patches directly, and then followed by cross-sensor token mix-up that I'm going to explain. And after it, we have spectrum-aware image reconstruction stage for mass data modeling. And finally, these steps allow for downstream transfer agnostic to any sensor. So let me introduce you each step in detail. For the first step, we aim to learn spectrum-aware projections depending on the considered frequencies, considered wavelengths. So to this end, we first project the bands of each sensor by using wavelength-specific projection layers. Actually, it is a simple linear layer, and then aggregate those projections to obtain patch tokens through averaging and scaling. Actually, such a design eliminates the need for separate models or backbones for different sensors. Thanks to that, we can tokenize images from all different sensors, so that on top of it, we can apply whatever we want, actually. So in the next step, which is cross-sensor token mix-up, we first use aligned image pairs from different sensors, and then exchange their tokens with mix-up to eliminate the bias specific to sensor or spectra combinations, and also increase the pre-training data efficiency, which is quite important for us. And later on, we feed the cross-sensor mixed embeddings into a standard encoder-decoder-based transformer that encodes tokens and mask out some of the tokens to reconstruct back, as you know from very well-known mascot encoder. Actually, it's a quite standard mask data modeling approach, but differently here, we reconstruct images back to the original spectral bands through spectrum-aware remapping functions, as in the first step. And by relying on mass data modeling with transformers together with token mix-up and spectrum-aware projection functions, our model can be effectively scaled onto larger models with more data and more sensors. So actually all those steps allow to use the resulting single encoder for any sensor downstream transfer, either by using the existing projection layers when they are available, or adapting them for unseen sensor by interpolation. So let me show you some results. For pre-training, we use pair images from the functional map of the world RGB, which is commercial, very high resolution data, and it is Sentinel-2 counterpart. And also, we use paired images from Big EarthNet that includes Sentinel-1 and Sentinel-2 images, so it's GRD data only. In total, we used 500K images, which is actually smaller than the existing models. That significantly reduces the pre-training time. And based on two well-known transformer backbones, we pre-trained two models for 300 epochs. And it's important to mention that compared to standard MAE, we have only 5 or 6 million more parameters, thanks to the lightweight projection functions and also remapping functions. And for downstream transfer, we performed experiments on diverse inputs, tasks, and setups that I will try to explain one by one. So let's start with the results for multi-label classification of Big EarthNet. And we obtained single model results on the third and fourth columns for Sentinel-1 and Sentinel-2, and also multimodal results in the last column. We tried both linear probing and fine-tuning setups, where you keep encoder and projection layers are frozen, or you continue to train. And for multimodal experiments, after tokenization, we apply token mix-up, actually, during the inference phase, and then feed the mixed embeddings direct to the encoder, concatenate the resulting embeddings, and so that we can apply any kind of downstream transfer. And for these specific experiments, there's a simple linear layer on top of the encoder. And here we try to compare with different large-scale models, but I mean, there will be much more actually, but just for the presentation. And as you can see, not all the existing models are capable of Sentinel-1 or multimodal data, or they need different pre-training stages to handle different conditions. But our model with a single backbone achieves the highest scores compared to those approaches by using the least amount of Sentinel-2 pre-training data. Here you can see on the left, our VIT large base model uses less than 300K Sentinel-2 data for pre-training, but still able to achieve actually very good results under linear probing, fine-tuning, and also on multimodal data. And for downstream transfer to an unseen data set, our models achieve state-of-the-art performance on Eurosat dataset for sync classification under linear probing and fine-tuning. Here you can see. Considering time, I will skip this. And for semantic segmentation on the FC 2020 dataset, we again add a simple linear layer together with upsampling on top of the encoder, which we kept frozen. And as you can see here, also for semantic segmentation, our model achieves higher scores than the existing models. That includes here Chroma, SAT, MAE, and IEJPA. And let's move to an interesting experiment where an unseen sensor is encountered during downstream transfer, as in the crop type segmentation on SICL dataset, which includes Landsat 8 images with thermal infrared bands, which are unseen during pre-training. And for optical ones, we have already learned projection layers for the bands of Sentinel-2 that we can directly use for the optical bands of Landsat 8. But for thermal infrared bands, we apply interpolation to unseen spectrum ranges based on the projection layers that we have already learned during training, so that there is no training for this stage. It's just interpolation of existing projection layers. Actually, under this setup, our model is capable of achieving the highest scores compared to fully supervised models even when we keep the encoder frozen. So the other two models are fully supervised and you train everything. For our model, we are just training a linear layer on top of the frozen encoder. And actually, there is a big drop in performance when we don't use the projection interpolation. That also shows the effectiveness of this zero-shot unseen sensor transfer. And on multi-scale RGB inputs, our model achieves the highest scan and classification scores, showing its robustness of different scales. Here you can see. And for sync classification on very high resolution RGB data, actually, our model achieves a remarkable performance by using a significantly smaller number of RGB images. Here you can see it's just 60K, sorry. And here in this slide, inspired by the TerraMind paper, we conducted full-way one-shot classification on Eurosat, which is a very challenging task, actually. And it's quite important to understand the effectiveness of learned image representations. And for each image here we want to classify, we have only 10 images and one per class, and we only do feature matching without any learning. And these results are averages of 200 random runs. And with our smaller VIT-based model, pre-trained with a significantly smaller data set compared to other models, we are able to achieve better than both pre-tuned models and close to the TerraMind models, which is actually on different scales in terms of the parameters and pre-training data. And for the pre-training data size and number of parameters, I try to mine, so you can see I'm going to the conclusion, just last slide. So to conclude, our model breaks representation barriers across Earth observation sensors, as I explained, and this leverages synergies between different sensors characterized by different spectral properties, eliminating the isolated efforts with a high pre-training data efficiency. And please stay tuned for model weights, code, paper, and more. In 2 weeks or more, we would like to publish everything. But we don't have enough people, actually, and we are planning to have one more PhD. If you're interested, please scan the QR code. Thank you for listening to me. I hope you will have some questions.
I'm going to apologize, but in the interest of time and everybody waiting for lunch,
Okay,
let's have questions during the lunch. So our ESA colleagues told me we should be back at 2:40 for the next session. So please enjoy your lunch, but please be back in this room or the other parallel room at 2:40. And yeah, please catch up with Gencer during lunch. Thank you, everyone. So we are going to start with the second session on the latest advancements in AI foundation models, and our first presentation is with Yi Wang. The title of presentation, Towards Unified Copernicus Foundation Models for Sentinels. Yi, please.
Yeah, thanks a lot for the introduction, and hello everyone. And I hope you had a nice meal. Actually, I enjoyed that. And today I'm gonna present our recent work towards unified Copernicus Foundation models for Sentinels. This is a joint effort with a lot of partners, aiming at advancing the current EO foundation models to the next stage with both the data, the model, and the kind of the evaluation benchmark. Right, so let me just recap again. I think most of you have been already well informed in the morning about the current background of EO foundation models. So I'm going to recap in 3 dimensions. First, there's still some challenge in the sensor diversity of pre-training data. For example, most of the models are still pre-trained on RGB or multispectral images. And with kind of rare exploration on SAR, we have a lot of current ongoing works and other thermal sensors, for example, the climate data. And second point, the current models, they usually lack in encoding flexibility in model architecture. They have rigid architectures to have fixed spectral channels as input. If you modify 13 channels from Sentinel 2, you might be not able to directly use a subset of the channels. So this is also one challenge. The third challenge is the evaluation breadth in downstream applications are usually still fixed in the sensor types, mostly Sentinel 1 and 2, and even RGB, and the task types, mostly classification and segmentation. So with these challenges in mind, we aim to push forward these EO foundation models in these 3 aspects. Okay. Okay, so in short, our contributions are like threefolds. One, Kubernetes pre-train, a big pre-training data set covering a lot of images from all major Sentinel missions, including Sentinel-3 and Sentinel-5P in there. And Kubernetes Foundation model, a flexible multi-model foundation model with the ability to process any spectral or non-spectral input. And the third, the Kubernetes bench, a comprehensive benchmark with 15 hierarchical downstream tasks, which I will present a bit later. All right, so let's start with the pre-training dataset. So Kubernetes pre-train is a unified pre-training dataset spanning all major Sentinel missions, from Sentinel-1 to Sentinel-5P. Of course, there are Sentinel-4 and Sentinel-6 that's not yet in major operation. So we're gonna extend probably in the next phase, organized in dense regional grids. This is in consistence with ERI5. As you may have known that ERI5 is a very famous climate data set with all the analysis data. And we align our EO imagery with the climate data such that there's a potential to link between them, which I will discuss a little bit in the very end. So the data sets, all the images are aligned with different modalities, and they are organized in the grids. So for instance, Sentinel-1 and 2, they are seasonal imagery. Sentinel-3 is almost monthly, and Sentinel-5P is, again, almost monthly. And we have also additional elevation model in there. And for each of the grids, we cover the whole grid for Sentinel-3, 5P, and DEM because they have a relatively lower resolution. And for Sentinel-1 and 2, we do the subsampling within the grids. This is a Gaussian sampling strategy, which has been used in seasonal contrast SS4EO series, and we use the same here. Okay, so in total, we have about 18 million, more than 18 million images of 8 modalities, grouped into 310,000 grids with 0.25 by 0.25 degree. So this paper shows some of the statistics, including the product names, modality, the ground sample distance, image size, timestamps, and so on. All right, so this is also the geographical distribution of the data set. So the left-hand side is the full data set with all the data. So for some of the grids, we don't have all the modalities available, but this left-hand side shows the grids that with at least one modality that's available. And the second figure shows the these grids that has all the modalities. So this is still pretty global coverage. And now let's talk about the model. So based on the Kubernetes pre-trained data set, we present one unified foundation model for Sentinels and of course beyond. So it has the ability to deal with any modality, not only spectral modalities such as like in the narrow sense images, but also these like Sentinel-5P atmospheric variables, like nitrogen dioxide, for example. And they support the metadata as additional input if it's available. So this is realized by two core designs. One that is extended dynamic patch embedding, inspired and extended from DOFA and FlexiVIT. And the second one is unified Fourier encoding to encode metadata. This is inspired from Aurora, one famous climate model. And we do the pre-training in mask image modeling plus continuous distillation, kind of combining mask image modeling and the contrastive learning concept. But we are not doing contrastive learning here. So let's walk through the pre-training pipeline. So given a common grid, there are a bunch of images for different modalities. We sample one image for each modality, and they are patchified with dynamic patch embedding layer, which with the corner weights generated from these hypernetworks. If it's a spectral input, such as Sentinel-2, you have a spectral response. So it goes to the spectral hypernetwork using its central wavelengths and bandwidth to generate the corner weights. Or if it's a variable input, for example, digital elevation model, there's no spectral, there's no fixed spectral response, so it's go to the variable hypernetwork. I will go to the detail later. So this enables us to process any modality. And after that, we also add metadata tokens by using Fourier encoding to encode location coordinates, the area, the scale, and the time of the acquisition date. So the training design, the training architecture is a standard transformer. So we do mask image modeling plus continuous distillation with DynaV2 to subsample the RGB bands from Sentinel-2 to make use of the powerful DynaV2 vision foundation model. So let's dig a bit into the details about the first one, the dynamic patch embedding. So if you are familiar with DOFA, so this is a similar extension of DOFA. For spectral input, we use wavelengths plus the bandwidth of the spectral response of each channel. and they are encoded into using Fourier encoding into like feature tokens, and using a transformer to project these tokens into the hyperplane, and then use this hyperplane to generate the weights for the first layer of the patch embedding layer, usually a standard convolutional layer. And that's the spectral input. For non-spectral input, we do not have quantitative attributes of the metadata of the channel response, but we have the name of the input. For example, center 5p nitrogen dioxide, center 5p some of the atmospheric variables or digital elevation model, and these names are available, and we have the powerful large language models outside, so we just use a large language model to encode these variable names as text. So they still, after that, that's the same. So these language tokens are projected into the hyperplanes and then reshaped to the corner weights of the first convolutional layer as the patch embedding. Okay, and then for the metadata, this is a bit simpler. So we simply use the Aurora Fourier encoding. This is another way of positional encoding to encode the location, the scale, and the time of the image, and all the these spectral or non-spectral response into these also meta tokens as position encodings and added to the patch tokens that's sent into the transformer architecture. Right, so this table shows some of the ablation studies that shows kind of consistent improvements of each of these different blocks that we added with the baseline of DOFA plus the dynamic patch size, because we have pretty different sensors with very different spatial resolutions. For example, one grid for DEM, it has almost 1,000 by 1,000 pixel size. And for center 5P, because it's 1 kilometer spatial resolution, so it's like 28 by 28. So we do dynamic patch size, similar to ANISET. I think you have known that in the morning. And apart from all of these major like blocks, we also find that for the metadata, it helps a lot, of course, and also the coordinates of the metadata is helping the most. And for this one, you can refer to the appendix in our released paper. I'm going to skip that details here. All right, so then finally the benchmark. We present the hierarchical benchmark, including 15 tasks covering all major sentinel missions. We organize the tasks into 3 levels. First level is pre-processing, mainly clouds. And second level is land use land cover, the base applications that is further extended to a bunch of different applications. And the third level is specialized applications, for example, flood mapping, biomass estimation, and so on. Most of the data sets, like 9 of them, are derived from existing data sets, and 6 of them are newly curated, mainly for Sentinel 3 and Sentinel 5P, which are not very much present in the current literature. So here's just a simple table for some benchmark results comparing our Kubernetes foundation model with state-of-the-art single model foundation models, dual model foundation models, or any model foundation models. And it just kind of demonstrates consistent performance, comparable performance of Kubernetes foundation model compared to the existing models in like these existing well-established modalities such as Sentinel 2 and Sentinel 1, and also, of course, quite superior performance on Sentinel 3 and Sentinel 5P for these new sensors. All right, so that's the standard efforts that we have had. One more thing that I would like to share a bit here is what exciting direction of linking EO with climate. If you have still remember in the very beginning, we have the Kubernetes prediction dataset that's aligning EOI5 with EO data. So we just based on that, we create a toy dataset or toy task to predict 10-year mean and standard deviation of 6 climate parameters from EOI5, and just use the geographical coordinates or the embeddings. So this is the one toy task to evaluate the performance or the potential to link them. So if you can see from the table, using only coordinates, using encoded coordinates, using the EO embeddings, the grid embeddings that we get from encoding the images into like feature vectors, and using embeddings plus the coordinates. Definitely using the embeddings is performing much better than using the raw coordinates itself. So this shows that this EO imagery does have some help to the climate kind of characteristics. And using embeddings plus coordinates, definitely having the best performance. And this is just climate strategy, so very long term. We also foresee that these embeddings can potentially also help weather forecasting. For example, as extended surface variables, static surface variables in EI5. Currently, EI5 has this land mask, for example, water mask. These are static surface variables. Maybe our EO embeddings as a map of the globe can be some extended semantic information of these surface variables. And this could have great potential in the future. So to wrap up, we have presented a series of efforts towards next generation EO foundation models with a data set, a model, and benchmark. We also demonstrate the potential of bridging EO and climate with EO learned embeddings. And we foresee this as a great potential in the next direction of EO and climate research. So all of our data, codes, and models are available online. Every related information can be seen in the GitHub repo. And also you can scan the QR code to find that. If you have any questions, you can feel free to ask or send me an email later. Thank you.
Thank you. Questions?
Hi, thank you for the talk. So you basically pre-train on the whole planet. And so you may have some kind of registration of the whole globe. And you test on a lot of static data. But have you tested, for example, disaster prediction or things like this that just are out of the scope of your pre-training? That basic, I mean, you have GEM, so for example, I'm pretty sure that you will be really good at heights of trees or things like this.
Mm-hmm. That's a good question. So I think that's also within our initial scope of the evaluation. Because of it's just too many sensors, and so that's in our first stage. We just focus, kind of expand a little bit the existing benchmarks with, for example, land use and cover is very well evaluated, the second level, right? That's the standard. Everyone evaluate on some part of the data sets. And we do not specifically evaluate on, we do not specifically curate one out-of-domain data set. Let me phrase like that. But all of these data sets are kind of, we do not intend to cover them. Also, our Sen1 and Sen2 data are, they are not covering the whole globe. They are just still do the subsampling within the grids. So, for example, we have flood. Here is kind of one disaster response, but it's standard machine learning data set still. So, for the real, let's say, to really deploy it into, test it on a real scenario, I think that still need to be done in the next step.
Thank you, Yi. Let's continue the chat in the break. Thank you.
Thanks.
Our next presenter is Zhitang Jiang, the GeoLang bind, unifying EO with agglomerative vision language foundation models.
All right. Good afternoon, everyone. My name is Zhitong Xiong, and I am from Technical University of Munich. I am from the chair of Data Science in Earth Observation. And today I would like to introduce our recent work. The title is GeoLanguage Band, Unifying Earth Observation Data with Agglomerative Vision Language Foundation Models. And let's begin with the challenge. As we all know that there are different EO sensors, and we have captured different EO data from these different sensors, including the RGB data, the SAR data, the multispectral data, hyperspectral data, infrared data, and digital elevation models. So as these data are captured using different sensing principles, so there's a problem. The diversity makes it difficult to do a unified analysis. And we also consider the popularity of large language models. So we have a research question is, can we use the natural language as a bridge to align these different EO data modalities? So our goal is very simple. We would like to develop a foundation model, we call it the GeoLanguage Band, to unify these diverse EO data modalities using the language embedding as a shared common embedding space. And here I summarized the key contributions in the geologic band. The first contribution is we developed a new large-scale data set. We call it geologic band 2 million, which contains 2 million image text pairs spanning 6 different EU data modalities. And the second contribution is we developed a new model architecture, and which includes modality-aware knowledge agglomeration module. We call it MACA, and the other one is a wavelength-aware range encoder. This is identical to the DOFA model we developed. And the third thing I think is very interesting is we developed a new efficient training strategy for this multiple modality data. We call it progressive with merging strategy. And finally, our model can achieve state-of-art zero-shot performance across many EU data sets and tasks. So first, I will introduce the geologic band 2 million dataset. As we all know, there are many image text data for natural domain, but for EU, I think most of the data only includes the RGB image with text descriptions. So to solve this problem, we created a geologic band 2 million dataset. This dataset contains 2 million image text pairs, which spans these 6 key data modalities. Yeah, you can see here, including RGB, SAR, multispectral, hyperspectral, infrared, and elevation data. And in the right side, you can see the visualization of some data samples from our dataset. Each sample is paired with very detailed textual descriptions capturing the key land cover types, objects, and geographic features. And then we come to the model architecture overview. You can see the left part is the main architecture. The upper part, you can see the input, which is the text input. We use the SIGLEAP text encoder, which is frozen to extract the text features. And the lower part, we have different modalities as the image input, and we use the DOFA VIT to extract the image features. And in the middle part, you can see there's a contrastive loss, which is used to train such a model. So it's very, very simple, actually. And the additional module we designed, we call it a MACA. You can see in the left side. We would like to further enhance the image features, the spatial details, and the semantic content of the features using existing large-scale foundation models like SIGLEAP, DynoV2, and imminent pretrained. Yeah, here I will not go into the details. In the following slides, I will introduce the 2 key techniques we use to train such a model. The first one is the MACA module. We call it a modality-aware knowledge agglomeration module. The purpose here, as I just said, is to enhance the fine-grained spatial patterns of the image features beyond just a simple image level text contrastive alignment loss. And how it works, as we can see from this figure, the right side, we have we have multiple teachers, and we do feature matching to do multi-teacher distillation, and we propose the MACA module to let the model know which EO data modality the model is handling. So the model can be adaptive to different EO data modalities when doing the knowledge distillation. So this module, I think, is very crucial for adapting the knowledge distillation module to different EO modalities and improve the knowledge distillation performance. And I think the other key technique here is the progressive with merging. As we know, we have 6 different EO modalities, and actually these data are quite imbalanced. in our data, RGB data actually takes more than half part of the data set. If we just simply mix everything together to train the model may be significantly biased to the RGB data. So to solve this problem, we designed a strategy which is more effective than simply mixing all the data together for the training. So this strategy is we train separate models on these different data modalities in parallel, and finally we do a linear weight merging for these different data modalities to get our final model. So first of all, we we merge the original SIGLIP data, the original SIGLIP with our RGB model using a factor we call it M1, and then we merge the intermediate model with the model trained on other data modalities using a factor M2, and finally we get the final model. So this is very simple, and we can make it very easy to scale up to more data modalities. This means that we don't need, when we have new data modalities into the data set, we don't need to mix it with the original data and train the model again. We just need to train on the new coming data modalities and merge the model into the older one. So it's very easy to scale up to more data modalities. And then we come to the result part. The first one I would like to show is GeoLanguageBand actually improved the cross-modality alignment, which is our motivation. And we use the TSNE visualization to realize whether our model can align these different EU modalities with the text modality. Here you can see the circles represents the language features, and the triangles represents the image features, and the same color means the same modality. Different color, you can see here the same color with aligned well for the image features and the different EU data. Yeah, the second result is our model, thanks to the Markov model we designed to improve the spatial details and the semantic patterns. We can see here we realize the deep features of GeoLanguageBand and also some existing models like Remote Clip and SkyScript. We can see that GeoLanguageBand can produce features that capture finer spatial details and the semantic structures compared to the existing models. And regarding the zero-shot model evaluation, we have done experiments on more than 20 diverse EU datasets and tasks, including the zero-shot scene classification, semantic segmentation, and fine-grained classification, cross-model retrieval. And actually, our model works quite well on these different tasks, even in zero-shot matter. And then we come to the conclusion. Our summary is GeoLanguageBand showcase an example of a unified vision language model for diverse EU data modalities. We use the language as a bridge. And the key contributions are GeoLanguageBand 2 million dataset, the wavelength-aware encoder, which is identical to DOFA, and the Markov module for multi-teacher distillation, and also the progressive weight merging for efficient and effective training, especially when we have new data modalities coming in. And the dataset and pre-trained models will be made public very soon. And we believe that this idea can not only be used in this EU data, we can even extend this idea to weather variables and to put it together with this EU observation data to do a unified analysis. And thank you very much. So.
Questions from the audience? I can ask one. So the heat map you were showing from the features that you compared remote clip to your model and others, was that for a specific layer in all of those models? How did you, because different models have different architectures, how did you decide on which layer you compare these features from? I didn't get that part.
So you mean which layer we're using?
Yes.
Yeah, actually we're using the last 6 or 5 layers of the features and do a mean average.
Okay, so this is average of multiple feature layers. Okay.
Can you expand a little bit on the advantages you found on using something like building on DOFA rather than doing like most people are doing in the community, trying to adapt something that comes from RGB world and just doing continual pre-training most of the time on EO from the vision encoder perspective?
Okay, so the question is why we choose DOFA to build upon.
Different approach to what was tried before, so we seem to what we do.
Yes, I think this is a very good question. As there are something I did considering the limited space and time I didn't present. Actually, DOFA, as you know, it can accept any number of channels as input if you give the wavelengths, or by default, we just use the RGB data. And so our zero-shot model here means that even you're using an unknown sensor, we haven't trained in our encoder, it can still perform the zero-shot scene classification. So this is the benefit of using a vision encoder such as DOFA.
One more question, maybe?
Hello. So, what's the benefit of using, in your opinion, progressive weight merging with respect to, for example, fine-tuning or retraining simply? In which situation would you do a weight merging rather than retraining or a fine-tuning?
Yeah, I think this is also a very good question. Actually, we have done experiments to compare. Actually, first of all, we train the model directly on the mixed EO data modalities of data, and the performance is not good. It is biased to the RGB data and perform very bad on the other EO modalities. So and finally, we found a very efficient strategy is we can train these 2 models in parallel, and finally we do a very simple linear interpolation of these weights, and we get the final weights which can perform zero-shot tasks on both the modalities. So the benefits is we can train this model in parallel, and we do a post process to combine these different data modalities into a unified one. And when you have new data modalities, you don't need to mix this data with the original data and train it over and over again. You just need to train the geologic band model on the new EO data modality and do a linear interpolation of the weights, and finally you get a new model that can handle all these different data modalities. I think this is a good way to scale up to more data. Yeah.
Let's thank Jitang one more time. Thank you. Our next presenter is Joel Hanna, presenting on MapX, a modality-aware pruning of experts for efficient multimodal remote sensing foundation models.
Yeah. Hello. Hey everyone, thank you for being here. I'm going to present today our latest work that is called MapX. It stands for Modality-Aware Pruning of Experts, and it was a work done together with Linus Scheibenreif and Damien Bort. So I'm going to start by setting up a bit the context here and explaining to you what the problem that we're trying to tackle is. So a very common setup in computer vision or machine learning in general is to start with a large model and to pre-train it on unlabeled data, and then in a later step, use a smaller set of labeled data and fine-tune it for a specific task. So I think this is very standard. Now, what is a bit specific about remote sensing is that many applications rely on certain type of modalities. For example, you might need to use SAR for some applications, or infrared, or elevation maps. And you can see that all of those modalities are very different from each other, but they're also very different from the modality that was usually used for pre-training, which is usually RGB or multispectral data. So the first thing that you see here is that there's clearly a mismatch between the modalities that are available for the application and the modalities that are used for pre-training. A second thing that you might see also is that pre-training usually leads to large models, whereas downstream applications require lightweight models in general. And my point here is that there's clearly a gap between what is happening in the pre-training stage and what is actually useful for the applications, be it on the size of the data or on the task or the modalities available. So what we're trying to do here, and our solution to try to mitigate this gap, is to go from foundation to lightweight specialization. So our idea is to start with a model that we pre-train on 6 modalities. Of course, we can add more later, but so far we started with those 6 modalities. And our goal would be to train this foundation model and try to specialize some part of it for some modalities using a mixture of expert architecture or a mixture of modality experts. So the idea would be to specialize those experts for some modalities. And why this is useful? This is useful because if we have, for example, for some applications only access to SAR data, well, we can prune all the irrelevant experts and only keep the parts that is interesting or useful for SAR data. If we have 2 modalities, well, we can keep, for example, 2 parts of the model. And the point here is that the models that we have for the applications are genuinely smaller. It's not just that we're setting weights to 0, we're actually pruning the weights. And this pruning step is for free in the sense that there's no computation involved, right? It's just getting rid of some experts and only keeping the ones that we're interested in. And this whole machinery is what we call here MAPEX. So it's a modality-aware pruning of experts. Now, I'm going to dig a bit more into how MAPEX actually works. So we start with a set of modalities. Then we patchify them. We add a positional embedding. So far, this is very standard to any transformer. Then we add a modality embedding. So this modality embedding can be seen as a spectral encoding. So the positional will be the spatial encoding, and the modality would be the spectral. Spectral in the sense of the number of modalities. So if you have 6 modalities, well, the depth will be 6. It's not related to the number of channels for each modality. It's related more on the number of modalities. And this modality embedding will be learned during training. Then we have an encoder, which is like a VIT backbone. It's different blocks of self-attention, and instead of feed-forward networks, where we have a mixture of expert architecture. So instead of 1 feed-forward network, well, we have 12 if we have 12 experts, for example. And if we zoom a bit more into this, before the experts, we have a router that will decide to which expert the tokens should be routed to. And if we zoom here a bit, we will see that the router takes as input this modality embedding. So that's why it was useful to add this. It serves as an identifier to the modality. So we feed this to the router outputs some probability distribution, and then if we keep, for example, the top 2 expert, we route all of the tokens from that modality to those 2 experts. So that's a bit also what's different between a regular mixture of experts. So we don't split, we really route all of the tokens of one modality to the 2 picked experts, for example, if k equals 2. We do the same for all the different modalities, and we can see that sometimes experts can be shared across modalities, so they can be picked twice, and that's fine. I mean, we're not. I mean, it can mean, for example, that the modalities share lots of information, so that's fine, and it happens quite often, though. Now, if we go back to the big overview, so we have this encoder, and during the training of the encoder, we will specialize the experts. Then we will add a decoder, which is also a standard transformer blocks, and then we train the whole pipeline for masked image modeling. So we masked some parts in the input, and we're trying to reconstruct them after the decoder. Now I want to mention something. So the experts here are specialized, but there's a big part of the model that is not specialized, so it's shared, so the self-attention and many other parameters. So in order for those also to be robust to different amount of input for the application part, well, we also add some modality dropout during training. So we randomly mask some modalities just for the remaining part to be robust also to a different number of input. So that was it regarding the pre-training stage. Now, as I mentioned, there's pre-training, pruning, fine-tuning. The pruning is very straightforward. So as I mentioned before, it's kind of for free. We're just removing the parts that we're not interested in. For example, if you have the modality blue, well, we only keep the experts blue. So this is a very simplistic visualization, but it's pretty much what is happening. There's no computation involved. We're just removing the parts that we're not interested in, and we end up in really a smaller model in size and in number of parameters. And it's only that small model that we will fine-tune later, so we'll add a task head, and then we'll fine-tune that, which will be much easier than fine-tuning the big model. Yeah, so that's it regarding the whole training and pruning. Now, if we go through some results now, the first result here, the big table, is for land cover classification. So each row corresponds to one modality, and so I compare on the right column corresponds to our smaller pruned models. And the first thing that we wanted to compare to it was more of a sanity check to see that, to check if the pre-training actually works. So we're comparing our smaller pruned models with the same size, same architecture, but trained from scratch, just to make sure that the pre-training, the way we're doing it, actually works. And I mean, it was kind of expected, but it does help. It consistently improves the performance by 5 to 13%, depending on the modality, but it's a consistent improvement. So this was more of a sanity check for us. The second thing, if we focus on those modalities, the first three, you can see that if we compare our models on the right to other foundation models, you can see that, for example, Scale MAE outperforms our model. One explanation can be that, I mean, it's 2.5 times the size of our model, so this might be an explanation to why this is the case. But if we look at the other modalities that I'm highlighting now, I mean, those are actually very different than those that Scale MAE or SAT MAE have seen during training. And on those modalities, our method consistently outperforms those foundation models. And the point here is that this highlights actually the problem of this modality mismatch. So the more the data is different from the pre-training and to the application, well, the more fine-tuning it will require. And what is cool about our approach is that we can add as much modalities as we want in the pre-training, and even though it's a bit expensive to pre-train, well, we do it only once, and then we can prune many smaller versions of the model and use those for the applications that we are interested in. Now, also, I'm going to quickly show that other applications, so we tried also flood detection. It's also outperforming our model, outperforming other foundation models. We tried wildfire detection. It's basically the same performance. or sometimes outperforming 2. We also tried segmentation just to show that it also can work on fine-grained tasks and not just on classification tasks, because so far it was only classification. We wanted to also compare it with a standard UNet, and it's comparable in terms of performance, which was actually pretty cool to see. Also, I'm going to quickly show some ablation studies, because when we're talking about mixture of experts, I think an obvious question would be like, how many experts should we have in the beginning, and how many experts should we keep per modality? So we did a small study, and I think a good compromise between accuracy and size was to keep 2 experts per modality, and this is what we used throughout the study. Because, I mean, if we keep more experts, the size will be bigger, and it defies a bit the purpose of everything we were trying to do. So it was a good compromise to pick 2 experts. Another ablation that we did was on the type of routing, because also this is a main point in our mixture of experts. As you see, so as you remember, we feed this modality encoding to the router to decide to which expert we should route the tokens. And this modality embedding, I don't know if I mentioned it before, but it's learned during training. So we initialize it and then we let it learn. So we compared this, which is on the right, to the same fixed modality embedding, as like a sinusoidal positional encoding, but on the depth dimension, which is the second column from the right. And then we compared this also with a deterministic approach, where we, for example, we fixed the first 2 experts to be for modality 1, 3 and 4 for modality 2, etc. And well, the best was the one we kept, obviously, but it's also because I think we let it learn. Okay. Anyways, just so this is the concluding slide. This is just to summarize why MAPEX is actually pretty cool, because it combines the best of both worlds. So we're taking advantage of large-scale pre-training, multimodal pre-training with also task-specific specialization. The models are lightweight and outperformant, and we can use as many modalities as we want at test time. Thank you.
Thank you. Time for one question, just behind you.
Yeah, thanks for a very nice presentation. I was wondering, you said that the pruning is without any compute. How do you figure out which expert is specialized on which modality?
Yeah, so this, since we, so the routing, well, you can look here, it's the same small design. The routing takes as input this modality encoding. So at the end of the training, we know the modality encoding, and we can just feed this to the router, and if we keep the best 2, we know which ones are those. Yeah.
Maybe one more question.
Thanks so much. It was very impressive. Quick question. What will be the impact, or do you have a quantification of the impact if you are performing the pre-training on multimodal as compared to having the expert from the get-go on one single modality? Just a very rough number if you have that in mind.
So comparing this with what exactly?
So right now, you have your initial pre-training on multimodal data. Question is, and then you would prune your experts. Question is there a quantification if you only perform the pre-training on one single modality? For instance, you showed that for SAR, your expert is actually outperforming. Question is, what if you actually pre-train your model, a single model, on SAR only, and you don't have this shared modality, if you have a quantification of the impact?
So we have it somewhere. It was better that way, but I don't remember by how much, maybe 1 or 2%, not huge, but a bit better. But do you mean pre-training? Because we also have the same, this is, just a second, we have here on, here, the right column is if we train from scratch on SAR versus our prune model on SAR. So there was no pre-training involved, but it's trained on SAR versus the prune version. Yeah. I think that's the closest to your answer that I have on the slides. Yeah.
Okay, we changed the program slightly. Right now there will be Jonathan Prexel presenting from University of the Bundeswehr in Munich. And he will talk about towards sensor-informed foundation models for satellite-based Earth observation.
Okay, hello everybody. My name is Jonathan Prexel. I'm finally a PhD candidate under Michael Schmidt at the University of the Bundeswehr in Munich. And today I want to present you two of our works from our lab that deal with the concept of sensor awareness in the context of EO foundation models. So each measurement we are taking or each data we are getting from a satellite is always uniquely linked to a set of sensor parameters that actually describes the nature of the measurement that you did. And now that we move towards the heavy usage, I would say, of foundation models, we would argue that it's very important that those models are kind of aware of what the specific sensor parameters are, especially when they process data from multiple sensors or in multiple conditions. And I will show you an example in a second. So today I want to show you two works very briefly. One is called SenPaRMal, short for sensor parameter mal, and it's a framework for multispectral data, and the other one is called SAR-Former for high-resolution SAR data. So looking at the first one, so in the SenPaRMal framework, the goal is to have a network capable of processing data from multiple multispectral satellites. And in order to make the model aware of what's actually presented, we inject the main sensor parameters of the sensor. So the most two important sensor parameters that describe you what kind of multispectral signal you're dealing with is firstly the spectral response function, and you see it here at the top right for three different sensors, for Sentinel-2, Landsat, and Planet SuperDove for commercial sensor. You see that each of those bands has a unique spectral response function that gives you kind of the sensitivity of the channel with respect to the incoming light as a function of the wavelengths. And next to that, the second and maybe a little bit more easy to understand concept is the ground sampling distance. Is probably everybody's dealing with that quite often. And you see at the bottom for the same screen sensors an example on how that looks from going from 30 meter over 10 to finally 3 meter ground sampling distance. And so now we want to pre-train a network with data from all those three sensors, and for this we choose, as many people did apparently, mask autoencoding as a self-supervision task. So we train a vision transformer on data from Sentinel-2, Landsat, and SuperDove. And sensor parameters are included in the following way. So on the right-hand side, you see the mask autoencoding framework, and maybe a small modification or small comment here. So we do one token per position in the image per channel. So not all the channels merged into one token, rather we leave them separately. We will see in a second why. So after embedding and after positional encoding, we have this, what we call here, sensor parameter encoding module, and we take here the two quantities that I just showed you, the spectral response function for each channel and the scalar value that describes you the ground sampling distance. We embed them with two small neural networks and add them onto all tokens corresponding from one position, or from one channel rather. And this gives the network the opportunity that each token is uniquely identified by the corresponding sensor parameters, and the model can be aware of what's actually presented. So in this framework, there was a second kind of contribution, and that deals with augmentation. So of course, we want to usually, especially during pre-training, have augmentations on our data to have as diverse as possible data set. But if we work in this concept of keeping the physical integrity of the signals, we can of course not just adjust the brightness values of our reflectances up and down. So in order to work around this, we introduce what we call a spectral superposition augmentation module. And what you do here, it's shown at the bottom, you take two channels from your input signal, and you take the corresponding spectral response functions, and you can add them up. You can also have different amplitudes for them. You can add them up, so build a superposition, and that contains the physical integrity of the signal as long as you do the same for the spectral response function. So you also have to add them up with the same amplitudes. And the second kind of augmentation that you can apply is downscaling, and it also still gives you a meaningful signals as long as you apply the right downsampled ground sampling distance then into the sensor parameter encoding module. So pre-training then would look like this. It's a small example. So here each row corresponds to one channel of your incoming data tensor, so to say, and you see we have like different ground sampling distance. So within one image you can have different resolutions, and we have different spectral response function. That just means we have different channels. And in the first row there's also an example for the application of the spectral superposition augmentation, where this is so to say a synthetic channel that we get by adding up two of the incoming channels. And then on the right-hand side, you see the random mask. We apply a random mask per channel, and then all the way to the right, you see the reconstructed image where the input data was masked. So now, of course, we want to see if this is any useful, and for this we did a bunch of experiments. Today I just want to show you one, which deals with zero-shot distribution shift. So we take this pre-trained network, which is pre-trained on data of the 3 sensors, and we're going to fine-tune it to predict the ESA world cover class via a dense prediction transformer extension in one specific sensor arrangement. So fine-tuning is only done with the 10-meter GSD channels of the Sentinel-2 mission. And then we're going to test in a zero-shot manner. We test how the model reacts when we present different data. So we have kind of different magnitudes of a change in distribution. For instance, here, as you see on the bottom left, we can only swap out one channel, or we can even take data from a different satellite, and you can either do take the matching channels, or you can even make it harder and take the exactly non-matching, non-aligning channels here. And then we get following kind of results. So on the left-hand side, you see the validation scores for 3 setups validated on the same data where you also do the fine-tuning. And I quickly walk you through. So the blue model, the blue bar is a UNet baseline trained from scratch, and the 2 green ones are both pre-trained models on the big data set with all the 3 satellites, so Planet, Supernova, and Landsat. But the light green one in the middle is without sensor parameter encoding, and the dark green one, there's the sensor parameter encoding applied. And now if we do the zero-shot evaluation and go to the right side, you see that, and it's kind of expected, especially for the model trained from scratch, the performance dropped significantly because it never saw anything else than only the 4 10-meter bands of Sentinel-2. Whereas multi-satellite pre-training helps already a little bit to stabilize, but even better if you have this kind of sensor parameter encoding active. So this is one example on how you can make your model aware of your sensor parameters in a multispectral scenario. And we wanted to extend those ideas and move it to high-resolution SAR data. And so in the second publication, we have a quite similar concept. The main difference here is, up to this point, we dealt with multiple satellites. Now we have only one sensor, but what's changing is actually the acquisition conditions on how we observe the scene. Because in high-resolution SAR imagery, typically your imagery is task, so it's not constant monitoring, and therefore you have different looking angles, azimuth angles, or orbits even, or also imaging modes like strip map or the higher resolution spotlight imagery. And the idea is quite similar, and we want to encode those kind of acquisition conditions, as we called them, into the model. So for this, we took 200 tandem X acquisitions with different acquisition parameters, and we have a framework where we either supply the network with one SAR acquisition or with multiple over the same scene, but those multiple acquisition would then be from different angles. So you look at the scene from different directions. And once again, we want to inject the acquisition parameters here, and we do it slightly different by the introduction of a metadata token. So for each input view, we have one additional token beside the image tokens, which carries the meta information. And this is in contrast to what I showed you earlier in the SenParMile context. There, we added the sensor parameters onto the image tokens themselves, like a positional encoding. Here we found out via some experiments that it's beneficial to have this additional token. And the whole framework is evaluated in a multitask setting where the tasks here are the prediction of the height above ground, so the DSM values in two geometries, in the slant range geometry and the ground range geometry, as well as the prediction of the building footprints in a binary way here. But all the results that I will show you in the following, it just corresponds to the height in ground range, since this is probably for most of you the most interesting quantity here. So just to give you an impression, here's an example. So we have an aerial imagery, so you have an idea on how the scene is looking. Then in the middle, the high-resolution SAR image. This is a strip map acquisition, and height above ground LiDAR ground truth on the right-hand side. And at the bottom, you see the comparison between like a standard unit that we trained, our method with the active acquisition parameter encoding without pre-training, and then the best performing version all the way to the right when we pre-trained the network in a self-supervised manner. And so up to this point, this was only SAR data from one sensor, and I want to finish with a little preview. So we started to extend this framework onto multiple SAR sensors, and so I brought you a little example here. So this is a scene over Berlin, and we have collected data from ISA, Capella, and Umbra, and you see this in the middle row, the SAR imagery. So this is SAR imagery acquired, of course, by different sensors, since it's different companies, but also different imaging modes, as well as different angles and orbits. And at the bottom, once again, you see what I just showed you, the height above ground prediction. And I would say beside maybe the vegetation areas where changes could be due to seasonal effects, you get a very homogeneous way across all three sensors. And that's it from my side. Thank you very much.
Thank you, Jonathan. Questions?
Thank you. One quick question. What you've shown for SAR former is mostly for high-resolution SAR. Question is, could you comment on medium resolution, or like Sentinel-1, and the impact that you would foresee?
Mm-hmm. So in the case of Sentinel-1, of course, it's like constant monitoring. So we have, I mean, the angle, of course, changes within the image, where the acquisition angle, but it's not as drastic as in high-resolution SAR, where you spot, where you would actually steer the satellite to see something, maybe even like quite off nadir, and then the effect is quite higher. I mean, most of the people, like when we looked today and we saw the networks that deal with SAR, I guess nobody would take into account if the patch was acquired closer to the sensor further away. I would say on 10-meter resolution, or it's actually like 5 by 20-meter resolution, you can neglect those kind of effects.
Yeah, also thank you from my side. Very interesting. So I'm wondering, in the first work that you had, you said that you are encoding the spectrum with the linear layer. I was wondering, how do you encode the spectrum as the input to the linear layer? So how do you transform this to like a number of parameters?
So I take the spectral response function, which you can just download for every satellite in orbit from the internet, and that's just like you get a CSV file with maybe 2,000 values, right, as discretized over the wavelengths.
And this is just pure values that you take.
I answered your question.
Okay, yeah, thank you.
Mm-hmm.
There's a last one there. One more, it's okay.
Quick question on the optical data. Did you use TOR or bottom of atmosphere data?
Surface reflectance. So
surface reflectance. But isn't the spectral response function already incorporated in the atmospheric correction? So then you have, say, like a double treatment?
In how far? No,
usually it is. So in if you do radiative transfer modeling, you would also consider the spectral response function for that.
I mean, maybe you use the spectral response function for the atmospheric correction, but it still exists afterwards. I mean, we are measuring whatever, if the spectral response function gives you a central wavelength and a certain width, this is still what you're observing on the ground. You observe the reflectance within this window. So this is, They're all normalized. I normalized it, so they're all normalized already when I put them into the network. Yeah.
Okay, so maybe we have time in the coffee break kind of to follow up on this question. Thanks, Jonathan, again. So now we have a speaker change. Instead of Nikolaos, we have Papa Zafeiro Boulos. Is he here? Yeah, okay, great. He will talk about investigating redundancy in remote sensing images and their implications to foundation models.
Hello everyone, I'm Tasos Zafiropoulos from Orion Lab, a lab between National Technical University of Athens and the National Observatory of Athens. Today I'm going to talk to you about investigating redundancy in remote sensing images and its implication to foundation models. By the end of this presentation, I want to be understood that we don't need all the information we have. So let's go to the motivation of our idea. And I think the best way to understand our motivation is by an example. So let's go for the first example. How many of you can recognize the objects in this image? In this, slightly better. In this, I'm sure that many of us can recognize this object. This is the original image. So, in the first image, we saw only the 5% of the image. In the second, the 15% of the image. And the third, the 25% of the image. So, a definition of redundant information could be that the information which is not necessary for our task. These images are from the paper Masculine Encoders, are scalable visual learners, and are depict fruits. So what about Earth observation images? Earth observation imagery is quite different and shows unique characteristics compared to natural images. It has multi-scale scenes from small objects like tree crowns to entire landscapes. It has no clear background. Every pixel contains significant information. And also, it has high spatiotemporal variability due to seasons, climate, and geography. So why remote sensing is so redundant? Because it has large spatial coverage. A single image can cover hundreds of square kilometers, often including many repetitive or similar regions. We have repetitive patterns over space and time. And the last one, data comes from a wide range of sensors. Each one introduces its own level of redundancy. Let's go back to the paper, Masculine Encoders as Scalable Vision Learners. Masculine Encoders are a self-supervised framework where an encoder learns representations by reconstructing an image from just a few visible patches. Even with 5, the impressive is that even with 5 or for 15% of the image, we can reconstruct the large portion of the image quite well. So a large portion of the input can be redundant, or at least not essential for learning useful representations. How can we apply a similar idea in Earth observation? This drives us to our key questions. Given the existence of redundancy in remote sensing, how can we exploit it instead of ignoring it? What happens when we eliminate redundancy? And how does this affect model performance, especially across different downstream tasks? Our proposition is that Earth observation imagery carries inherent redundancy that may be proven to exist and masked out to focus on information-rich regions. Our key hypothesis is that by quantifying and exploiting this redundancy in Earth observation imagery, we can understand the domain better and therefore unlock more robust and scalable Earth observation foundation models. Let's go to our proposed approach. An overview of this is that we want to investigate two tasks: multi-label classification and image segmentation. For each task, we design a specific architecture that integrates redundancy-aware mechanisms. For classification, we use RVIT vision transformer, which incorporates patch masking into its learning process. For segmentation task, we adapt the wrappernet backbone, a transformer compatible ARPANET variant to handle spatial redundancy more effectively. Let's go to our first backbone, which is redundancy-aware vision transformer. The idea behind of this is that we want to focus on information-rich patches. So we want to remove redundant information via masking. We have implemented 3 masking strategies. The first one, and our primary implementation to investigate what we want, is the dynamic one, based on the cosine similarity. We have computed cosine similarity between all pair of patches and kept only this below a specific threshold. We tried different numbers of thresholds. This leads to varying number of patches per samples. The second approach, it's a static one, and investigates the same thing, but gives us a better interpretation of our results. It's a top K% of the least similar patches, again based on cosine similarity. And the last one, it's we mask patches in a random way, just to have a baseline. So the second backbone is for segmentation task. Again, we use the same encoder, RVIT, and now we, in combination with an ARPANET architecture that extracts the level, the hierarchical level from information for the encoder and performs the segmentation tasks. Let's move forward to our evaluation framework. As we said, we have 2 tasks, 2 backbones, and what about data? We have 2 datasets per task to ensure the robustness of our analysis across domains and data distributions. Our aim isn't to maximize performance, but analyze how redundancy-aware training impacts learning and gain valuable insights for our domain. So, we have used BigEarthNet dataset and MLRSNet for classification tasks with macro multiple average precision, multi-label average precision, weighted multi-label F1 score, and multi-label F1 score macro as metrics, because these metrics are more common in literature for these datasets. And for the segmentation task, we used Woody and Flair dataset with these metrics. So we selected this dataset because it includes data at multiple spatial scales from very high resolution to lower resolution. So we can test how well our model handles different levels of detail. This is important because objects can appear very differently depending on the ground sampling distance and their size of granularity. Also, these datasets vary in spatial coverage from small, as we can see, from small areas to large, diverse regions. So we can evaluate generalization across different environments. And one other reason is that some of these datasets include different sensing modalities, such as RGB, multispectral or SAR, which help us test our model's ability to work with different types of input data. So overall, we have a strong and diverse benchmark to test both performance and robustness. This is an example of images that we modeled during training. This is an original image from the right one, from Bighall, and this, the left one, when we have masked the 65%, and a similar approach for MLRSnet, we have masked the 60%. So let's go to our preliminary results. Okay, as we can see in these diagrams, the performance maintained when patch matching ratio increases. We have the black dashed line, which is the baseline of our models, which is when the model sees all the input. And as we go left, the orange line, we have tested the model in less input, as we can see in the diagrams. We can see in many metrics the same trend, that even with 20 or 15%, the performance loss is minimal. Something similar to image segmentation result. So why this is important? This is important because we can unlock efficiency without sacrificing performance. We have robust performance under heavy masking. Minimal precision, accuracy, and F1 score loss up to 60% masking in all tasks, and in some cases up to 85% masking. This is a path to efficient large-scale models. By pruning redundant patches at the same level, significantly reduce compute and memory needs, making it feasible to train much larger transformers on Earth observation data. And also, we can focus on the most informative regions to drive our models toward learning richer, more generalized features, emphasizing quality of input over quantity. This is the last slide, so yeah. This is a work in progress, so our future steps is the deepened analysis of our preliminary findings to develop inside mask-driven masking strategies and validate across additional observation datasets, fine-tune segmentation tasks, quantity efficiency gains, systematically report memory footprint and training speed up under varying mask ratios. And also we want to explore some more research questions, like can we achieve comparable downstream performance when pre-training on smaller information-rich subjects of Earth observation data? And how does per-sample redundancy correlate with generalization across tasks, modalities, and geographies? This is my end of my presentation. Thank you very much. I'm happy to receive your questions.
Thank you, Papatafeiro. We have time for a short question.
Yeah, hi, thank you for the very nice presentations. Do you have any results on the other types of masking strategies that you presented?
Yeah. Yeah, the results are more or less similar in every type of masking, but I decided to present only this because it's a little bit difficult to directly relate the threshold with portion of information we masked out. So for the speed up of my presentation, I presented only these results, but it's more or less similar regarding how much information we masked out. I think.
Okay, thank you so much.
Thank you.
let's thank the speaker again. Do we have Yagis here? Great. Do we also have the presentation about the GeoVIT? Can you display it, please? Good. So Yagis is from the BTS labs, and he will talk about GeoVIT, a self-evolving foundation model for dynamic Earth observation through adaptive vision transformers.
Yeah.
Is yours.
Yes. Hello, everyone. I'm undergrad student in Kırıkkale University in Turkey, and this is my first presentation, actually. Like, this is my first conference and first presentation, so... Thank you so much. So I will talk about the challenges and our core innovations and our progressive learning process and our future distillation process and our data sets. And we employed actually like self-evolving foundation model architecture for Earth observation and novel temporal spatial progressive learning. And we developed a temporal consistency score metric. And our performance highlights 85% accuracy in real time, change detection, and 70% reduction in computational overhead, and 78% zero-shot transfer accuracy. So, like as you all of you know, like there's some challenges in dynamic Earth observation. For example, computational constraints or cross-scale integrations, or like static foundation models like can't dynamic Earth observation because they are too big. And Earth systems are changing at unprecedented rates. They require Earth observation systems that can adapt quickly and detect emerging patterns. So this is our core innovations, actually. We developed adaptive attention mechanism, dynamically adjust focus based on detection environmental changes and emerging patterns, and temporal aware architecture, and integrates time-based dependencies to model environment changes across varying time scales and efficient compute paradigms. And this allow us to like 70% reduction in computational overhead. So how does temporal spatial progressive learning works? This employs dynamic memory networks, progressive attention mechanisms, adaptive compression units. We first take satellite imagery input and then take temporal features, spatial features, and employ it in the dynamic memory. And then progressive attention and adaptive compression. We do that both, and then we have a self-evolving input. And this like eliminates the need for full modular training as new data arrives, and preserve performance on historical tasks while learning new patterns, and enable us to detect gradual environment change over time. And this is the cross-scale feature distillation. So we employ 10 million high resolution data sets and 30 million medium resolution, and take like daily updates, monthly series data sets. And at the end of the day, we have a like multi-resolution learning data sets for our model, and then we employ the knowledge distillation to like make it a smaller model. And we use Sentinel-2 dataset, Landsat-8 dataset, and weather station we take weather station data, we scrape them. And actually, I had a Google Cloud credit, so I used like $1,000 for 8 NVIDIA A100 GPU and 48 hours to train them. And in the model, we have like vision transformer backbone with like 12 layers and 12 heads. And we modified the self-attention with dynamic memory extensions. So these are our results. So in the baseline models, like we can offer a better interpretability and adaptability. And we developed, as I told you, like we developed a temporal consistency score, and like in baseline models, it's like 42, 0.42 for baseline models, but our model is like 0.75. And this is the GeoExplainer model in GeoVIT, actually. Like today, I see like a lot of good models. They were like very good, very big, and like they can do most of the things. But in GeoVIT, actually, we try to be like sustainable. we are like trying to be like smaller models, but actually when we developing smaller models, we want them to like interpret. We want to understand why we are taking these decisions. So this is like one of the good things in the Jovit. We have attention map, and we can see like what is like affecting our model, what features are important in the model, in the data, and we can see like what places are needs high attention, or what places not in high attention, low attention. And real-world applications, as you all know, like environmental monitoring, agricultural management, or like disaster management, it can be adapted anywhere. And this is our like conclusion. Self-evolving architecture is one of our key achievements. We develop temporal spatial integration and mostly interpretable AI. Thank you for listening to me.
So Yaris, you can stay there. Thanks for the presentation. So you can also take your first question then. So what is the first question for Yaris?
Okay, I'm going to ask that. So the Geo Explainer, is that, can you go back, is that specific to Geo VIT, or it's a generic package for VIT? I didn't get that.
Like, think about this like a shop. Like, I developed this model and integrated. And like when we I also like plan to publish this paper as a full paper in the next week in archive. So like there will be a huge section about GeoExplainer. GeoExplainer is a model, not model, a module for like explaining, like shop for like geo, like you understand, like shop for actually Earth observation. Like you can understand like what's affecting the model, what's affecting like what is like most important and what's not most important. And maybe in the future, maybe you can like distill your data set. For example, if it's a feature is not important, you can you can't like you can miss it, then you can use the high impact ones.
Thank you.
All right, thank you again. And let's thank the speaker. So with this, we conclude the session. Both sessions actually on the latest advances in AI foundation models, and we go for the break, and we are back for 4:35 p.m. Thanks.
All right, so it is my pleasure to open this session on computational challenges in training, running large-scale foundation models. This is a very important topic, as we probably realized, as that foundation models are multidisciplinary domain where you need experts from different domains, including computation, computing, HPC, and several other aspects. So it's good to have a session in this workshop. My name is Gabriele Cavallaro, and I'm with the ULIC Research Center and the University of Iceland, and I'm here with Kumar from NASA, and we're very happy to have this set of speakers. So we will start with the first presentation, which is be done by Vito Remote Sensing from Cristina Bucco. And the title of the presentation is, What Does It Take to Deploy a Foundation Model in an Operational Context? The World Serial Presto Global Crop Mapping Case Study. Thank you very much. The stage is yours.
Thank you. All right, hello everyone. My name is Cristina Bucco, and I'm from Vito. I'm working in the ESA's World Serial project, and today I'm honored to present this joint work from World Serial and NASA Harvest teams. And I find it quite symbolic and delightful that here at this Esa-Nasa workshop, which is some sort of a organization-driven collaboration, I'm presenting this truly people-driven collaboration where two people from the project actually met at one of the events not far, much like this one. So there is that. Collaboration works. Keep that going. And let's get started. And before, let me introduce who we are and why that matters. We are a partnership between ESA's World Serial team at Vito, and there we have years, if not decades, of operational Earth observation experience, and NASA Harvest, who are pioneers in self-supervised remote sensing models. At Vito, we already have and maintain global pipelines processing billions of pixel time series, handling clouds, missing data, and multiple sensors. And we are, of course, as practitioners, excited every time a new foundation model comes out, but integrating them into our existing complex workflows, complete already with custom cloud masking and composites and preprocessing, is a real challenge. And foundation model developers, on the other hand, face the opposite issue. They prove their models on standard benchmarks, but they rarely see them in full production pipelines. And rebuilding our infrastructure and pipelines around each new foundation model is simply not practical and not feasible. And so instead, we asked ourselves, how can we harness foundation models with minimal disruption to existing pipelines? And today, I'll cover why practitioners like us care about foundation models, how we integrated Presto into World Serial, our general 4-step protocol, and key takeaways both for foundation model developers and operational teams. Let's begin by reviewing our two projects' backgrounds and how we actually came together. World Serial is an ESA-funded initiative and an extension of the previous project where we produced global cropland and serials pixel maps. In the second phase of the project, we have two goals. First one is global annual mapping at 10-meter resolution. We need to map temporary crop versus temporary cropland and non-cropland, and then 9 major crop types, all using monthly Sentinel-1 and 2 composites, Meteor and DEM data. The second goal of World Serial project is on-demand custom maps for any region or crop subset driven by user-supplied reference data. To achieve worldwide coverage, fast production, and user flexibility, we decided to switch the backbone in this second phase of the project to a foundation model. Because it promises the large-scale pre-training, promises great generalization, at least on paper and on benchmarks. It handles well, it is resilient basically to clouds and missing observations, and it also frees us from this brittle and hand-engineered indices and region-specific rules like manual feature engineering that we used in phase 1, which is also a good thing. And our foundation model of choice turned out to be Presto. And Presto is at the heart of our system. It is a transformer encoder trained with masked autoencoding on millions of unlabeled Sentinel-1 and 2 pixels, plus auxiliary inputs like DEM and Meteor data, which is already very much like what we used in phase 1, which we liked immediately. The claimed lightweightedness was a very important factor for us as well as the fact that Presto operates on a pixel level rather than on a patch level, but more on this later. Presto produces 128-dimensional embeddings that can either be frozen and fed into a downstream classifier or fine-tuned end-to-end, giving us both efficiency and flexibility for global and custom mapping tasks. Here is our existing World Serial flow and where Presto slots in. For the sake of time, I will not go into too many details, but just a few highlights here. At this user-facing side of World Serial, users are free to choose their area and time frame of interest and their own samples for training, or they can rely on what is publicly available in our existing database, which is already quite a lot. Then the extracted raw pixel time series get harmonized, cloud masked, composited, and windowed into a uniform format ready for modeling. And we send them to our fine-tuned Presto, getting a 128 feature vector for each 12-month pixel sequence. Those embeddings become the input to a lightweight downstream classifier. In our case, we offer users CAD-Boost, yielding custom models fine-tuned on user-specified labels. And finally, our team's favorite single generate map function, which orchestrates on-the-fly or batch inference through OpenEO and Copernicus data space to deliver regional on-demand maps. To make Presto play nicely with our operational data and needs, we applied 4 major tweaks. First one is self-supervised pre-adaptation. We ran an additional round of masked autoencoding on World Serial's own reference dataset, which aligns Presto's representations with our unique input distributions. like different cloud compositing, different DEM, and weather sources, etc. Then, to gracefully handle real-world gaps, we employ end-to-end masking during fine-tuning as well. And here we are inheriting from original Presto pre-training routine. And thus, our foundation model simply learns to ignore masked inputs without degrading the rest of its embedding. Then we introduce the temporal cues and augmentations, which you see here on the slide, we introduce this focus token to direct the attention to the important part of the season where label is actually located, because we have label for the whole 12-month time series, but it is obviously present at some, often can be present only at some portion of this time series. We also apply slight horizontal jittering of this focus token to also ensure some robustness to temporal misalignments and data sparsity. Finally, we decouple representation from classification. While we still can use end-to-end fine-tuning for a particular task, we provide users with a frozen encoder that serves as a feature extractor, fitting even CPU-only inference. And this dual option underpins both our global production and user customizable workflows. Here are our headline empirical results, both for, they compare conventional baselines to Presto-based approaches across both binary cropland detection and 9-class crop type mapping. In both tasks, Presto-based approaches demonstrate much better generalizability across all splits, both including spatial geographical holdout test and also temporal holdout test. But in Earth observation world, numbers are one thing, but it's always extremely important to look at your maps and to see if they make sense, if they look and feel nicely, which is sometimes quite hard to quantify. And to keep it clear, we concentrate on 3 cases. Belgium is our usual place for sanity check. It's a very straightforward region, and we always expect very good results here. Presto sharpens field edges and eliminates stray misclassifications, while also better matching ground truth crop colors. Argentina is a very different. Phenological signatures and sparse labels, and both options of Presto capture field footprints and the correct crop mix far more faithfully than other approaches. In this classic USA maize soybean region, we again see that Presto reduces salt and pepper noise and recovers the actual rectangular parcel shapes, both for simple cropland mask and for multi-class assignments like maize and soybeans. We do see and acknowledge that there is sometimes somewhat unexpected behavior between this additional SSL versus non-additional SSL, and we don't really know how to explain those yet. And hypotheses include that some domain shifts in pre-training data, label sparsity effects, and seasonal dynamics, and investigating these behaviors is a key next step. But the bottom line is the same. Even just fine-tuning, Presto reduces noise, sharpens parcels, and produces operationally useful maps across continents and cropping systems. And here is why Presto makes large-scale crop mapping practical. And here I come back to this, why it's important for us to use pixel time series instead of patch time series. Each Pixel's 12-month Sentinel-1, 2 plus auxiliary series cost only 38 million max, which is over 20-fold lower than patch-based models like ESA-ESRIN. And for us, we understand that incorporating spatial context around each pixel will reduce, obviously, salt and pepper noise, and it will result in probably better results in numbers and figures, but at 20 times more compute. It's just we are risking to miss not to hit our operational deadlines and compromise, in general, compromise the scalability of the project. Another interesting effect that we see is that we can actually pre-fine-tune Presto on all the detailed classes that we have, which in our case is 63. And while the end-to-end classifier in this case is not really the best one for any particular class, the resulting encoder is extremely useful. We see that these broad embeddings can then be mapped to any subset, specialized exotic crops, via lightweight downstream classifier and recover per class accuracy with minimal additional cost. This separation of representation and task-specific classification is what gives us both speed and flexibility. And now slightly expanding on this last thought from the previous slide, here is a chart where I deliberately removed all of details, but for those of you interested, there will be a link for a more detailed one. But the key message is here that we are comparing two downstream classifiers to an end-to-end fine-tuning. And what we need to pay attention to is first the shape of the chart. We see rather equal tails on both sides. Then the magnitude of y-axis, which means that performance differences are really very small, even if they exist, and the absence of clear winner between the two colors, which is another argument that the differences that we see here is rather a random one. Up for now, we've seen why Presto is such a good fit to World Serial Dual Mission, thanks to its efficiency, robustness, and flexible embeddings, and how it was practically integrated into the existing pipelines. And here is what we distilled our experience to: a generic 4-step protocol for foundation model adoption, which we followed and verified with our own experience. And so let's reiterate again. First, define your requirements, then make necessary adaptations, do the empirical testing, and finally, keep in mind deployment considerations. Before wrapping up, I'd like to share key lessons and best practices we have uncovered. First one is that foundation pre-training matters, which I think is preaching to a choir here. Everybody would probably agree to that. Then task-dependent SSL adaptation is a very interesting thing, but should be treated with caution. For us, we do see gains in some tests, but on some other tests, we see some sort of chaotic performance. Then pixel level efficiency can be really important for operational needs. Then decoupling representation and classification is also very important. Then, to conclude, I will not reiterate the bullet points here, but just looking ahead, I want to tease one more thing that which is quite experimental, but something that we're working within the same framework, within the same system and code base, basically. It's time-explicit prediction. On the right-hand side, you can see a few examples of such predictions, even though the data set that we used to train on contains labels only per one timestamp, and they are usually hard-coded to actually just a generic middle of the whatever agricultural season in a region. But still, look how nice and consistent these predictions, time-explicit predictions already are. Okay, with that, I'm concluding. Thank you, and happy to chat. Give a try to our World Serial system. It's a link on our GitHub, and feel free to try and produce your own maps. Thanks.
Thank you very much for the nice presentation. Open for questions. Okay, if not, I will maybe have a question. So in the slide, you were mentioning some adaptation highlights. Mm-hmm. So I was wondering if you could, explain more what you think is the main challenge adaptation that you have to make or compromise when you need to set up such a model for production or for a, for use case.
This is a very difficult question. What is the main trick to actually adapt? For us, we immediately chose Presto because it already pre-aligned somewhat to what we have in our operational pipelines, but we still needed to do quite some adaptations. I would say that from those steps that I listed here, the self-supervised pre-adaptation was an important step, which gets your foundation model acquainted to the concrete data inputs that you have available to you, not immediately what the model was pre-trained on. So this is a really important step. Well, actually, the end-to-end masking during fine-tuning was also important. At some point, we ended up also implementing our own masking for like in-season maskings, where we mask completely a whole second part of the season, which also is something important. Yeah.
Okay, perfect. Thank you very much. We have a question online first, but we need to hurry up.
Congratulations, it's fantastic work. The question is how much your embeddings affect your time scale? Because you're showing here your mapping scale, which is taking a year, and you're using embeddings of one size 128. How many of those reflect time? How many of those reflect other band coordinates? Because you say you're pixel-based, so some of those are time, some of those are band information.
I think this question brings us back to the discussions that we already heard in the room about the interpretability and understanding what is actually happening in the embeddings, what they are. This is something that we within the team like to do a lot to just visualize the embeddings that we get. And with full honesty, I cannot answer you which of the 128 embeddings that we get from fine-tuning Presto is responsible for time and which one is responsible for coordinates or whatever other inputs. I think this is a work in itself, a big chunk of work. Thank you.
Hey, I have a question. In your slide on computational efficiency, you were talking about generic 63 class embeddings. So I understand self-supervised embeddings, having a generic embedding and then fine-tuning from there.
Yes.
Can you elaborate on what it means to have class embeddings and 63 class embeddings and getting a downstream, fast downstream from there? And as an add-on to that, what it means to have multi-objective fine-tuning, generic multi-objective representation and fast fine-tuning from there as well, because it seems like you're going in that direction from this experiment anyway.
That's a rich question. Again, thank you. First of all, to explain a bit about the 63 class embeddings, the embeddings shape that we get in this case is the same as 128-dimensional embeddings that our foundation model produces. But the thing is that we indeed fine-tune for 63 classes that we have available in the data set, like even very small ones, even like very unbalanced setup. And so we end up with a quite weak fine-tuned, end-to-end fine-tuned model, which is not really particularly fine-tuned for any specific class, but it's really well, it can adapt when we use the embeddings and then train downstream classifier a detached one on these embeddings. Does it answer your question?
And the fine-tuned classifiers are part of the 63 classifiers?
Yeah, they should be, hopefully. We want, yeah, there are a lot of crop types, but we are really hoping that with 63 classes, we cover quite many of them, and they are super detailed. So hopefully, yes, you will be using a subset of those 63 classes.
Yeah, thank you.
Okay, thank you very much. We need to move on. Thanks again, the speaker. All right, so the next speaker will be Aziza Ibrayeva, and sorry about my pronunciation, and you will present integration of foundation models with up and downstream application and geospatial digital twins. The stage is yours. Thank you very much.
Thanks a lot. Hello, everyone. In a submarine 1,000 meters underwater, we tested AI models that run without any cloud server or even stable connection. Those same conditions, low bandwidth, full isolation, harsh environments, are exactly what satellites face in orbit every day. And yet, most satellite systems still rely on centralized processing, waiting for a brief contact window to send everything down. So the question we ask is, what if satellites could think for themselves and decide what data to send and when? I'm Aziza Ibrayeva. We have prepared together with David Aronchik this presentation, and today we will explore how foundation models can enhance geospatial digital twins and discuss the practical implications for Earth observation missions. Geospatial digital twins are digital replicas of physical environments and essential tools for NASA and ESA. They enable precise simulations crucial for predicting climate patterns, responding effectively to natural disasters, and improving logistics and military planning. Essentially, they help us make smarter, faster, and better informed decisions. As it was said today a few times already, we are now in the era of geospatial data explosion. The geospatial analytics market alone is forecasted to grow to reach over 226 billion by 2030, driven by exponential growth in satellite data, drone imagery, and billions of Internet of Things devices, generating real-time location-based information. Satellites generate far more data than they can downlink, often limited to just 10 to 20% of daily output. This makes onboard edge processing not a luxury, but a necessity for managing scale, ensuring timely decision-making, and filtering data before it is transmitted. However, there are significant practical limitations we must consider. Low Earth orbit satellites orbit approximately every 90 minutes, yet their connectivity to ground stations is extremely limited. They typically have only 8 to 12 minutes per pass and only 5 to 8 passes per day. So this means that realistically only about 10 to 20% of data they collect can be transmitted back to Earth each day. Also, we should consider that not every time the data that is collected is a good state to be processed and to be delivered to customers. So that limits even more. Traditional architectures rely on pushing all data to Earth, but that approach causes delays, drives up mission costs, and often means critical insights are missed in real time. We need to move analysis closer to where the data is generating, meaning on board. I have background in a SAR satellite manufacturing company, and from personal experience, I can say that because of the matter of our business, we could have saved much more lives if we at that time could deliver data faster than we delivered when I was working there. And to address these constraints, edge processing becomes essential. Edge processing means analyzing data directly where it's collected, in our case in space, allowing satellites to prioritize transmitting high-value insights rather than downlinking the raw data, and significantly improving efficiency and response time. In our approach, we use advanced AI foundation models like YOLO v5, optimized and deployed directly on devices using container technology. We rely on Bighall, an open source system capable of operating even without continuous connectivity, ensuring the important data gets processed and transmitted as soon as connectivity is restored. Deploying AI at the edge has notable advantages. It drastically reduces latency, enables real-time decisions within seconds. Bandwidth requirements are reduced by approximately 90%, ensuring only critical insights are transmitted. And it enhances data security because sensitive information remains within the satellite. Finally, it scales efficiently for larger satellite constellations. So we have conducted these tests on unmanned submarines for US Navy. Unfortunately, we can share only so much because of some confidential clause, but as much as we can share, I will present today and we will discuss. So the architecture we propose is decentralized, using containerized tasks that function independently on board on each submarine. Tasks are queued and executed locally, synchronizing essential data only when connectivity is available again. This design provides reliability without needing significant changes to existing mission architecture. To validate this approach, we have conducted extensive tests. To validate this approach, we have conducted extensive tests on submarine environments. Submarines share many operational characteristics with satellites, such as limited bandwidth, intermittent connectivity, and isolated operations. The successful use of Bighall technology in submarines demonstrates its potential viability for space missions. Bighall seamlessly integrates with existing infrastructure, capable of operating across multiple servers, IoT devices, and embedded systems. This versatility ensures efficient and streamlined data management, and crucial for real-world operations scenarios. Okay. In our analog test using submarine environments, results were highly promising. We achieved real-time inference within 5 seconds. Bandwidth consumption dropped dramatically by more than 90%. If I'm not mistaken, it was 96%. And crucially, we maintain near-perfect execution, reliability even during connectivity outages, and with queued tasks executed seamlessly upon reconnection. Moving forward, our next goal is to validate this approach in an orbital test campaign. We aim to rigorously benchmark our system in real space conditions, assessing latency, reliability, data management strategies. We invite collaboration from partners interested in supporting payload hosting and telemetry analysis. Our technology directly aligns with strategic objectives of NASA's Earth Science Technology Office and ESA's Future EOR initiatives, addressing critical priorities like onboard analytics, minimizing data downlinks requirements, and enhancing operational autonomy. By achieving these goals, we not only improve mission efficiency, but also significantly enhance security and responsiveness. What if the next generation of satellites could decide what to send before they even connect to Earth? We have shown that deploying foundational models at the edge using open tools like Bighall reduces bandwidth, boosts security, and moves us towards true onboard autonomy. If there is one thing I hope you remember from this presentation, it is this. These systems are ready to be tested in orbit, and we are actively looking for collaborations to make this leap together. Thanks a lot for your time. I look forward to your questions, and I welcome opportunities to refine and extend collaboration with NASA and ESA community. Thank you.
Thank you very much for a nice presentation. Do we have any question? Yes, there is one there.
My question is about the amount of energy overhead that comes with edge computing on board satellites. My assumption is that satellites need to be very energy efficient, So does it add a lot more energy consumption overhead to existing satellites, or?
It doesn't add too much of the extra energy consumption because this platform is very light, and you can run it even on a Raspberry Pi. So it doesn't takes too much of the energy from a device.
Right. Thank you.
Thank you.
Hi. What is the hardware that you're running YOLO v5? Because to take 5 seconds for inference on YOLO, it's a bit like very slow. Yeah, I don't know what is the size of the data that you're using, but like even in constrained hardware, you can get something like 30 milliseconds for one inference on YOLO 5 or 6.
Yes. Yeah, thanks a lot for this question. So this platform, this solution can be run on, it's very agnostic. So it can be run on Linux, for example. I'm not sure what did they use for the submarine case, but yeah, it is very agnostic. So it could be run also on Linux. Thanks.
Any other question? Okay, maybe I have a question. So in the future roadmap, you were mentioning that now you have objectives to do more benchmarking and more work on that. So is there enough for the community to support such activity, like data sets, benchmarks, and tools that can help the whole community to work together on such a topic?
You're asking whether it is enough, or?
Yes.
Well, we welcome any opportunity for collaboration at the moment, but we are looking for 3 steps roadmap. Basically, we want to first try and test it in laboratory on a satellite, on a payload. We are in negotiations with a few companies in Europe already that are providing, so basically what they do, they build payloads and then they sell it for to satellite operators. So we're planning to test it with them. After that, the next step would be, of course, to test it in orbit. Today we were talking a lot about, not a lot, but a few times it was mentioned that in the future there will be satellites, and it's in the process right now, when they can also communicate with each other. I went in March to such show in Washington, D.C., and satellite operators from Satcom, they were talking a lot about the need of building this solution when they, on every layer, satellites communicate with each other, meaning GEO, MEO, and LEO. So the next step, of course, would be to help them process data on edge as well.
Okay, thank you very much. Unless there is no other question, let's thanks again our speaker.
Thanks a lot.
And we will just move on with the next presentation from Michele Becchini. Is that correct?
From?
Michele?
Lorenzo.
Ah, okay, sorry. I made a mistake. So I'm Lorenzo.
Yes, it's mine. Hello, everyone. I hope that the presentations that you heard were nice, and I hope that you will find nice also mine. I am Lorenzo Beltrame. I am a PhD candidate at TU Munich, and I also work at the Austrian Institute of Technology. Today, I will be talking about the computationally efficient head-only fine-tuning for EO foundation models and how to benchmark things freely. This work is done in the context of the Saphir project, and it is founded by the National Agency in Austria. So, to give some context to this contribution, training things from scratch, usually it's not how we do things right now. We have foundation models that are run by someone, and we fine-tune them to our own applications. The point is that those foundation models started to become so large that even casual remote sensing practitioners are not able to run them on consumer-grade GPUs. And very often, HPC capabilities are required to get the models going and fine-tuning them. In this contribution, we will focus on the encoder-decoder architecture only, where we have a backbone getting the raw spatial features and the decoded getting refined segmentation features. Then a segmentor gets the segmentation masks out of that. We are purposefully ignoring any approach that includes SEM for two reasons. First of all, there are a lot of models out there, so we had to make choices. And second of all, we wanted a solution that even an entry-level practitioner in remote sensing could work with and apply. We can broadly divide foundation models into two large families: supervised computer vision models that then get fine-tuned on EO datasets, and self-supervised approaches that try to learn spatial features in them. Most of the current literatures do not differentiate on that. Everything is compared, models are used, and we believe that this is not fair, and they should be differentiated, and there should be a more nuanced understanding of that. So, to answer this question, how can a practitioner choose the most fitting model for their EO case efficiently? We propose two strategies. The first one is to freeze everything from the backbone down and focus on the raw spatial features. We would plug on top of it a fully convolutional head, one single convolution, and then we would learn some feature based on the spatial features, raw features that are extracted. In this case, the comparison between self-supervised and supervised methods would be fair, because we would be focusing on the spatial features only that get extracted, and not also on the interpretation operated by the decoded. In the second strategy, conversely, we want to test the frozen refined segmentation features. So we also include the segmentation head on top of the backbone. Notice that for the self-supervised methods, the strategy 2 and strategy 1 are the same. So they just have one single convolutional layer. To learn some parameters, we are learning we are adding a fully convolutional overhead before the segmentor. We chose to use a NeurIPS dataset. It's called LoveDA. It's quite a complex dataset. The best performing model right now has an intersection over union of 0.57. And it comprises rural and urban setting, so quite mixed. It is multi-scale and has inconsistent class distribution. It is only, though, geographically related to China at the moment. To see, first of all, the runtimes. We have two main gains. TOV is the only model of which that I benchmarked that presented some kind of runtimes. All the other models didn't. So one single epoch in TOV during the original pre-training took around 300 seconds to be completed, while when I fine-tuned it to our dataset, it was taking around 242 seconds, while fine-tuning it using our strategies, so keeping the head frozen, had significantly less computational saving time. Secondly, since the only tunable parameter in a convolutional head, given all the setting and the input that are acquired, is the number of channels that are considered, you only need to tune on one single hyperparameter instead of multiple, as a full fine-tuning on the new dataset would require. So we can see some results. There aren't too many models. We are working on expanding them, but everything needs to be adapted, imported to segmentation, which is the framework we decided to use. And if we consider the Spearman ranking between all the strategy 1 and strategy 2 MIUI against the fine-tuned version, we get some encouraging result. We have a monotonic dependence with a factor of 0.728 when we consider only the spatial features comparison. When we consider the more refined features, so the segmentation features, we get a slightly lower result. We were initially dubious about those results because they are not as conclusive as they may seem. So we divided the pre-trained models, the self-supervised models, and the fully supervised models. If we consider only the self-supervised methods, the Spearman ranking increases, even though the p-value is slightly above, but I guess that having 5 samples in total doesn't help either. But when we consider the supervised methods, we have perfect ranking. So instead of using the Spearman ranking, we wanted to get a more stringent metric, so we used the Pearson correlation. In doing so, we observed that when we are comparing the spatial features only, we get very good results. While if we consider the segmentation head on top, fully frozen, we have statistically invalid results. So we interpreted this, and I am very open to discussing this, as an indication that those supposedly said foundation models are slightly biased by the task they were trained on. So if you're feeding them to a difficult data set, these things start to arise, while only evaluating the spatial features with less bias from the way those features are aggregated leads to significantly better results. So to summarize, we have that if we consider all the models, we have somehow a monotonic dependence on the ranking between both strategies and the fine-tuned versions. But strategy 1, so only using spatial features, has higher MIOU. While if we divide by pre-training or training strategies, we observe that for supervised models, there is a strong predicting power using strategy 1 of the final fine-tuned versions. So a practitioner, instead of running several fine-tuning experiments of several models on his dataset, can first select a few models. How many is debatable, depends on the resources at his or her disposal. But those results are early, and we wanted to share with them. To get a more stringent statistical value out of these, we need to increase the number of experiments. Also, I repeat once again, the Spearman correlation index seems to show that the supervised models might be biased to the tasks they were fine-tuned on. So the practical impact is that it reduces the number of full hyperparameter selection done to fine-tune the models, because you are fine-tuning less models. And there is a good predictive power of the final performance once fine-tuned, only using the backbone. In future works, we are planning to expand these experiments, also including more datasets, more state-of-the-art networks that they require additional care when setting up, and including other tasks outside of segmentation. I wanted also to make an extra point, because when I was doing all those benchmarking experiments, replicating the results, a lot of implementations were not possibly be replicated. They couldn't be replicated. And I find this quite concerning, because if missing hyperparameters are missing, or for example, training parameters are missing, those results cannot be independently verified. So those are the resources of the models that I used. And thank you for your attention. If you want to connect, please write me an email. And if you want to see my other works, please look me up on Google Scholar. Thank you for your attention, and I'm waiting for some questions.
Thank you very much. Sorry for missing your name. So do we have any question? I think you made a nice stimulation in terms of topics and criticism. So I'm wondering if there is anyone who wants to react on what you just stated. Yes, please.
Thank you for your presentation. I was wondering, fine-tuning the task-specific head, does this open up a use case where embeddings can be pre-generated and saved, and so you could run this much later against the pre-generated embeddings and still get the performance?
Yes. Regarding these two things. First of all, storing the embeddings means that the practitioner needs how to deal with loading these embeddings and integrating those embeddings into their pipelines. And this is not often the case because in many remote sensing small labs, maybe you don't have like those capabilities. Or for your specific remote sensing applications, for example, in my own research, like wind throw segmentation in forest, there aren't really good even data sets for doing pixel level segmentation. And actually, like we will be probably publishing one now. So given this, let's say, mismatch between all the possible downstream applications that can be applied and the current capabilities of generating those embeddings in a centralized and reusable ways, I would say that we should first get into having fully standardized and replicable results using our foundation models. And then we could focus on also generating embeddings and scaling up the approaches.
Thank you.
I don't know if I answered to your question.
Yeah, I can talk to you later.
Okay, sure.
Any more questions? Okay, if it's not the case, let's thanks again our speaker.
Thank you, Gabriel. For the next 3 presentations, I will take over the responsibility of organizing. My name is Muthukumaran. Some of you may know me as Kumar. I work as a computer scientist for University of Alabama in Huntsville, and I work for a NASA Impact project. My focus is on large language models and specifically how we can effectively and safely use them for science and scientific research. And you'll know more about that tomorrow. So if you're joining tomorrow, we'll talk more. For the presentation, next presentation is about enhancing deployable models for onboard applications through multimodal remote sensing foundation models. It will be given by Michele Becchini. I hope I'm not pronouncing your name incorrectly. So please go ahead.
It was good. Okay, so good afternoon. My name is Michele Becchini, and today I will show you how in ICO we use foundation model for our onboard application. But before looking at that, just a quick introduction to what is ICO. We are a small startup based in Turin, and our main commitment is in developing and enhancing the autonomy of spacecraft, providing both onboard softwares and also on-ground models for enhance the predictions and the data usage on ground itself. In particular, I came from the ClearClaw and ClearCharts application, where we use passive and active payloads to perform directly onboard any space analysis of the data acquired, trying to enhance and deliver better information on ground, so doing a part of the pre-processing directly on board. So here we want to develop cutting-edge AI-based solutions, trying to eliminate delays and inefficiencies. So basically, our main objective is to provide scalable and adaptable architectures tailored to your needs and to, most importantly, to your hardware and onboard data processing pipeline. So this is what we do in general, let's say. More in detail, we have some R&D activities to enhance our products. Here I will show you one of those that is particularly related to the remote sensing foundation model that obviously, since you are here, you may know that they are the new frontier for AI-powered Earth observation. They have a lot of good points and point of strength, but they also have the big issue that they have a very high computational cost, so they are quite difficult to be deployed on board. So our idea is to leverage the already available remote sensing foundation model to enhance our product and our models that are deployable on board, leveraging knowledge distillation techniques. So this is our objective. In order to do that, during this R&D activity, we developed an internal tool to do knowledge distillation. This tool has been thought to be easy to use and to streamline the process of doing knowledge distillation experiments. In fact, it requires a minimum coding effort from the user. As you can see from the scheme, it is basically split into portions. The upper one is where the user actually needs to do things. In practice, it just needs to define a YAM file, that is the configuration file, and a very, very simple main script that just calls the main function from the tool. In the backend, there is the tool that do all the work for you. I will go a bit into the detail later. The main points of this tool is that it is fully compliant with PyTorch, so it should be very easy to use. And further, it relies on several third-party packages to optimize the efficiency. Further, you can rely on built-in modules, but also there is the possibility to plug in customizations and so going more into the detail of each component, relying still on this package. So basically, it has been built to be modular, adaptable, and most importantly, maintainable. Further, there is also a quite huge library of available built-in distillation, so it is quite easy to experiment with most of them. So as I was saying, the key is the configuration file that you need to define for each experiment, and that controls everything. In particular, it controls also the building of the model. And through it, you can define if you need to attach or if you need to, let's say, extract features, you need to attach layers, and so on. In the backend, there is the trainer class, that is the main class of the package that validates the configuration file that you give and builds all the models, so the student and the teacher or the teachers, it depends. Wrap the model, attach hooks that maintain the added layer trainable, that is the key for the knowledge distillation, and so on. Then it outputs all the log, the final model exported, and so on. So this is our tool, and we use it for our experiments. Here, I provide you an overview of one of the benchmark tests that we did. In particular, here, the scenario is the distillation of a remote sensing model into a very small UNet MobileNet V2 model. The task here is the active file segmentation that in theory is not a very difficult task if you have the SWIR bands, because as you can see, basically you also can avoid using AI. But here in that case, we are constrained to do not use the SWIR bands, so the task is by far more complex. Here I just reported some information of the dataset that is a Sentinel-2 based dataset that is freely publicly available online. And we use, as I said, the UNet MobileNet V2 model for the downstream task, and we consider the F1 score, the intersection of a union, and the area under the receiver operating curve as main metrics. We also have a single evaluation matrix that is given by the geometric mean of these three metrics to streamline and ease the evaluation. First of all, I show you here very briefly the results of the original model, so the UNet-based model on our test set after the training without distillation. So this is our baseline. As you can see, the model is very small because it's 2.3 million parameters, and after the training, it achieved pretty good results, but not satisfactory for us. in particular from the metrics and from the segmentation maps, you can see that there are several false positive, and further also the masks are not so sharp and not so similar to the ground truth that you can see in the third column. So basically these are the issues of the models, and we want to enhance it through distillation. Here we have the outcomes of the remote sensing foundation model that we use. In particular, we used ANISAT, and luckily they presented the ANISAT model this morning, so I don't waste so much time on that. This transformer-based foundation model has been taken from their Git repo, and we also use their pre-trained weight. In theory, we should have used just a simple linear probing to fine-tune the model for our task, but in fact, since the model expects to receive all the Sentinel-2 bands, the outcomes were very, very bad, since actually we do not have the SWIR band. So we did a fine-tuning by providing the SWIR channel max, so all equal to 0, so without providing any information from them. This model is quite huge, it is 95 million parameters, so we expected to have better performances. And in fact, after the fine-tuning phases, we achieved very high score on all the metrics. In particular, they are by far higher than our UNet MobileNet model. And further, as you can see, the maps are very, very precise. This brings to conclusion from this. So the first one is that it's actually possible to extract highly accurate segmentation mask for active fires without the SWIR channels. And the other one is that since the scores are so high, it is ANISAT is a good candidate for the distillation into our model. Moving to the strategy that we use, here I just reported a comparison of 3 strategies that we consider for the feature-based distillation. In particular, I want you to focus on the batch size dependency, and you can see that the attention-based is the only one that does not depend on the batch size, while the other 2, even if they are more advanced distillation strategy, are strongly dependent from the batch size. And unfortunately, since we have some constraints from the computational capacity that we have, we must use small batch sizes. And so for this reason, we selected the attention-based transfer. Despite that, we forecast to find some ways to use to test also the others. We have some preliminary tests that were not satisfactory, but we want to go more in depth, and also possibly combine them since they are some way complementary. So selected this strategy for the feature-based part. Here I show you the full distillation pipeline. As you can see, we extract the attention map from the ANISAT backbone that has been freezed, and from the decoder output of the UNet MobileNet V2 encoder-decoder architecture. Then, to try to achieve very accurate mask, we also use a standard KL divergence loss for the logits provided as output by the 2 segmentation heads, and further the standard task losses that are the cross entropy and the dice score. The idea behind this scheme is that in the early training phase, the attention-based loss should drive the learning of our CNN to be more focused on the most important part of the images, since it should rely on the broader context driver attention of the ANISAT model. Then, in the later training phase, the KL divergence and also the task losses became predominant, and so they should, at this point, increase the accuracy of the segmentation map. This was our idea, and in fact, here I show you the results of the distillation experiments. And as you can see, the results are by far better than our previous model without distillation. In particular, the masks are very sharp, and there are no more a lot of false positives around. This can be seen also from the scores that strongly improve. Here you have the actual score and the percentage improvement with respect to the case without distillation. So basically, this led us to a highly performant model that is still deployable on board. So in practice, using our knowledge distillation tool and our knowledge distillation strategies allow us to distill any SAT into a very small and easy to deploy model, and having a strong improvement of all the metrics. So to wrap up everything, here I also show you a comparison between the mask predicted from the same images by the model with and without the distillation, where you can actually see the improvement. Here, we just wanted to demonstrate that remote sensing foundation model are a very, very good tool for on-ground application, but they can also be used to enhance the performances of small CNNs that are still deployable on board. And this is made possible by knowledge distillation. Our knowledge distillation tool is a valuable tool, proved to be a valuable tool, and it is effective in streamlining and easing the distillation processes, allowing us to do several experiments in a very short amount of time. You just need to change 2 lines in the configuration file, and basically that's it. Actually, we also get that the attention transfer, that is a pretty old, but in that case, pretty effective techniques, is still valuable, but we also want to deepen this with some ideas that we have for the future. And most importantly, here we show just the distillation between any SAT and a simple UNet mobile net V2 model, but in fact, the same strategy can be applied to any couple of foundation models and CNN models, but in fact also between foundation model or several foundation models. This brings us to the ideas that we have for the future. In fact, we want to test and implement more distillation strategies, and we also try to find a way to develop dedicated distillation strategies that allow us to bring the knowledge from transformer-based architecture to convolutional-based architectures. And further, we also want to try distilling the knowledge from multiple resource foundation model into a single student to try identifying which are the best couple and which are the best things to distill from each model. That could be also a way to have an overlook on what the foundation model is doing, so try to, let's say, opening the black box of foundation models. And lastly, as we have seen in some presentation today, we also try to transfer the sensor agnostic and multimodality natures of foundation models into our deployable CNNs. So this concludes my presentation. We are open to continue working on this topic, and so find way to collaborate with other institutions. So if you think, if you want, we can get in touch and see what we can do together. So thank you for your attention, and if you have any question, feel free to ask.
Thank you very much for the presentation. Do we have any questions?
Hi. So thanks a lot for the presentation. So one question I have is, these foundational models are obviously pre-trained on very heavily processed data that is L1C, L2A, data that is usually not available on board the spacecraft or the satellite. So there is this gap between what you capture, which is raw data, and what the input of your model expects. So in this line of work of adapting these foundational models on deployment, do you have anything in that line to adapt this raw data to the expected input of these models?
Well, actually, the model that we used, the ANISAT model, was pre-trained on GeoPlex datasets, but actually, as the Astrux says this morning, This is a composite data set made by several sensors and time series and so on. Actually, we do not have those information on board, but what we want to leverage in those experiments is exactly this type of knowledge that on board we don't have. So in our data sets for the onboard application, we do not have this knowledge, but this knowledge exists actually. So we want we tried, and I hope we succeeded in getting this knowledge and bring this knowledge into our model. So yeah, basically we do not have the knowledge, but the knowledge exists, so we try to exploit it.
Thank you.
Thank you very much. Any other question? Maybe I have a question. So in terms of, I'm going to talk in terms of compute and data efficiency, specifically with respect to traditional fine-tuning of foundation models versus knowledge distillation. I'm trying to understand what the difference is in terms of compute, because even in the fine-tuning, we are starting from a learned semi-supervised model and adapting it using a smaller set of weights for a fine-tuning head. Versus here, we are utilizing a larger model with higher parameters. And distillation happens on a smaller model where we are task-specific fine-tuning, of a task-specific distillation process happens. And there is a fixed parameters for both of these models in terms of compute and in terms of data as well, fixed data where you're adapting for the specific tasks. So can you comment on fine-tuning versus knowledge distillation in terms of computation and data efficiency?
Okay, yeah. Just go back to the scheme. So basically, yeah, fine-tuning the foundation model is quite heavy, and it's take quite a long time. But in fact, you can do that just once that you have your downstream application. You select a data set for to transfer the knowledge. Here we use just a small data set based on Sentinel-2 images. And once that you have done this, you basically the most time and computational consuming part is done, because then in the distillation part, the model here, the foundation model is freezed. So even if you plug some feature alignment layer or something like that, basically you just need to perform inference of the foundation model. So the most complex part regarding the foundation model has been already done. So yeah, this is basically the trade-off. Concerning the overhead between the distillation and the training from scratch of our UNet mobile net v2 model, clearly the overhead is quite heavy because the inference of the foundation model still takes some time. In that case, it is in the order of something like 0.5 seconds for a batch of 10 images. So it is not negligible, of course. But overall, concerning the gradients that you need to backpropagate and so on, is exactly the same.
Thank you. Any other questions? Okay. Thank you very much.
Thank you.
I have a question. Oh, one last super request.
Yeah.
Have you considered applying also other kind of strategy and like quantization, pruning, and benchmark also that ones?
You mean for the downstream model?
Yeah.
Yeah, we are considering them. In fact, there is also a branch of the research that is completely dedicated to quantization-aware distillation and so on. We are exploiting them. We are still working on that, actually. But yeah, we consider them.
Thank you very much.
Thank you.
The next presentation is on designing compact multimodal change detection models for onboard Earth observation by Arjit Mukherjee.
So good evening, everyone. So I work in TCS Research, the research stream of Tata Consultancy Services in India. And let me make two very candid confessions upfront. This team that you are seeing there, we are not experts in foundation model. Rather, as the group name defines, we have an expertise in embedded devices, intelligent systems. We try to create optimized models for tiny edge devices. Devices like your smartwatch. Even we create optimized medtech models for your pacemakers. So that's the kind of devices we focus on. The stage was nicely set for the need for computation on board, especially edge devices. So I'm not going into the details of this, but the concept of on-board varies from vertical to vertical, I mean from application to application. So in case of medtech applications, the motivation for onboard is privacy. For satellites, it's more like energy constraints and data transfer bottleneck. So we have already discussed about these things. So in case of small sats, there are models, foundation models that might work. So things like segmentation, anything model, SAM, SAT-MACE, SkySense, these are all there. But the size of the model, the cost of training, all these things are prohibitive. They are not really ready for onboard computing. So again, going back to our medtech background, the embedded devices background, we actually tried, we started working on this with a background on creating something very efficient for medtech applications. So this is just an example. Fusion of CT and MRI for embedded devices that appear in hospital infrastructure. The motivation was, in this case, again, privacy. But the need was CT, the CT scans, they focus on the hard tissues, the bone and structures, very high resolution definition of bone structures, and MRI is for soft tissues. Now, if you merge these two, if you can fuse the segmentation mask for these two, you might get a better diagnostic. So this requirement came from healthcare companies, that can you do these kind of things on an embedded device. Now, there are obviously state-of-the-art models like UNet, like dual stream V4, which are capable of doing these things, but they are again highly, memory consuming and large, computationally very intensive with high number of parameters. For example, UNet has around 30 million parameters, so you cannot put them on those kind of devices. Now again, CT and MRI, since they are very complementary in nature, when you have to fuse them, their intensity distribution, imaging properties, they are different, but if you can fuse them together, they enrich the contextual understanding. So this distribution difference becomes a challenge in case of these devices. So we created something novel called YNet. In terms of nomenclature, it's similar to UNet, but it's a completely different architecture. YNet, that has achieved around 93.5% IOU with only 0.34 million parameters. That is less than 1/100th of 30 million parameters. So I'll just give a briefly how YNet works. So in case of CT and MRI, so let's say you have two different sets of images, the multimodal medical input CT, and you have the MRI input as well. We create a cross-attention mechanism using a joint modality encoder block. Now, this joint modality encoder block is a shared one that is modality agnostic, or not dependent on the modality, but it can beautifully extract the complementary features of the two modalities of input data. Then we use a bottleneck layer with squeeze and excitation blocks and ASPP pooling that actually transmits the semantically contextual information to the dense layers. And then we create two different encoders for the different type of input modalities. So one decoder for CT, one decoder for MRI, which work on the multi-scaled fuse features, and we send the spatial features from the shared encoder. And then we can get a fused image segmentation mask for CT and MRI together. And that worked beautifully for medtech datasets. So we tried on chaos dataset with an average IOU of 93.5 for CT, 89.6 for MRI, and CT-MRI jointly 92.3, which actually surpasses the state-of-the-art DSV4 and UNet. So this worked. Now, from our embedded background, once we started getting the requirements from the satellite people, the people who work on remote sensing, we started thinking, okay, can we use this backbone, the same YNet backbone, for a different kind of task? Now, the problem here is YNet itself is a small model. If you want to train, if you want to use the knowledge distillation method from, say, for example, teacher models like SATMAI, if you want to use the distillation from SATMAI to YNet, it might work, but there are challenges like the contrastive distillation that is costly. You have to use large batches. There are specialized architectures. There are solutions in some cases, but the problem is the teacher size itself is much, much larger than the student size. YNet is very small, whereas SAT4MAI is a large model. Now, when this happens, the teacher size is very much larger than the student size. The representations do not match. And these representations are not necessarily always images, so you cannot resize, you cannot do interpolations. So there is a problem in mapping those things. What we did was, we used the SATMAI teacher as encoder, but we introduced a new layer. You see that green thing over there? We introduced a new layer. We froze the rest of the SATMAI teacher architecture, and we trained only that new layer, which can be done very fast using the original training mechanism. And then we use this teacher model, which has the representation dimension same as the student representation dimension. We use the same model to distill the knowledge from the teacher to the student. And we applied this thing on CLIP, and we achieved fairly good amount of result on CLIP using different types, different modalities like task-specific distillation, two-step distillation with CLIP. But our distillation gave, this one actually on the right-hand side, gave pretty much good result, comparable results compared to all other mechanisms. So that's when we started adapting this YNet architecture to satellite change detection. So again, we have a shared encoder with cross-attention mechanism for RGB and NIR datasets. We have modality-specific decoders for RGB and NIR. And we introduced a consistency-enforced bottleneck that aligns the decoder outputs before fusion. And this is the mathematical core of the whole system. Again, keeping the backbone of YNet exactly as it was before for the medtech experiments. So we have RGB image input, we have NIR image input, and we have this shared joint encoder. We have a similar kind of bottleneck layer. And from there, we get an RGB decoder and an NIR decoder, the dual decoder architecture. So you see the backbone is same as YNet. Additionally here, we have the ground truth for NIR and RGB. And then we do a representation learning by DEL to get the vector embeddings from each of this and do a cosine similarity operation. And finally, we arrive at the change detection. So overall, these are the differences. So on the right-hand side, you see that within each box, the right-hand one is actually what we did for YNet in medtech. And sorry, the left-hand one is what we did for YNet in medtech, and the right-hand one is how YNet was adapted to satellite representations. And overall, in a summary, so we have we still have the dual modality encoding. We still have the distillation with SAT4MAI. We have a mathematical loss design based on BC, DICE, and some other things. And there are deployment challenges, of course. I'll come to that later on, especially the timestamp thing. And there are future enhancements that we have planned. Now, this is an experimental experimental result. This is still an ongoing work. So I do not have detailed results as others, but this is some qualitative evaluation that we have done recently. So on the left-hand side, you see an image that's the ground truth image of the region where I stay, actually. That region, in every rainy season, it gets flooded. And this is a ground truth image from September 2024. That is 17 September 2024. After there was a deep depression in the Bay of Bengal, and the two dams, Maithon and Panchet, released around 250,000 cusecs of water from each of the dams. Now, the top one here on the right-hand side, that's the change detection based on pre-RGB and post-RGB analysis. And the one in the bottom, that gives you the change detection for pre-RGB, NIR, and post-RGB, based on YNet. Now, see, when compared to the ground truth, the precision in the last one, the lowermost one, is much better when we compare it with the top one, which is just based on RGB images. So YNet actually worked. And we found a strong 91.7% MIOU on ERA dataset. And these two images were also from Sentinel dataset. So to summarize, we have effectively used RGB and NIR fusions using a backbone of network that was designed for a constrained medtech device successfully in a constrained satellite environment, which is lightweight and adaptable. However, there are room for improvements, and we want to extend this to multi-temporal data sets, explore transformer and enhanced backbones. And another thing I want to mention is this. In case of medtech, we really don't care about the temporal differences, because a person's disease doesn't change in 2 hours. But here we have to consider the temporal differences, which is not there yet. That is one of the additional things that we want to bring in. And we believe that YNet gives you the exact fitment for change detection mechanisms when you have multimodality data sets. Normally, you won't require that similar kind of backbone if you are using multi-scale, what is it called? Anyway, so normal satellite images, you won't require that. If you are using two different modalities, then YNet matches the exact scenario here. And one last thing, somebody asked about the energy constraints on satellites, right? So this is one option that you can use small devices. This one was tested on a RPi-3 board. So these boards, by default, consume very little amount of energy. At the same time, we are also working on something called neuromorphic systems, neuromorphic computing systems, which are designed to take 100 to 1,000 times less energy compared to standard computational systems. Now, all these edge devices and cloud devices we talk about are von Neumann systems. Neuromorphic systems are non-von Neumann. That is the next step that we want to take up in this case. So that's all. Thank you.
Thank you for the presentation. Do we have any questions?
I have a question. Are there any kind of problems related to registration of the vectors when you compare for change detection?
Sorry.
I mean, if they don't cover exactly the same area on the ground.
Yeah, that's the spatial problem. So one thing that we did in case of the medtech thing, and that exactly matches with the satellite as well. You are taking the images of CT and MRI on different devices, right? So there is high chance of spatial differences there. So YNet takes care of that thing. And here also we have seen that the spatial differences doesn't really matter. YNet can manage to take care of that. The problem will come if there are temporal differences. We still don't know how that's going to end up, but we hope that we'll be able to work out something.
Right. One final question before we move on. Can you talk about the footprint of this model on an RPi-3?
2.2 MB.
Okay. Thank you. Okay, the final presentation for this session is going to be on PySatNet, and it's a deployable foundation model for onboard AI on PySat-2. The talk will be given by Carlos Collado Capel. And yeah, please go ahead.
Good afternoon, everyone. I'm Carlos Collado. I'm a master's student at EPFL, and I'm going to present FISAT-NET, a deployable AI foundation model for onboard processing of FISAT-2. That is the project I worked on during my internship at ESA Lab earlier this year. The motivation for this work can be divided into three main pillars: foundation models, onboard AI, and why do we want to use foundation models onboard AI. Due to the focus of this workshop, I'm going to skip the first one and talk only about the second two. So with respect to why do we want to use onboard AI, there are different reasons for this. First of all, it's very interesting for low latency applications such as disaster response in earthquakes or wildfires, where they help us to achieve lower response times. Also, there are bandwidth limitations in sending data back to Earth, and with onboard AI, we can do the processing directly on the satellite and only downlink to Earth the compressed results and the insights. Both of these are even more relevant for CubeSat constellations, which are usually deployed in constellations, so they can achieve lower revisit rates, which is important for low latency applications. And also because they are smaller satellites, they have more strict bandwidth limitations. In this work, we are going to focus on FISAT-2, that is a CubeSat launched by ESA and OpenCosmos in August of 2024, which with a multispectral imager and which hosts 6 AI applications. With respect to foundation models for onboard AI, it may sound a little bit counterintuitive at first, because foundation models on one hand are like these very big models, while for onboard AI you would want very small models due to the computational constraints. However, there are several advantages for this. First of all, you can have a unique backbone, so if you want to deploy onboard several applications, you can have a big unique encoder and then several small heads, making model size efficient when several applications are deployed. And also in the onboard community, there is also the interest to uplink new models onboard the satellite. So if you use a foundation model as a unique backbone, you can have this fixed big encoder, and then you only need to uplink new very lightweight heads if you want new applications or update existing ones. Also, there is an interest because of the few data sets, because of course for new missions you're not going to have data acquired by the satellites yet because they have not been launched. So foundation models are useful because they can be adapted better to different sensors. And also because if you have data, it will probably still be unlabeled. So with foundation models, you can exploit this unlabeled data via self-supervised learning. And I'm going to talk a bit about the challenges for onboard AI deployment and specific for FISAT-2. First of all, the VPU running on FISAT-2 is Myriad-2, which was discontinued in 2020, so it's a bit outdated. So models must be deployed on OpenVINO 2020.3, which has no support for a lot of different layers. For example, for upsampling layers, they had to be implemented manually, or most importantly, no support for dynamic access, so transformer models or attention-centric architectures cannot be used. Also, it has a maximum inference memory of 512 megabytes and no support for floating point precision of 32. Also, as I said previously, there's a limitation on the data, as there are no data for new missions. However, for FISAT-2, they developed a simulator which takes as input Sentinel-2 L1C, and it is also the simulator we are going to use in this project. Here you can see a diagram of the simulator, but I'm not going to spend time talking about it. And finally, of course, there are other constraints such as energy or latency of these models. So we can summarize the contributions of this work in 4. First, FISAT pre-trained, that is a 500 gigabyte dataset of simulated FISAT-2 data. Onboard EO-Bench, that is a benchmark of 300 gigabytes of diverse tasks and tasks relevant to onboard AI for FISAT-2. Also FISAT-NET, a deployable foundation model that achieves state-of-the-art performance on FISAT-2. And finally, an analysis on the limitations and performance of foundation models if deployed on FISAT-2. First of all, with respect to the dataset creation, Even though FISA2 imagery exists, it's still not sufficient to create a whole pre-training dataset. So we're going to continue using the simulator that already 2 applications on board FISA2 use, and construct a global dataset of 500,000 patches of 256 times 256, using major TOM as the input in L1C. And we are also going to have in this pre-training dataset 2 supervised signals, coordinate encoding, and climate labels based on the Köppen climate classes. With respect to the benchmark on board EO-Bench, we can further subdivide it into 2 subsets. Filiosat subset that is derived from FilioBench, and it focuses on segmentation tasks, and it uses a Sentinel-2 L2A. So we are going to extract the equivalent Sentinel-2 L1C from this dataset and be able to convert it to FISA2 using the simulator. Also, we include the LLL-SAT subset that is specific to tasks that are relevant directly to onboard AI, such as methane and wildfire detection. But however, the benchmarking on this subset is still in progress. With respect to the dataset preprocessing, just a short comment, we do the normal standardization as always, but we include a square root before the standardization to be able to solve the long tail distribution that is seen in the FISA2 data and favoring more stable gradients and faster pre-training. With respect to the FISATnet model architecture, as a reminder, attention-centric architectures cannot be run on Myriad 2 and therefore on FISA2. So we focus the analysis on CNN-based architectures. And as we can see here, the most relevant CNN-based foundation models are based on ResNet 50, which excel at classification, but not so much at segmentation tasks. So therefore, as segmentation tasks are more important for onboard AI, we will use a unit backbone for this foundation model. FilioBench actually already introduced 2 pre-trained units, which achieve the state-of-the-art performance over foundation models on the Sentinel-2 data for segmentation tasks. So we're going to implement a similar architecture to GeoAware for FISATnet. Here you can see an image on the specific architecture of FISATnet, which uses a multitask pre-training with mass reconstruction as self-supervised learning, but also 2 auxiliary tasks, climate classification and geolocation. And we pre-train for 100 epochs on 6 GPUs. We're going to benchmark on the Filio subset of the onboard EO-Bench, which has tasks for land cover segmentation, land cover classification, building density regression, and row density regression. For the land cover tasks, we will use the micro F1 score as the performance metric, and for the regression tasks, the mean squared error. And we will compare FISATnet to the CNN-based models that I talked about previously, also to the units presented in FilioBench, and also about a few VIT-based foundation models. However, as VIT foundation models are non-deployable, we will not focus so much on their performance. And also, as a comment, the other foundation models are only potentially deployable because some layers would still have to be adapted to be able to run on FISAT2. So only FISATnet is the only truly deployable foundation model here. And we will use a common CNN decoder as you see in the FilioBench benchmark. And for the land cover classification task, we will use simple linear probing. We will do n-shot performance to account for the scarcity of datasets of FISAT2. And we will evaluate both freezing the encoder and doing full fine-tuning. We can see that for land cover segmentation, FISATnet outperforms all the other models, and same is true for land cover classification, building density regression, and row density regression. So we can see that FISATnet outperforms in every scenario, and we can see the same results here in a table where we see that FISATnet for the n-shot of 5,000 outperforms all the other models. We can see also here the outputs of each model for a sample image, where we see that the ResNet-based foundation models such as DINO or GA-SSL as they are based on ResNet, they achieve worse performance for segmentation tasks. We can especially see this in the building density regression and road density regression, while FISATNet more closely approaches the label. We can see this also for other examples. And finally, about a comment on some constraints that we can see is that even though the memory required by units is similar to the ResNets, they have a much higher floating point operation requirement. So as future work, it should be to optimize these units for onboard deployment in terms of latency and energy requirements. And now I'm going to finally present just a few more future work directions. So for example, foundation model compression techniques, that is my current research focus right now at my university. Also the analysis of latency and power of foundation models. However, as FISATNet is able to run on Myriad 2, we would expect that it's low enough. What FISAT2 product is best to use? In this work, we use FISAT2 L1C product, but FISAT2 also includes L1A and L1B products, so it would be interesting to study their performance. Quantization techniques for OpenVINO. Currently, we are using post-training quantization, but other techniques could be explored. Generalization across satellites, because we pre-train FISATNet on FISAT2 data, but it could be interesting to pre-train on other onboard missions. And finally, and probably most interesting, to have onboard deployability in mind when designing new foundation models. So this will be the end of my presentation. Thank you all so much. I'm looking forward to your questions.
Okay, thank you very much. Do we have any questions for him? Okay. Maybe I have a question. So you mentioned deployability, and for the FISATNet, that's with respect to the Myriad chip.
Yeah.
What other considerations are there out in the literature, and what it means to be deployable?
So I would say that the main deployability issues with Myriad 2 are that a lot of the layers are not possible to be deployed because it relies on an older software of OpenVINO 2020. So there are some layers of the typical deep learning models that cannot be deployed, and also the inference memory, that it has a peak memory of 0.5 GB.
Go ahead. Just sorry, one moment.
Thank you for the presentation. You mentioned only ResNet 50, and since like the computational power at disposal in such a constraint setting is low, why not also trying out ResNet 18? Because many of those pre-trained strategies were also published for ResNet 18 backbone. Is there a reason, or simply because those are the standard in literature?
You know, that's a good question. Basically because even though they are also, of course, better in terms of latency and all of that, I wanted to benchmark FISATNet against the models that would give the best performance. So I would expect the ResNet 50 to give a better performance than the ResNet 18 when compared to FISATNet.
More questions? Otherwise, maybe it's time for a nice poster session and cocktails. Thank you again for your presentation.
Thank you.
Maybe, Nicolas, you have some announcements?
No, yeah, just to tell you that there will be some bus leaving from 8 something to Frascati Center. It will be just there, just nearby the building, waiting for you around 8. So no rush, we'll wait for you, but yeah, the poster session will close around 8 p.m. Thanks a lot. Enjoy.